My name is Kathy Hollis. I'm at the University of Manchester, and the Carbonate Forum is something that I've organised for the last 2 years with Fiona Whitaker, Pete Burgess, Rachel Wood, and Stephen Lokia and his team at SEDS Online. So a big thank you to Stephen and to Joanna at SEDS Online today for setting all this up and making it all happen. We've got a full day of talks ahead of us, so I'm not going to say very much. Just want to say we're all going to, this is being recorded, as you just heard, so please, if you keep your cameras off and keep your microphones off until the questions, and we will then have open discussions on each of the talks. So I'm going to hand over now to JP, who is going to chair the next session and explain to you how this is going to work. So welcome everybody, and I'm looking forward to a really good day of talks.
Thank you, Kat, and hi everybody. It's nice to be here to host the first section. We are going to have 3 presentations. The first one is from Grisel. She will talk about the geological process modeling of carbonate buildup system. Then we are going to have the Haiwei presentation that he will show us the controls on microbialite morphology. And then Ahmad will show the creative application of the conditional generative adversarial network. And just to remind all the speakers that they will have 12 minutes for the talk. I will give an oral advice when it lasts 2 minutes. And all the questions will be made by chat. I will read the questions by the end, and we'll have 7 minutes for discussion. So let's start with the Grisel.
Right, thank you. I'm going to share my screen now. Is it okay? Yes, right?
Yes.
All right. So good morning, good afternoon, everyone. Today, the title of my presentation is a representative depositional facies modeling workflow using multi-point statistics in TX carbonate buildup in Central Luconia Province. My name is Grisel Jimenez. The co-authors are Dr. Abdul Halim Latif, Professor Michael Popelreiter, and Mr. Kaider Ramatsia. Myself, I'm Grisel Jimenez. I'm research scientist, University Teknologi Petronas at the Center of Seismic Imaging, which is located in Seri Iskandar, Perak, Malaysia. If you have any questions regarding to this research, please do not hesitate to contact me through this email. So we'll start the presentation. I will start this presentation discussing about that in Central Luconia, building static models, especially in Central Luconia and in carbonate environments, proved to be complex due to the multidimensional nature of poroperm system. Karst, especially because we are talking about karst and also microporosity. And we are dealing basically the permeabilities in Luconia can arise from 1 millidarcies until 1,000 millidarcies. Therefore, the one first challenge here in Central Luconia is the property modeling, but also to build 3D facies, to understand the 3D facies architecture through the depositional system. All right, so the study area is located in offshore Sarawak, which is located in northwest Borneo, Malaysia, with an aerial extent of 40,000 kilometers squares, and we have over 250 isolated carbonate buildups that have aggregated mainly from a middle Miocene substrate. At the study field, we have in our research several fields that has been studied currently, but today we are going to talk about TX. TX is located in the northwestern part of Luconia Province and is one of the 7 stratigraphic culminations on a major mega platform, which is 30 per 50 kilometers large. So the carbonate buildup has experienced an aggradation phase followed by a backstepping phase during a series of third order sea level cyclicity during the middle Miocene. So as you can observe here, the stratigraphy of Central Luconia is roughly divided in 3. We have the MMU, which is middle Miocene deposits, which correspond to the cycle 1, 2, and 3. We have a mid-late Miocene carbonate, which correspond to cycle 4 and cycle 5, which is basically the focus of this study. And then we have the cycle 6 to cycle 8, which correspond basically to clastic. So overall, we have been seeing that most of the central Luconia models are based on seismic inversion models, which are very coarse. We have also the traditional web map-based models as well, and few forward stratigraphic models in this zone. But basically, modeling this traditional modeling algorithms tend to ignore some valuable information and might not be able to represent certain characteristics of the carbonate architecture in Luconia. So which is the data set that have been used for this? Basically have 3 wells and have a 3D seismic surveys, which is tied with 3 wells. Actually, in these 2 wells are where we have actually the core data, and the core data has been also calibrated with the stratigraphic markers and also with the seismic stratigraphy. So we have the stratigraphic model that has been developed, a zonation that also has been matched with the core information, and then we have isocores that has been developed as well correlation, and what we have is the basic from the aerial gradient and also the seismic surface, which is the pre-modeling part for the modeling stage. So this is basically a little bit about the MPS, which is to make it very simple. It's basically an algorithm that converts a training image. A training image is basically a geological conceptual model into a reservoir model. So basically, this is a training image example that we take from Semporna area. And then in this case, the bariogram will be replaced by the training image and the MPA, multi-point facies pattern. So this is the methodology. As you can see, we have a lot of information from core until satellite image, and have divided the workflow in 4 steps. The first step corresponds to the pre-modeling part. The step number 2 corresponds to create the training image. The 3 is to create an auxiliary variable. And finally, the number 4 is to run the MPS simulation. So as you can see here, overall, what we observe is that in terms of the seismic interpretation, the TX platform corresponds to a parallel layer stratigraphy. So we have the eastern margin, which is rim, which may correspond to a high energy organic reef, which is non-continuous and often chaotic reflectors. Then we can observe overall also erosion and faulting combined with depositional thinning. So in terms of qualitative and some quantitative analysis has been done in this case. What we can observe is basically some dimension that has been taken for different intervals, and that has given a little bit more understanding about the evolution of the platform. As well, we have extracted the seismic facies, different trends from the seismic. So in this case, as you can observe here, several geobodies has been extracted and then converted into depth to be uploaded into the model. The same, we have an integrated seismic core information. We have identified 4 zones and 8 seismic stratigraphic unit, and basically these 4 zones are mostly separated by floating and tie intervals that later on will be explained further in detail. So this is just to show you a little bit about how a powerful tool is the spectral decomposition in terms of to identify several structures from base to the top of the carbonate platform. So this information has been used to extract, in this case, seismic facies. As you can observe here, we have the karst seismic facies, which is correspond to SF5. And then we have other seismic facies that also has been identified. We can observe here the reef rim, which correspond to the SF1. And then we have the lagoon, the internal lagoon, which correspond to the green part, you can see here. And the patch reef, in some areas, we have been identified the patch reefs and also proximal reef as well. So this is one part, and then correlated with the core information, as you can observe here. And then just to show some examples, identifying, for example, the tide layer intervals has been also very important in terms to correlate integrate the well logs together with the seismic information and also with the core information. In this case, what we can observe is basically that in this case, we have pore types basically dominated by microporosity, and we have around the gamma ray usually between 20 to 40 API and a very high density in this case. Overall, we have also the progradational porous layers, which correspond to SS7. In SS7, what we have is basically porous layers similar to SS5, SS6, and also SS7. And this is considered in this in terms of reservoir potential as a good reservoir potential. And basically what we have in terms of core information is coral-dominated grindstone and coral-dominated floatstone indicated a good porosity. We're talking about 25% around porosity. And in terms of pore types, basically we have moldic and also baggy porosity. So in terms of the geomorphology, as you can observe here, some of the progradational intermals, they have developed these patch reef structures that also has been later on extracted as a geobodies. Finally, we have the karst layer, which correspond to SS2. As you can observe here, as correlated with, we have a very extensive karstification that is basically very characteristic in terms of the dendritic patterns, but also in terms of the core information. What we have is chalky limestone with moldic especially, and with abundant baggy porosity in the core samples, as you can observe here. And especially in terms of the range of the size of the karst, we have around 2 kilometers to 15 kilometers, and the presence might be influenced by the presence of the pre-existing faults in the zone. So basically this is the interval number 2, and then the next step is to create the training image. The training image is basically for us to guide the model in terms of facies neighborhood. So what we have is basically the talus, the reef rim, the proximal reef, shallow lagoon, deep lagoon, and patch reef are the main features. This has able to help us to create a training image, which is a trend property, and then we have also a 2D trend image. And later on, that has helped us to identify a 3D trend in for the simulation, and then use that together with the grid, and then to come up with the final model. So basically, what we have here is what we call auxiliary variables. Of course, that in MPS we can apply different kind of trend maps. In this case, the trend map that have been used is correlated with the energy. We expected to have lower energy, and we'd add the values of lower energy in the deep lagoon and also in the shallow lagoon. And then we expect to have a higher energy towards to the talus zone. So this information has been used later on in terms of auxiliary variable plus the grid, and then this is the result. So in terms of the result, this is the final grid. We can see that this simulation grid is simple, but is capable to create and also to represent the reef rim, which is very important for us in terms of modeling. And also to get...
You still have 2 minutes.
All right, thank you. So basically what we have is the reef rim is modeled in a continuous way, which is based on the spectral decomposition attribute and also from the geobodies. However, we don't have, as you can see, we don't have wells that have been drilled outside to the lagoon zone. So we don't have the control for that. So for that, this is very important information. So in terms of the conclusion, so this MPS method for this data set proved to create a simple model, which has combined a satellite image, which is an object-based concept, object-based element, which is based on comparative sedimentology. And then the proposed workflow, as you can see, include the pre-modeling part, which include integrate also information from core, but also logs, mass, plus the attributes and the geomorphology. And the step number 2 is to create this training image, or can be a set of training image with sufficient geological information. And the next step is to create this auxiliary variable or this trend map to handle one or more trends. Of course, for this example, I just show one of the trends. And the step number 4 is to simulate the positional facies, which is using the 2D training image plus the 3D auxiliary variables. So in terms of the model, the result can be in terms of realistic, because the objective was to model the reef rim, and can potentially enhance the credibility in terms of the carbonate platform model construction. And finally, the simple model can also help to improve to understand the reef rim growth pattern, and also the karst development for in the future research. So some publications, this is part of a publication from 2020, and I would like to acknowledge Malaysia Petroleum Management and the Center of Seismic Imaging, Becky Hughes, Ellis, and Sikar for helping in this research. Thank you very much.
Thank you, Grisel. The questions will be handled by chat. So please, if you have a question, I will read. So the first question is from Katie. She said, "Hi, Grisel, thank you for a really nice talk. Can you tell me a bit more about the karst? Does it occur at just one horizon or several? Did you say that you think it is controlled by faults?"
Thank you for your question. Very interesting question. So basically, the karst interval is in the base of the. Let me show this. Maybe this part. Yes, we have the base, and as you can observe here, the karst is basically in the northern part. And then towards the north, towards the top of the carbonate, there is no more development of karst. So yes, basically into the base. And the zone has been, we have some faults, but for this work, I didn't model yet the faults, as the objective was basically to model the reef rim. But it could be a very good, interesting topic for the future, to have the merge of the link between the karst and also the faulting. Thank you.
Thank you. We have one more question that is from Peter. Very interesting talking, Grisel. Thank you. The facies map in your training image looked very linear rather than a mosaic pattern. Do you think a facies mosaic model might be more realistic in a platform top setting where the water depth range is low?
You mean this training image?
Yeah. I think is the training image that you showed.
No, this one, that facies map is just very linear stripes, basically, rather than a mosaic.
Oh, yes, because in the workflow, you can change the surface of the contact between the two fishes. It is possible to make that. It is also possible, like in this case, to add the patch reef, which is something that maybe is not sometimes expected, because it's irregular. The surface is irregular, right? Yeah.
Okay, the third question is from Fiona. To follow up on Kathy's question, is the karst seen depositional? Is the northern area relatively elevated at the time of the deposition? Does karstification show trends toward away from the margin?
Right, yes. Well, to the base of the carbonate, if there are regional faults, yes, there are regional faults that might be linked with the control of the development of the karst. But as for this study, I did link some regional patterns, but not too much focus on the karst part. This is part of another research, which is basically for actually karst modeling. But I mean, for the karst part, I think will be also a very interesting part to develop furthermore. Yep.
The fourth question is from Ahmad. Hi, Grisel. Thanks for your talk. Does your spectral decomposition guided by window-based or horizon-based?
Window-based.
Okay, and the last question is from Muhammad. Is there any obvious clue for presence of karst on seismic sections?
Yes, as I have shown in one of these slides, you can see here, right? We have the Choky-file intervals in karst in the core, sorry, and we have also the baggy porosity that is very well, that is registered in several literature review, which is also very connected with the karst intervals.
Okay. Thanks, Grisel. I think our time for discussion is over. And I would
Thank
like
you.
to remind everyone that at the break, all the mic will be open and we can continue the discussion. And other advice that I think I didn't say clearly in the beginning, any type of record is forbidden. And then I will call our next presenter, that is Haiwei, and he will talk about controls on microbialite morphology. Yeah, perfect, Haiwei. Good presentation.
Okay, so thank you, everyone. Today I will talk about part of my PhD work, controls of microbialite morphology, using numerical forward model. So in today's presentation, I will start from a brief introduction to microbialites. Microbialites are present over a substantial fraction of Earth's history and record information useful for understanding the history of life and paleo environment. But reliable interpretation of microbialite morphology can be difficult due to the multiple combinations of controlling factors and their interactions. So we have developed the Stromatobite 3D, a reduced complexity but process-based numerical model to tackle this complexity. I will present 3 model sets to test how various hypothesized controls on environmental conditions could translate into different microbialite morphologies, followed by a comparison with what we see in the outcrop. Microbialites are organo-sedimentary deposits that have accreted by benthic microbial community. They usually have some internal fabrics, laminated or clotted, and they can form by precipitation or green trapping on their sticky microbial mat. In this study, we will focus on stromatolite. Several factors are important for their growth. Water chemistry controls rate of precipitation. Abundant extracellular polymetric substance, EPS, produced by microbes facilitates green trapping under agitated conditions. Microbialite morphologies are influenced by the spatial interaction of microbial community and environment at multiple scales. As we increase the scale of observation, there's a decreasing microbial influence and an increasing physical environmental control on microbialite expressions. In side view, stromatolite shape is determined by synoptic relief that in turn reflects accretion rate on the stromatolite surface relative to adjacent sediment. So high relative accretion rate generates high relief and simple shapes, where reduced relative accretion rate results in a low relief surface prone to overlap by adjacent sediment, generating more branching and irregular shapes. So our model, Stromatobite 3D, is a small-scale, fully deterministic model. It includes a simple hydrodynamic model that calculates flow magnitude for each point on the model grid. A dominant flow direction needs to be defined to represent conditions under strong wave or tidal influence environment. Multiple flow streamlines entering the model edge will follow this defined direction, but also interact with the topography due to refraction. As a result, flow magnitude is higher where lines are converging after passing a shallow area. In contrast, flows diverge and decelerate in deep water. We assume that external fine-grained sediments in suspension are entering the model at a user-specified maximum rate. They deposit and produce a mud to packstone lithology at risk depending on surface gradient and flow magnitude. They provide sediments to be trapped and bind into microbialite, but they can also inhibit growth if their concentration in the water column is too high and disturb the mat growth. Microbialite growth, especially by trapping and binding, favors agitated condition with enough but not too many suspended sediment. So the rate of microbialite growth is controlled by the calculated flow magnitude and the amount of sediment in suspension, highest at the optimum trapping and binding level and the threshold trapping and binding rate, respectively. We will change these two parameters later in the model and share their effects. Finally, when included, slope failure produces a breccia lithology if mountain surfaces become too steep and overstable after exceeding a specified critical angle theta. So these materials are transported downslope as bed load away from the microbialite mounds, but usually not very far. Here are the model inputs. This is the initial surface with relief up to ½ meter. The initial water depth is 1 meter and is rising slowly. 3 model sets are shown here with different tested input parameters and purposes. The first 2 sets do not include the breccia lithologies, so only include 2 lithologies. The first set consists of 9 model runs with different combinations of maximum in situ growth rate on the horizontal axis and the maximum background sedimentation rate on the vertical axis. All cross sections are shown perpendicular to the dominant flow direction, and these horizontal black lines represent timelines at 50-year increments. We see increasing growth rate or decreasing background sedimentation, or a combination of both, generates more persistent buildups with increased height, weight, and density. It also tends to increase surface relief to trap and bind new sediment for their own growth. So lateral sediment accretion and coalescence are facilitated. 4 model runs in the corners are discussed here. Case 1 shows a few localized small accumulations that primarily go vertically because both rates of deposition are low. Case 2, rapid growth is combined with slow sedimentation, so mounds go both laterally and vertically, producing large columns fully linked to each other. Also, the timelines are condensed in the youngest strata due to the limit of accommodation. In case 3, mounds are volumetrically small and quickly buried by sediment from suspension. In this particular case, the mounded accumulations are composed of largely suspended sediments with some microbialites, especially on steep flanks. In case 4, when both accumulation rates are high, microbialites are exhibit more complex and unstable morphologies resulting from rapid mound expansion and smothering, indicative of strong oscillating behaviors of 2 interacting processes. And this is evident that the microbialite thickness between successive timelines vary very rapidly. When looking at the time evolution of 2 depositional processes for these 4 model cases, each case has its own and very different trajectory. Case 1 shows very little oscillation, suggesting a potential dynamic equilibrium. Case 2 has a clear linear trend varying along the Case 2 has a clear linear trend varying along the vertical axis, such that microbialite accumulation increases initially to catch up with the rising water level. Then growth is limited by accommodation. Case 3 shows a similar trend to case 2, but it's varying along the horizontal axis. There's an initial increase of mud to packstone depletion until 50 years, followed by a rapid decrease. Because sedimentation from suspension is slope-dependent, increased surface relief and gradient prevent sediment settling on some steep mountain flanks, providing suitable locations for later microbial recolonization and microbialite accumulation. In case 4, both lithologies increased to about 60 years, and between 60 and 200 years, the data points become more scattered due to some strongly oscillating interactions between microbialite and adjacent sediments. And after 200 years, accommodation limits accumulations of both lithologies. And the second model set explores the contours of responses of mat building microbial community to flow magnitude and suspended sediment input. In situ growth rates are highest at the optimum trapping and binding level. So changing this critical value of flow magnitude represents different sensitivities and responses of microbial community to water flux and currents. Increasing this parameter tends to increase mud to packstone deposition because suspended sediment can fall out and get deposited across a broader range of flow magnitudes. Conversely, increasing the threshold trapping and binding rate allows more adjacent sediments to be trapped before pointling buildups, leading to slightly increased buildup size. The last set explores the complex behaviors of mount growth dynamics and local downslope sediment transport. The slope failure critical angle theta on vertical axis determines mount surface stability and therefore controls when and how many branches are shaped from microbial mounts. A low critical angle can quickly generate lots of branches from the base of growing mounts, but leaving insufficient in situ sediment to accrete vertically, therefore generate some surface relief. Therefore generate very little surface relief. And we see some mounds that are overwhelmed by adjacent sediment. And in comparison, a higher critical angle can delay and reduce the production of breccia, promoting in situ accumulation and producing mounds with increased relief and size. And for the same angle theta, rapid in situ growth can produce taller mounds and shed more materials from the growing mount for longer transport distance.
Hi, you have 2 more minutes.
Okay, thanks. The model captures some key features observed in outcrops, like a relationship between microbialite and adjacent sediment. The modeled mount size also match well with modern marine microbialites. And we see individual stromatolite morphology observed in Shark Bay can be replicated in our model. The internal stacking patterns indicated by the time lines are analogous to laminates and can be very useful. We see stratiform shaped microbialites, type 1. They develop very little surface relief, and they are characterized by flat and closely spaced time lines across both microbialite and adjacent mud to packstone. And these domical shaped mounts generate relief progressively through time, displaying low angle time lines with a gently convex upward structure. These club-shaped mounts show relative flat time lines at the base, from which the structure goes both laterally and vertically and display thicker convex up time lines towards the top. And also it's important to note that many types here are intermediate and gradational in nature. We propose a genetic classification of microbial strata based on the relevant importance of depositional processes and their products. So an in situ growth dominated group features closely spaced microbialite buildups, sometimes elongated in the dominant flow direction with little time equivalent mud to packstone. Early lithification is likely to be an essential process to help mounts stabilize at a higher surface angle against degradation. And this group is common in some high energy settings like the Shark Bay and the Bahamas. In contrast, a background sedimentation dominated group is favored by tranquil settings. The mud-rich Eddy-Carver and Nama group in Namibia is a good example. Low relative accretion rate perhaps suggests strong disturbance of the suspended sediment, which tend to develop smoother surfaces and leading to scattered localized accumulations. The third group has a noticeable proportion of breccia, which requires a delicate balance between growth, sedimentation, and downslope transport. And given this specific requirement, a high proportion of primary breccia at the time of deposition is maybe unusual and could occur under a fairly narrow range of environmental conditions or require some post-depositional processes such as dissolution, fracturing, and collapse. Okay, just to summarize, increasing in situ growth rate or decreasing background sedimentation rate or a combination of both tend to increase mound height, width, and density. Lateral growth can help develop microbialite rich and composite forms. When included, downslope sediment transport can be an important process for mound growth dynamics and morphologies. The comparison with modern Shark Bay works well and suggests modeled processes are at least one plausible explanation for observed natural geometry. And finally, modeled microbialite strata can be classified into 3 major genetic groups to recognize key end members. Okay, and thank you very much.
Thank you, Haiwei. And remind everyone that questions can be made by chat. We already have one question from Stephen Locker. Great presentation. Maybe I missed it, but do you consider how energy may affect the action of organisms that feed on the microbial community?
Yeah, that's an interesting question. And I think the answer is we don't really model this explicitly. And the reason, or maybe part of the reason is that, as I mentioned earlier, this kind of the microbial influence on precipitation and sediment trapping is it's quite obvious at a very small scale. But as you increase the scale of observation, this process becomes much harder to observe, and the environmental conditions of ambient water and sedimentation patterns become more important at a much larger scale. And I think a key message from this analysis, from this modeling work is focusing on, like, when we looking at like how the surface, the mound surface, the laminate, and how these laminates can translate into much larger scale external morphologies.
Okay, thank you, Haiwei. We have another question from Fiona. Lovely talks. Thanks, Haiwei. Have you tried to model fluid flow through your synthetic stratigraphic or the effect of the morphological and facies distribution contrasts? If you did, what did you show? If you did not, what do you imagine it would show? Thanks.
Actually, the hydrodynamic model we used, it's a very simple representation, and the aim of this hydrodynamic model is just to create some spatial interactions between flow and topography. So, and then we add a link between microbialite growth rate and the calculated hydrodynamic energy. I think a key question is, in reality, the the flow behaviors are more complex, and especially for many like shallow water microbialites. For example, those in the Bahamas and also Shark Bay, the water depth is only a few meters, and they change, I mean, annually. So there's so it's a bit difficult to incorporate those complexities in a numerical model. But I mean those are very interesting thoughts here, and we should perhaps incorporate those complexities like in future work.
Okay, and Fiona added a complement as is linked with the first question. I will read first. Sorry, that was clear in your talk. I meant after you had modeled the stratigraphics flow through the sediments. Okay, maybe Harry, we can move on for the next question, and you can talk with Fiona later. Kathy has a question. She said, "Hi, Howie, great work, thank you. Do you think your results are scalable? If I understood correctly, you have focused on small stromatolites, but do you think the same combination of process control the morphology of large buildups?"
Yeah, I think I think like sometimes I found, like, for example, there are definitely some similarities between like those microbialite I modeled and like coral reefs, for example. I think a key, for example, for coral reefs, we always get elevated carbonate accumulations along the rim, along the margin, and this is because increased carbonate production rate due to like easier access to nutrient and increased like hydrodynamic energy, and this is also the same, and the same fundamental controls also operate on this stromatobite 3D model. This is why we see that when those flow streamlines, when they converge, they usually are along the edge of this microbialite, which will increase the microbialite growth rate there. So yes, I think to your question, I think, yeah, there are definitely some similarities there.
Okay, thanks, Howie. I think we are at the limit of our time. We have to move to the next speaker. Thank you for the nice talking.
Thanks.
So I would like to invite Ahmad to do the next talking. He will talk about the creative application of the conditional generative adversarial network.
Yes. Can you see my screen now?
Yes, thank you.
All right. So let me just put pointer. Greetings, everyone. In this presentation, I am going to discuss the creative applications of the conditional generative adversarial network to promote data integration and visualization between geophysicists and carbonate sedimentologists. Before I begin, let's see these two pictures. On your left, we see an image of an outcrop. The upper part of this outcrop is a bedded strata that overlaps toward the chaotic to bulbous middle part. The lower part, again, is bedded strata. On the right side, we see an image of a carbonate platform with well-defined barriers, shoal, sandbars, inlet, reef margin, lagoon, etc. What if I were to tell you that the two images that we saw before actually does not exist in real life? The outcrop is actually a photorealistic rendition of a GPR image that you see in your left. Essentially, we turn the GPR data into the actual photorealistic rock model of the outcrop, while the carbonate platform image that you saw before is actually a photorealistic rendition of the seismic attribute time slice from the Luconia platform. The authors of this study mentioned that the Miocene Luconia platform is an analog to a typical modern carbonate platform in South China Sea. We literally just took the image from that study, ran our engine, and produced the image that we saw before. Therefore, we translate the seismic attribute into, let's say, a Google Earth of the Luconia platform. Therefore, for most sedimentologists, seeing the rock and depositional environment is much more informative than seeing geophysical image, since geophysical data presentation and visualization require specific expertise to interpret impedance, frequency, amplitude, etc. Therefore, we would like to bridge this interpreter-specific exclusivity by producing a common visual media for geophysical data visualization. The method that we implement is in the title, a conditional generative adversarial network. Without going too much into detail, in this deep learning method, there are two networks, the generator and the discriminator. The generator is making fake image, while the discriminator job is to catch that fake image. Both networks are trained in a competitive manner. With more iteration, the generator will learn to send better fake image, which mimic the real data, while the discriminator learn to discriminate better against the fake image. At the end, the iteration will stop when the generator can produce an image where the discriminator fails to catch. The two most common online application example of this method is the infamous deep fake, where you can blend someone's face to someone else's body, or to perform pixel-to-pixel image translation, as you see in these two examples below. In the following slides, we are going to present the two examples that we showed you before in the first slide, with the first example being the outcrop behind the outcrop from Gpr data, which reveals the 3D morphology of stromatoporoid coral buildups. This application is based on the radar-gram facies concept, where sedimentological features expressed in the outcrop is visually similar in character and reflection with the Gpr reflection data. In this slide, we see some example where geometrical expression of outcrop facies is very similar with their Gpr image counterpart. For example, this FC3A, which is the build-up, the stromatoporoid coral build-up in the outcrop is also seen as a build-up in the radar-gram. We simply then color label the outcrop photo from drone image and perform a forward modeling from that color labeled facies into a synthetic Gpr data. Then we pair the synthetic Gpr image with labeled facies. We train this couple to produce a network that can translate the Gpr image into the facies label. Secondly, we pair the facies label with outcrop photo. We train this couple to produce a network that can translate the facies label into outcrop photo. And then after we have these two trained network, we input the actual Gpr data, which will output the label facies. After that, we input the label facies to the second network, which will output the outcrop photo. The result during training can be seen here, where we see a progressive improvement during the training process, which we convert the Gpr image into an outcrop. Here, in the example of the animation, we see the synthetic Gpr utilized to train the networks to convert into facies label. And at the second network, please see the animation down here, where we see the progressive improvement of the networks to train the facies label that can produce the synthetic outcrop photos, especially the large build-up in the middle that has been rendered quite nicely in the synthetic outcrop. Using the two networks that we trained before, we convert the Gpr data in A and C into a model that we call outcrop behind the outcrop. In B is actually a outcrop rendition, photorealistic outcrop renditions from 2D Gpr networks in A. Figure D is actually a 3D behind the outcrop model from 3D Gpr data in C. This slide is showing you an example of how we utilize both the 2D and 3D composite outcrop behind the outcrop for data interpretation, as you can see here. And this is another example where the 2D composite lines, is utilized to perform outcrop behind the outcrop interpretation, where the dashed outlines are the interpreted build-ups. Notice how we can actually treat the outcrop as if it was a 2D composite Gpr lines. Another example is outcrop interpretation through 3D outcrop cube. In this example, we are showing you an outcrop depth slice, where you can see circular to pseudo-ellipsoid expressions of the stromatoporoid coral build-up in 3D. The blocky pixelization image that you see is a limitation that we are still working on due to the limit of data size. We cannot display our model in a full resolution due to the limited number of voxels that can be rendered in our standard GPU. Therefore, we upscale the model, which gives you this blocky appearance, but the circular pattern of the buildup can be seen very nicely in this model. The second example is seismic attributes to depositional environment. In this example, we perform modern analog in a literal sense, where we render seismic attribute time slice into satellite images. This is an example that we have seen in the first slide before, where we convert instantaneous frequency versus instantaneous phase attributes into an image of carbonate platform. Here we can see how closely they are in terms of locations of the reef margin, shoal, localized islands. Additionally, we also see inlet over here, sandbars, patch reefs that are not in the attribute time slice, but it rendered in the photorealistic model. Some other example is we convert RMS amplitude from Basinella lithocodium buildup. Here we see the buildup is outlined by the red colored high amplitude RMS map in red, and on B is the photorealistic renditions of the RMS amplitude in A, which interestingly enough, not all the high amplitude anomalies are rendered as a buildups, can be seen as this chaotic patchy looking features in the image, but some of them are rendered as sand, as you can see here. Lastly, we are building a graphical user interface that will allow us as a user, as a sedimentologist, to manually edit the image after we convert them from seismic attributes. This is a work in progress, therefore the GUI is still rudimentary. However, the idea is to manually edit the image after the translation, where we see unrealistic render, as well as to draw as many models and scenarios to the interpretation derived from seismic attributes. For example, we see that in your left, I just draw simple patch reef in the label, and on your right, the patch reef will draw the photorealistic renditions of that. Some of the examples are included as well, where I try to build an inlet in the carbonate platform. I just cut this, for example, with the yellow, and then it will create an inlet over here as well. So the engine is running. At the moment, our example is actually just carbonate platform. However, it can be applied for any kind of depositional settings, like for example, channels, fluvial channels, etc. But the GUI is ready. With that, I would like to conclude that we have developed a workflow that can translate geophysical image into photorealistic model of outcrop and modern depositional analog, which the workflow itself utilizes a conditional generative adversarial networks. And we have provided you 2 examples as an outcrop behind the outcrop and seismic attributes to modern depositional environment. And as a future work, I would like you to see this picture. You see again an outcrop. You see the parallel bedded strata on the top and chaotic strata in the middle, which we can outline and differentiate between them. And again, this outcrop does not exist in real life. This outcrop is a photorealistic renditions of the acoustic impedance image of the stromatoporoid coral buildup area. Again, we see high amplitude corresponds to the buildups, low amplitude at the top corresponds to the parallel bedded strata. With that, these are the references, and thank you for the listening.
Thank you, Ahmed. It's open for question. Just to remind you, the questions is made by chat. So if you have a question for Ahmed, and in the meantime, when we are waiting for the chat question, I have one question.
Sure.
Have you applied it with different hydrothermal or different diagenetic pattern?
The question is, so the engine itself is
Yes.
a forward model to pixel translation. As long as you have one image that can be correlated with other image and it has similar matching pattern, it will generate it, irrespective whether it's like hydrothermal applications or diagenetic applications or facies applications. As long as it has a matching pattern, it will reproduce that. So the application that I'm showing you right now is in the carbonate facies. It can be diagenetic as well, as long as it has a pattern in both datasets that can be utilized.
Okay, thank you. We have a question from Maulana. Good presentation, Ahmed. How is the minimum resolution to capture, visualize the field carbonate outcrops? Thank you.
Yeah, thank you very much. The resolution that we generate in the photorealistic synthetic outcrop is the resolutions of the outcrop image. For example, in our case, the resolutions of the drone dataset that we use is 3 centimeter per pixel. The model, the digital behind the outcrop model that we generate is at 3 centimeter per pixel as well, irrespective whether the resolutions of the Gpr data is let's say 20 centimeter or so. So it will force the resolution into the resolutions of the ground truth image.
Thank you. Stephen Gershon has a question. Perhaps I misunderstood, but do you have good ground truthing of the distribution of facies? Examples, cores?
The answer of that, yes. In this presentation, I do not show that, but in the paper that we are writing, we do drill behind the outcrop at the location as a blind test, and we found out the matching is actually quite good, about 0.85, i.e. the facies that we predict in the behind the outcrop model with the facies that we describe from the core matching 85%.
Okay, thank you. The next question is from Peter Burgess. Very interesting talk. Thank you. Is there a way to flag the uncertainty inherent in the seismic attribute map into the new image to avoid problems with overinterpretation?
So the question is, so in addition to the image that we generate, we also generate another map, which I do not show. Is basically block by block confidence value, let's say that. So if there is like confidence value of, let's say, 0.6 to 0.7, that means that this particular block, let's say like 50 by 50 pixels, does not actually have a good pattern with the ground truth image, but it can still reproduce the photorealistic image. But let's say but with 0.6 or 0.5 sureness, not sureness, what you call certainty, let's say. Yes, the answer of that, yes, we do have it, but we do not display it. We just display the actual, the final results. We do have the map before the actual image, which is basically showing you how closely the patterns are matched with the actual input data, which can be used as a proxy to uncertainty.
Okay, we have one more question from Alhan. Thank you, Ahmed. Interesting talk. Can these images be compiled and constructed a 3D image or model of the basin out of them?
Yes, but it will require so many training images and in a different part of basins and in a different patches. Let's say, for example, we would like to reconstruct an Arabian platform during Jurassic, which is 1,000 kilometer long ramp, like for example. We will have to differentiate between one region with other region, and each region will have their separate training images, which can be done, but it will require like hundreds, if not thousands, of images for training. But it can be done for sure.
Okay, the next question is from Regimer. Very interesting talk. Which petrophysical properties do you assign to the individual facies when you produce your models?
So any petrophysical properties that are utilized to produce the facies model. Let's say if one geophysicist are more let's say one geophysicist like using acoustic impedance to correlate their acoustic impedance map with facies, we can forward model from acoustic impedance. Or for example, in the first presentation in this session, Grisel used spectral decomposition from frequency. We can use spectral decomposition of the frequency as well. The engine stays the same, but the input and the output will be different. So the input can be any properties, as long as you can relate that to the positional facies.
Okay. We have another question from Maven. Very interesting talk. Is the engine code available in the public domain, or how we can get access to it?
The engine is still in progress, in working. However, if you just Google pix-to-pix TensorFlow, you can see people actually working using similar kind of similar method. I mean, the ideas of this method is basically when I saw people drawing Pikachu just from squiggly lines. So why can't we just do that for geology as well? So the code is for our specific application is not available yet, but the base of the code, you can always Google it, find it in GitHub. Just Google like TensorFlow pix-to-pix. That should be there.
Okay, and we have one question for Noor. Very interesting topic, Ahmad. Which geophysical tool did you use to test your model beside GPR?
As I presented before, we tried it in GPR, we tried it in acoustic impedance. Apart from those two, we have not tried anything yet. However, maybe it will be interesting to try resistivity. But so far we only apply it for GPR and seismic.
Okay, one last question because we are running out of time. We have a question from Fiona. Really neat tool. How do you move from a 2D Gpr section to a 3D Gpr model?
Oh, so the GPR data that we have is both 2D and 3D. So for example, on the 2D case, we just input the 2D GPR image and output 2D outcrop image. Straightforward. But for 3D GPR cube, we separate that into multiple inlines. One inlines until inline number, let's say hundreds. And then we render each individual inline into each individual 2D outcrop images, and we construct a 3D model from those.
Okay. Thank you, Ahmed. I think we are done here. Our next talking is 10:30. We have 25 minutes of break, and when we encourage you to keep the discussion. Thank you.
Thank you.
Thank you very much to all our first presenters. Just some sort of meeting management thoughts. First of all, what we're going to do now is during the coffee break, of course, you're all encouraged to go and get lots of beverage of your choice. But what we'll do now is unblock all the microphones. We'll unblock all the videos so everybody can just have a general free-for-all discussion. Please keep it to the science. If you've got any more questions for our presenters, please ask them. They were terrific presentations. Also, we found out that some people don't do social media. Who heard of such a thing? For those of you that need a copy of our schedule for the day, it's available on our Twitter link, our Twitter feed. But if you haven't got a copy, just send me a message. So send a message to the main SEDS Online, or to everyone if you really want to, but just send it to that main SEDS Online, send it to me, and I will get that message. So you can send it through the message chat facility here. Just send a message with your email address and I will email you the schedule if you're not into the social media world. Right, I'm going to unblock everything now. If there's anything else, well, just email me. Thanks very much, everybody. Oh, Kathy, you're going to say something.
Yes. Do the speakers for next session need to go into the green room?
Kathy, very much correct. Please, yes. All speakers for the next session. I will now don't go to the green room yet. I will tell you in a minute. I will announce when you can go to the green room, but you will be going to the green room in about a minute's time. Thanks. Okay, everybody, you should be able to unlock your videos. You should be able to unmute yourselves. So please start chatting. In fact, JP, you should be leading this chat. So where's JP? JP should definitely be congratulated. It's the crack of doom where he is. What time is it with you, JP?
Now it's 6 a.m.
Oh, you deserve a medal. Well done. Okay, I leave it to you. It's your.
Okay. Oh, I have been invited to the green room, but I think I will stay here. Not now. Okay. We have Ahmed. We have a question. Maybe if you want to answer to break the ice from Al-Saman. Wonderful. Thanks, Ahmed. It would be interesting to apply it for borehole images and get semi-core images with low cost.
Thank you. The person that asked the question read my mind. We would like to do that as well. In fact, we developed another step on that. We would like to develop. We're still in the brainstorming process. A synthetic core generator where you input your well log data, let's say porosity, permeability, density, sonic, etc. Run the engine and output the core image out of that. But it's still a long way to go. Not just the borehole image, but the actual petrophysical properties into image. So.
Very interesting. Thank you, Ahmed. And actually, currently I'm working for my master project on this similar approach to model some carbonate formations here. And I'm trying to model the carbonates from the petrophysical logs that I have. So I'm trying to find some kind of tools. So thanks for giving us your thoughts on this.
Thank you. You're most welcome.
Okay, maybe we can try to organizing the discussion and get the opportunity for the first talk from Grisel to be back. And if we have further questions that we were not able to answer, I think it's the time to talk with Grisel.
Can I ask Grisel another question? Is that all right? I was interested in your flooding surface.
Sorry, Fiona, I was waiting for somebody I could interrupt, and I can interrupt you. Sorry.
You can interrupt me anytime.
I want to, everybody that's talking in the next session, the green room is now open for you. Please, can you go to the green room if you're talking in the next session? Thanks very much, Fiona. Please continue.
Stephen, I am in the next session. Should I go to the green room?
No, you do not need to go to the green room. Everybody else does.
Okay, perfectly.
Thank you.
Thank you.
Okay, I'll be in the green room in a moment. So I was interested in your flooding surface, which you describe as, I think if I remember rightly, lots of microporosity. And I was wondering if that flooding surface represented a shallow marine hard ground, and whether indeed there were multiple flooding surfaces that were low porosity.
Sorry, I just lost the last part because the internet is a little bit unstable.
The question was about your marine flooding surfaces, and I recall you saying they were full of microporosity, but also that they were overall low permeability surfaces. And I was wondering if they represented early marine hard grounds.
In the core description, I mean, so far we didn't found evidence about the hard grounds. However, I mean, the information from the log basically show us the microporosity, and then also very low, I mean, from literature review, from the work based from Weinkamp, basically, and from King, we have the evidence that no hard ground has been found yet into the core. However, the tight layers, because they are very tight, these levels, they can be interpreted also as baffles in the reservoir zonation, during the reservoir zonation. Yeah.
So you think they are fine-grained sediments? That's why they're tight layers?
Yes, also the compaction has been a very important role into the evolution of the platform, and the effect also of some of the intervals, because the karst intervals, they were very, some of them, they're very huge. We have dimensions of around 15 kilometers, and we have a very interesting karst network especially in the northern part, but I didn't cover to model that part. Because we don't have core data there. The core data is basically more into the lagunal site, which is basically in the center. There is no other wells that has been covered a little bit outside to try to model, because for the purpose of the project, I was basically to try to to do the modeling of the reef rim. So the idea was to understand how was the evolution during the base of the carbonate near to the cycle 2 and cycle 3, and then to understand towards to the top. To the top of the carbonate, which is basically the dimension of the platform when we have all the clastic coming from the from the clastic side.
Okay, thank you very much.
Sure, welcome.
We have a question from Haiwei. Hello, Kershaw. The model at the moment do not differentiate the type of microbial organism. So is the question that I missed? I will read the question first, then maybe, if you want to answer, go ahead. The question is, thanks for the nice talk. Does your modeling including effects of different kinds of microbial organisms? Example, some may be photosynthetic, other may not. Does the model allow this difference?
No, I think at the moment, like it's a bit difficult, to differentiate the influence of these organisms in a model, which gonna require like huge computational powers. And I think, in fact, the process of precipitation is super complex here, and I think it's very challenging to model using a geocellular model. So, and also, but I think we do not set I think to your question, like are those like photosynthetic? Well, I think we do not set a depth-dependent production rate curve like for those like coral reefs. Yeah, so it's sort of flexible. Yeah, and I think this goes back to the point like Cassie raised. Are you really modeling like the stromatolite, and can the modeling results be extended to other like carbonate systems? So I think, well, it's a bit flexible because the only two factors we are considering is hydrodynamic energy, water turbulence, and the sedimentation patterns. And in the talk last year, I showed some results about how the substrate control gonna affect the stromatolite distribution using exactly the same model. And so I think to your question, and I would like to know, like, maybe do you have any good suggestions?
I'm thinking about it. Yeah, thank you for the very interesting talk. One of the problems with stromatolites is that they are really very variable structures. So, for example, you can have stromatolites which are made out of simply layers of micritic sediment with no evidence at all of any microbial organism present, and yet they look like they've been constructed by organic processes. And in contrast to that, you can have other stromatolites which are made effectively of more almost like clotted fabrics, where you get the impression there's automicritic processes taking place, which would be much more easily understandable as organic processes. So the difficulty is discriminating between these two things, and therefore also knowing whether or not there is any organic process involved. So maybe what you could think about doing is adding to your algorithms so that you can allow some kind of automatic growth, which could be a sort of proxy for a photosynthetic development, something like that. My problem is I'm not a modeler. I just look at rock. I'm a bit old and out of the. I probably should try and learn more about the modeling things, but my learning is from the rocks themselves, and that's why I get these questions about whether or not you can really apply the modeling in a very satisfactory way, because you do need to know about the processes or whether there's any organic activity or not. So maybe what you could think about doing is choose some real stromatolites which actually contain evidence of organic processes and see if you can model those, incorporating some kind of automatic growth process that might be simulating the effects of light, for example.
Yeah, okay. Thanks for your suggestions. And I think actually those models are actually created not for me, but actually for you, like outcrop experienced outcrop geologists like you. Yeah. So, and I think, and also like to your point, like sometimes they are clotted, sometimes they are kind of laminated, and they are always like gradational. These two types here, and.
Yeah.
And I think like you highlighted this kind of like varieties of their internal fabrics and the lack of direct evidence of like microbial influence or involvement here. It's always like it's always tricky to model, yeah. And but yeah, go ahead.
I was going to say it certainly would be interesting if you can try to include some subroutines in your modeling, so that it has some kind of automatic growth which would be simulating a photosynthetic effect, something like that. You could try to see what effects those things have on the model, and see how that might relate to real stromatolites.
Yeah. Okay. And actually, like what I was thinking is actually to just focus on relative like small scale, like 2D morphology. So not going to like 3D, just going to go back to 2D. And actually, like for me, I think a problem I always found is because many of the morphologies I produce are kind of massive, like domal or kind of stratiform. But I think in the geological record, especially for those in like these arcane and early Proterozoic stromatolites, they're always kind of branched and showing like more complex kind of shapes here. And I think at the moment, like my model do not really capture this kind of branching patterns. So
you showed a very nice photograph from the Tieling Formation localities. I've been to that. I have a picture exactly the same as your photograph. I've been to that exact location, and if you look very carefully at that nice vertical face that you photographed, there are from other examples of some of those branches which are broken, and they're broken into pieces, so they were clearly solid objects growing up as branches. So they weren't controlled by sedimentation. They were growing as branching structures on the seabed, and then they were damaged by probably storm activity.
Okay, thank you guys for the discussion. I would like
just
to
one very quick comment, Stephen. Photosynthesis is in the model. It's just in most of the model runs we do, the water depth range is so small that it makes no difference, because it just doesn't get significantly lighter or darker across the range that the mound stromatolites are growing. So we have got it in there, and we do distinguish that in situ between trapping and all those things. It's just it's a little bit hard to summarize all of that in the talk, I think.
Yeah,
So
of course,
if you look at the papers, I mean, it'd be interesting to have your feedback on those, because everything's described, obviously, then you can, you can see all the details laid out.
Could you kindly send me the papers? Will that be?
Yeah, okay, no problem. Yeah,
Yeah,
no problem.
yeah.
I will do this. Yeah.
Yeah.
Okay,
No hurry.
thank you, guys.
Thank you very
I
much.
would like, well, thank you, Stephen. I would like to ask if someone else have more question for the three presenters. We have only 7 minutes later, so is the opportunity to solve any doubt that was left.
So I can ask a question for, was it Ahmed, about the map generation? So what I was trying to get at in the question that I asked was that seismic attribute maps are very uncertain, right? They're not reality. They're a model, and therefore what you're doing here is modeling a model, possibly modeling a model of a model. There's 3 steps, and therefore it's really important that the uncertainty in that original model, because that's what it is, it's not data, it's not fact, it's an interpretation of an attribute map, right? That then goes into the uncertainty from that propagates forward. And obviously the danger with that kind of uncertainty propagation is you quickly end up with 100% uncertainty. Right. So I think, is there a way to actually, to do that in the method you described? Because I don't think what you said was exactly that, was it? I think it was a slightly different thing you were talking about when you described it before, but maybe I misunderstood.
Oh, yes. So what I mentioned in the answer to your question was, so what we did was we try to find a matching in the pattern between geophysical properties, whether that's like amplitude, impedance, etc., with the actual patterns that we see in the real analog depositional environment. Let's say if patch rift is circular and we see circular features in the impedance map, it will match both those two as a pair.
Oh, I see.
So it's based on that geometrical similarities. So if let's say for example, we see a circular pattern that are not patch rift, but in the actual in the training image that we use, that circular it can be determined as rift. The photorealistic image will produce that as a patch rift, although it might not be. For example, it might be just acquisition artifact. That's why we have that GUI, the graphical user interface, where we can manually edit that. So the geologist can come and then let's say, oh, I would like to delete this part because this is actually not built up. Let's say this is just basically an acquisition mark.
Okay. But the issue will be that the geologist probably wouldn't know either, right? And I mean, if you think about that, okay, so a round feature, think of all the things that a round feature could be on the platform top. It could be a karst pit of some sort. It could be a buildup of all sorts of different types. It could just be a rounded, grainstone shoal of some sort that happens to have that shape. And so this is the issue, isn't it? Really, how do you reflect that uncertainty? I'm not even getting onto the seismic attribute, noise and such like. How do you? I mean, can you reflect that kind of uncertainty in the final map?
Yes. So what we can do is we can reproduce that circular features into different realization. Let's say, for example, this round feature can be rift. It can be shoal bodies. It can be, so there will be like model A, model B, model C. What I am showing you right now is just the applications of the engine. The engine itself, we believe, is working, but the actual application for uncertainty and everything will be highly dependent on the geologist itself that work behind the buttons. Basically, it is not actually cutting the interpreter from the equation. It is basically just putting them into a more geological features rather than geophysical properties, let's say.
But a sensible interpreter using this tool will still end up with several scenarios.
Yes,
right?
yes,
That's,
definitely.
I suppose, kind of the point, isn't it? Cool. That was really interesting, Ahmad. Thank you very much.
Thank you.
Can I just ask a quick question that's just to everybody? If Khalil Azanud, I think the name is, Khalil Azanud, if you're in the room, but maybe under a different name, because I know that sometimes happens, if you are here, please can you make yourself known to me? Otherwise, that's me. Go.
Hi, welcome back, everybody.
Hi, everyone.
Some good discussion going on during the break. We were hiding in the green room. So thank you, JP, for chairing the last session and keeping that going. That was a really fantastic start to the day. I think the 3 really, really good talks there. So well done to everybody. And now we've got 5 talks coming up to carry on the theme of carbonate sedimentology. I'm co-chairing this with Fiona Whitaker. I will disappear very soon. Unfortunately, I'm about double booking, so I'm going to introduce the session, first couple, and then I will return as soon as I can. So as the speakers know, they have 12 minutes, and then we will go to questions in the chat afterwards. And yeah, just a reminder to everybody that there's to be no recording, please. There will be a recording of everything provided by SEDS Online uploaded to YouTube. So please refrain from taking any pictures or recordings yourself. Okay, so to get us started, first talk this morning, Maulana Aditama, he's going to, from the University of Manchester, working with me. He's going to talk about structural and stratigraphic controls on carbonate platform growth, lower Carboniferous limestone in the Southern Irish Sea Basin. So Maulana, it's over to you.
Yeah, right. Can you hear me? Yeah. Right. Good morning, everyone. My name is Maulana from University of Manchester. I am now currently first-year PhD students. To be exact, now is my 7 months working in University of Manchester since I arrived at October last year. And I'm gonna give you my project's title is Structure and Stratigraphic Control on Carbonate Platform Growth of Upper Mississippi and Southern of Irish Sea. The main aim of this research is to understand the structure control on structure architecture of Mississippian carbonate and to determine the predictive framework for the growth, demise, and thickness based on the seismic data. And we are also doing some steps of the objectives, which is to determine the horizon interpretation, to identify the shape, platform margin profile of the carbonates, and then construct the fault model and possible structure reconstruction, controlling the Mississippian carbonates, and creating possible scenario schematic model of the Mississippian limestone deposition in the southern of the Irish Sea. And this is the workflow of my 7 months working in University of Manchester. Basically, we already run of data analysis, literature review, and then observation, hypothesis, and some of working in seismic modeling. We also doing some of the structure framework model in 3D data. And we are also combining with the field observation this summer. So we are going to the Landudno to examine the carbonate limestone outcrops in the Crete Orme Aspians in 23rd of May. We are trying to combine those research, the subsurface data with the outcrop as well. And then this is the data sets. Thank you to the British Geological Survey for providing the data. And also, if you see in this, the left map here, we have 25 wells spread it to the Irish Sea, and with 2D lines and then 3D lines. The pink one is the 3D seismic data lines that we are now currently working with. And we had more than 4 and 5 cubes in these pink lines. Actually, this is the stack of the seismic cubes in the southern part. And Also, we are aiming to get the analog outcrops in the Landudno. It's around here in the northwest coastline. And then talking a little bit about the geology of the Irish Sea. This is from the Faroe 2018 about the key Mississippian structural elements, which divided by some parts of the tilt block and then high shelf and then deeper marine. So we go from the high shelf from the south, then go to the basin deeper around the convoy platform, and then go to the tilt block slightly to the north towards the Manx and platform in the north. And if we combine to the current or previous work from the PGS in the right side here in the reports, which they did the 2D subsurface map, mostly of the structural orientation has a north to south major structural orientations. And we know, like from the literatures, that they had a differential periods of carbonate platform growth and uplift, and then plurial, which are very complicated tectonic settings, and it possibly can the carbonate itself has a very high variability of the thickness within the southern of Irish Basin. And this is the pictures at the outcrop that we are going to go this summer. And then the methods that we are working at the moment, we try to combine the seismic models. We're using a seismic facies and then also the fault mapping using the structural framework model. And then we also try to observe in the field what happened for the upper Mississippian, especially because in the subsurface we had a marker at the top Visian, and then intravisian, and then pastonation of deeper carbonate deposition. However, not all of the well are touching the top of the Mississippian carbonates. Most of them are in the Permian. So we try to see how this from the seismic data, the change of the reflector from the Poland shear formation towards the upper Visian. And this is the research graph. We try to build a triangle from the previous work, and then how can we fill in from the gap from the previous work. And the investigation main is how to understand and to investigate the development of carbonate growth, how they growth and then they got demise, and how the each of the horse or platform, they had a multiple of the potential carbonate mounts. We try to map them as well. And the limitation, because of that I mentioned before, there are no many wells that penetrates towards the Mississippian carbonate. So it's for us, we have to pay attention with some analogs to the onshore data as well, and then try to see what happened to the subsurface from the seismic data as well. And this is the chronostratigraphic and tectonic events that I made based on the reference from Fraser and Calthorpe, 2003. And if you see here, we are focusing at the top Visian and then intravisian and the base tornation. This is actually the base Mississippian carbonates. And if we correlate this one towards the event as well, they are experience with a multiple of the tectonic setting started by the pre-Carboniferous extension. They got rifting, they got the carbonate system platform deposited within the start from the marine transgression, and then they go the ram at the rim self in here, and then they go inversion, and at the end of the precantion, they got in here a variscan inversion as well. So they started from platform growth at the start of the Visian towards the platform demise, and we can try to see later in the map. And this is what I did. In the first steps, I try to do all the QC data and correlation, enhance the seismic, and then try to minimize the noise, because not all the 2D data is good. So we try to maximize the 2D and 3D data so we can see the reflector itself and make sure that the well and the seismic is tight enough, so we see exactly where is the apple bar, where is the millstone in here, and some of the marker that we can correlate with the wells. And the interpretation, this is the most interesting part, because we use 3D data in this stage of the research, and we correlate one of the section. If we see here, the wells not penetrates deeper to the top Visean. However, they are at the Permian and then the late stage of the Namurian as well. So we also use the attribute variance slicing to see is there any structure controls at the side of the top Visean. If we see there is a line, we try to delineate where's the gap, and we got like very interesting feature in there, because very complicated. Most of the top Visean experience the later stage of the Variscan inversion. And if we see focusing in here, we try to define the character of the seismic based on all the data we got from the high reflector, because we have the upper thick of the Paola shell formation, and then they go down with the top Visean carbonate. So it's very high reflector with a high amplitude, and some of them they got the high angle slope from the platform margin towards the deeper basin. And this is the results for the Southern Irish Basin, the regional interpretation. I show you before the data map. So this is the 3D section map of the subsurface. So we're working at this 3D hole in the southern parts. And then actually this interpretation is, they consist of like 4 to 5 major structure elements experienced from the top of the let's say like around Permian down towards the basement. So out there of that, they also had a the Mississippian structure as well. If you see the upper Mississippian carbonate shows lower value of the elevation time in the southern area. So it's slightly to the south and they becoming shallower. If you see in the base, they are very, very huge of the lineament of the Mississippian carbonate. It seems that possibly they are backstepping towards the top in here in top Visean in towards the south, and then probably because we had a angle slope in here towards the north, slightly around 44 degrees of angle of the slope around here. And it's very interesting because in here we had a multiple of possible mounts, and this is very high of the Timster platform, and they are bounding by a major fault in here. So probably we can see later on the thickness map that yes, there is a slope change and then a thickness variation in around here. And then this is why we try to see a little bit closer to the Hamilton. If you see here, 3D Hamilton, we try to build the line through the wells in here. So we can see how the upper part of the Visean, which is the Namurian and the Poland shell formation, the most of siliciclastic, they are overlapping towards the top of the inner platform facies. And then we can see like most of the in here, platform margin, they have a slightly thicker, and then they going to the basinal area, they have like thinnings, but it's not too much. But we can see maybe in the later stage, in the western part, they are thinning around 100 millisecond. And then this is how we try to see how the carbonate paleo high from the RMS amplitude. We try to make the horizontal slice to see how this carbonate bounds like can develop in the higher house platform structures. And we try to divide into the 5 possible carbonate paleo high in there based on the higher value of the RMS amplitude. And most of them, they are bounded by structures. And this is how, right, thank you.
2 minutes.
Yeah, so this is the thickness analysis that we mentioned before, how we divided this into the 3 major area. It's very interesting because previous references, they mentioned this as well, but we try to see the gaps because the previous research slightly mentioned about this the consistent about the structural elements within the spread of the basin from west to east, and the most structural elements north to south. However, in this research, it shows that it is more complicated, that it it was taught before. It's like there is in south here, we can see how the P4 is very thick carbonates and it's controlled by the Kogert faults in here. And it's going to be more interesting because in the Gogurt fault here, we had a inversion structure in the lates of the Variscan inversion. They have a bending feature of the P4 of the carbonates. And if we see here that we mentioned at P8 that before the backstepping features from the base of the tornation and towards here to the south, and then we can see probably in the field the great orm of Aspian deposition. It can be also give us the thought how can it be deposited in here and how they grow through the time. So we are working at the moment to this as well to model how the P1, P2 they are connected. And the one interesting part is we found that there is a potential relay RAM structure in here. They are started the structure in here. They are started growth isolated, and then they try to make interaction, but it didn't happen for the bridge, and then it stopped. So possibly it's like the second stage of the RAM structure happened in here. So we are now at the moment still working to try to build the structure evolution model and to build its more possible ways how it can be what you call a shape the carbonate itself. And this is the conclusion. Extensional structure is north-south oriented, controlled by the shape of carbonate platform, this one. And how this is, margin is very complicated. It's controlled by complex nonlinear fault termination, and also the thickness is carbonate is controlled by the faults, and then ranging from 350 to 450 milliseconds of thickness. And yeah, this is the future work. We are trying to create structure stratigraphic evolution, and we try to observe, is there any calcification feature from the seismic data? Is that possible? Is that feasible as well? So, yep. Thank you so much for all parts that support my research.
Thank you very much, Milana. So if you've got any questions, please can you type those into the chat? We'll just bring everybody back up again. Dan, you have your hand up. If there was a question, did you want to just type that in the chat? Okay.
Oh, sorry, that was by accident.
That's okay. That's fine then. Good. Thank you. Okay. Not seeing any questions come up at the moment. I mean, I have lots of questions, but I'm working on this, so maybe not the right person to ask at the moment. Okay, so question from Jim coming in. Hi, Milana, really nice talk on very challenging data, and that's certainly true. There are likely variable thickness of evaporites in the overburden. Do you think this may impact the variations of time thickness in the Visayan? And are you planning to do a depth conversion to investigate this?
Right. Thank you. It's a very good question. Actually, it can be like impacting to the thickness by the overburden, but we actually at the moment don't know, like, is that the main measure is the overburden, or is probably we think about when the upper Visayan are deposited, because the tectonics still happen, they might be in one part they are rich, and the one part they are not, because when they are more deposited mostly in the horse platform structure, which is quietly higher parts, and then the sea level is slightly shallower, they get more rich develop whereby when they go the platform margin slope deeper parts, it's going to be more linear and then more like fine as well. So we still consider that part as well, but we don't have evidence at the moment about the compaction and something like that, overburden and something. Because before I work in the slightly data in the Irish Atlantic margin, I examined before as well. There is a potential like that, but that's the Irish Atlantic margin for the Sherwood sandstone. There was a over compaction section that was in the west, but for this section, probably we take into account with this as well. But we try to find, is that any what you call like variable thickness due to the the evaporant. Yeah, and the second one, are you planning to depth conversion? At the moment, we don't have a exact what you call marker or well data that penetrates towards the upper Mississippian. So we discussed with Matthews, my supervisor. Probably we try to analog the velocity from the upper basins and the eastern basins, the onshore data. Probably we try to that, but that is very high uncertainty. It's so challenging because actually, if we want to see the shape and platform margin as something, probably we can use the milliseconds time section. But if we try to see like how this impacted towards the overburden or something, we will try to what you call try to depth conversion. But again, it's very uncertainty because we're gonna try to make some assumption of the velocity interval and put it towards the down of the seismic line in the our horizons.
Thank you, Milana. Yeah, no, good questions. This is really tricky data and lots of widely spaced 2D lines and very few well penetrations. Okay, I think we're almost up to time anyway. So thank you very much for getting this session started, Milana. And oh, hang on, sorry.
Oh, yeah.
Fiona, you're not off the hook yet. What are your plans for fieldwork?
Yeah, so actually we are trying to observe because the upper Vizian Mississippian limestone in the field, because we had the data which is the carbonate itself very deep, like around 2,000 milliseconds deeper, and then go shallower towards the south. In seismic, it's not feasible. We see like what happened. Like, is that like any internal mounds or something else? Like, is there any like stromatolite or something? But again, we need to see what happened in more detail. I mean, if at the top Asbian, and then is there any what you call geological sense that can be our underline to make interpretation subsurface? Because like in subsurface, there is a lot of factors that affects your carbonate shape, affects your what you call like the carbonate feature. So we're gonna see like details. So after that, we can talk about what happened subsurface. So we need to see the rocks, we need to see the carbonates, and then we can try to make links between that. Thank you.
Excellent. Thank you. Right, that's great. Thanks ever so much. And we will have to move on now, I think. So next talk is from Penchang Zhang. Penchang's there. Excellent. Hi. And we'll talk about microalgae influence on hydromagnesite formation. So when you're ready, Penchang,
yes. Yes. Can you see the screen? Yeah.
Yes, that's brilliant. Thank you.
Okay. Hello everyone. To be honest, I'm a master student. And I'm very honored to participate in this forum. Today, I want to share with you one of our recent exciting discoveries. As you can see the screen, my name is Pengcheng Zhang. I come from China, Chinese Academy of Science. And today, my topic about my report is microalgae influence on hydromagnesite formation. And my report will follow these 4 parts. In the introduction, I will give some basic information about Bango Lake in Tibet, China, and 2 current understandings about the formation of hydromagnesite. And in the experiment sections, I want to briefly introduce the 2 experiments of this reason, and then in the results, I will present some interesting findings from this study. So let's start this amazing journey. Okay, before this, I think we need to know the approximate location about Bengal Lake. As you can see from the satellite image, Bengal Lake is an inland salt lake in northern Tibet, and the scenery of this also very beautiful. And the table is about alveolar concentration of Bengal Lake. You can see that the salinity of the Bengal Lake water was very high. The highest about 162 grams per liter. And most important is Bengal Lake has reserves of more than 50 million tons of 100 megalite. And way through observation of 100 megalite sedimentary profile of Bengal Lake, we find in the lower layer is mainly gravel and clay, and the upload is mainly about gray-green hydromegalite. And there are also some global salts and other minerals are found upwards, and the top is granular or massive hydromegalite. At the same time, we found a very interesting phenomenon. Microalgae are abundant in the hydromegalite and the soil, including Bengal Lake and some surrounding ditches. Another thing, as we will know, there are two main understanding about formation of 100 megalite. One is lateral evaporation, and the other is biogelic. According to the results of lateral evaporation experiments of hydromegalite under laboratory conditions, the formation of temperature of 100 megalite formation should be at least above 45 degrees Celsius. And actually, the daily maximum temperature in Bengal Lake area is only 7 degrees Celsius. Obviously, it's difficult to form a large amount of 100 megalite by lateral evaporation. And another thing worth noting is that we can see the figure on the right, and you can see the when the temperature rises to a certain extent, the depinate can be converted to hydromegalite. In other words, the water crystallization mechanism carbonate mineral has the lower the relative stability of the mineral. Considering the constants of large number of macrolage in Bengal Lake refer to Paola. Paola's research work on 100 megalite in Artine, Canada. From this comparison, we can find that there are many similarities. There are a large amount of hydromegalite and a large number of macrolage developed around it. So based on the above observation, we give a question or a conjecture. Is the formation of 100 megalite in Bengal Lake, Tibet related to macrology in the lake? To verify whether the conjecture is correct, we conducted 2 experiments. To be honest, the experiment is so simple. The first experiment is about lateral evaporation crystallization experiment without macrolage. we just use Bengal Lake water to evaporate and analysis its solid sample. And the second experiment about 100 megaliths mineralization experiment with microlite. We use artificial light source and regularly replace the distilled water to maintain the evaporating liquid level and give nutrient source to ensure the normal growth of microlite. And about the results, we through the XRD analysis of the lateral evaporation samples, we found that only Lasker highlight appeared and hydromegaliths low formed. But in another experiment, we are surprised to find that the color of a solution is changeable. From these three sets of photos, we can find that from the beginning of the experiment to the end, the color changes from light green to green until off-white. And in addition, we found through conditions observation of solution pH, we found that pH has an upward trend, and it seems to be a certain correlation between the change of pH and the growth of macrolites. In addition, we found the white matters crystallize and grow at the radiculation loss of agar. Then these white minerals were then subjected to XRD analysis. We found that depinates appeared. This means that with participation of macroalgae, Bengal Lake water can indeed form 100 megaliths. This also verifies that our conjecture is correct. The formation of 100 megaliths in Bengal Lake is closely related to the macrolite in the lake. And of course, to be honest, this study is a little simple, but I think it's just the beginning of our study on microbialization of the Salt Lake in Tibet, China. At present, we are still studying on mineralization mechanism of 100 megaliths under the participation of macroalgae and mineralization efficiency of macrolites under different nutrient conditions. In the future, also it could solve the problem of high magnesium and lithium ratio in salt lakes. Okay, this is word of my presentation. Thank you for attention. Yes.
That was a great talk. Thank you very much, Pencheng. As you'll see, the chat is now open, so please do type your questions, Pencheng, in the chat. And yes, while we're waiting for the first question to come in, I'd like to ask you, what's the source of magnesium to the lake system?
Source magnesium.
Yeah. I guess it's what's the surrounding.
Yes. To be honest, the studying about this find that the resource about magnesium, you just need carbon and magnesium. it comes from the surrounding rocks, or magnesium comes from the surrounding rocks, and carbon dioxide comes from the atmosphere. Yes.
Sure. I guess I was asking what the lithology of the surrounding basin was, and whether the magnesium came in with either surface runoff in solution or as groundwater flux to the lake, or whether there were any deep hydrothermal sources of fluids to your lake.
What? Can you say it again?
Yeah, sorry, I did say look at people's questions, but they will type them in. So I'm the exception. I haven't typed in my question, but my question is, what is the lithology of the catchment area supplying water to the lake? And is the surface runoff bringing the magnesium into the lake, or is it coming from groundwater, either continental circulation to the lake, or maybe a hydrothermal source?
Yes, to be honest, I have seen some papers about this. In other people's study, they think the source of Bengal Lake is mainly from surrounding rocks, except the water, because different from other lake, Bengal Lake has no hot spring, so the source of hot spring is not possible. Yes, it's impossible. Right. It's under the rain, and the rain supply of it is just rainwater. Yes.
Okay, thank you. Has anyone got any more questions? Hydromagnesites are obviously a most curious mineral.
Yes, to be honest, it's my first time to contact mineralization, because my undergraduate major is geology, specifically deposits. Yes, but now my study has changed. Yes.
Well, it's a challenging field, working at the interface between mineralogy and biological processes. You identify algae in your system. Are there any other life forms in the lake?
Okay.
So Peng Cheng, I was wondering whether you had other forms of life in Bengal Lake in addition to the algae.
To be honest, I'm now a master student, but I have ambitions to do some research about this, and I think I will continue to do this.
But the algae are the dominant life form that you've identified. Stephen had a question for you, Peng Cheng. Stephen says, thanks for a great talk. He was wondering, what are your plans after your MSc? And do you hope to continue study on Bengal Lake?
To be honest, I just want to continue my PhD program, and I want to go abroad to learn some biogeology skill, because to be honest, I really lack of this knowledge, and I just want to study abroad and then return China to continue their study. Yes.
Good. Well, I mean, there's lots of interesting things that you can follow up there. Do you happen to know what the rate of evaporation from your lake is? Because your lake salinity is quite high, is it not?
Salinity is quite high.
Yeah, just remind us, what is the salinity of the lake water?
Yes.
Approximately.
To be honest, the data of this is just that we tested 2 years ago, but
Yeah.
In recent years, the salinity of Bengal Lake water has been declined. Yes, and
so the lake has got fresher over the last few years. Or it's got more salty.
Yes. It has a tendency to be fresher, but I think there are other reasons about this. There are many reasons. Because I and my teacher just discussed before some days ago about this. And now I do research about this. It's so later, but it doesn't matter because I'm now a master student. I have ambition to do this.
Okay.
Yes.
Well, that's great. We're going to close the chat now. Thanks everybody for your attention, and Peng Cheng for a great talk.
Thank you.
So we're going to move on to our next speaker now. And
okay.
Our next speaker is Dan Belen from Utrecht.
Yep.
Hi, Dan.
Hello. Let me just share my screen.
That would be great. Thank you very much.
Share.
That's perfect.
Wait, is that better?
Yeah, we can see the presenter view at the moment, so that's perfect. Right, thank you very much. Take it away. I'll give you a warning after 10 minutes.
All right. So yeah, okay. All right, so my name is Dan Belen. I'm an assistant.
We can see it in presenter view again. That's it. Perfect.
All right. Sorry for that. So my name is Dan Belen. I'm now an assistant professor in Utrecht University. And this talk is about the work I did during my PhD. It's a bit of an afterthought after the project that I did. So it's not by any means a completed or a matured project, but it's an interesting notion about sea straits and how carbonate production can affect their sedimentology. All right, so we're going to talk about what's basically the Protostrate of Gibraltar. So prior to the existence of the Strait of Gibraltar, there were actually there was a connection between the Atlantic Ocean and the Mediterranean Sea by means of two smaller corridors, which are the Betic corridor in southern Spain and the Riphean corridor in northern Morocco. So this talk is about sediments that were deposited in the Riphean corridor. Now, when these two predecessors to the Strait of Gibraltar closed, they actually caused the near complete evaporation of the entire Mediterranean Sea. And that's a very, very important geological event, arguably the most spectacular geological environmental event in the past 10 million years. And there's been a very lively debate as to what precisely caused the closure of these sea straits during this time. So the closure of this basin occurred at the end of the Miocene, in the Mycenaean time interval, and the sediments that I'll talk about are deposited right before that moment happened, right before the closure of the corridor. Now, the desiccation of the Mediterranean Sea left behind an enormous amount of evaporites. So in this view, this is in southern Spain. You can see all these rocks that you see are all evaporites that were left behind after this sea was removed. So all of this mineralogically is gypsum and hydrite and some halite. Now, the big debate for the past several decades has been whether this closure of these corridors, these bathic and reefing corridors, occurred because of eustatic sea level changes or because of tectonic effects. But my hypothesis that I will put forth here is that there may be a third option, which is that simply the deposition and the formation of carbonate material inside these sea straits to some extent caused their closure. So I call this this theory the arteriosclerosis of the sea, because basically that's what it is, right? You have these two sea straits and all this material that is produced there, this carbonate material, kind of clogs them up, and the clogging basically stops the ability of the water to move between the Atlantic and the Mediterranean. And because of the evaporative dominance in the Mediterranean, you actually get this desiccation. So the field area is located here. In the top you see a paleogeographic reconstruction, and the sediments that we're looking at were deposited immediately before the closure of this strait. Now these sediments, they're very, very high carbonate content, up to 80 or 90%. And they show evidence of shallow marine deposition and very high sedimentation rates. So what's very characteristic are these stacks of probably tidally forced dunes of carbonaceous material. And the interesting thing is that this material is very, very immature. So it consists of these very fragile shell fragments, barnacle fragments, foraminifera, that I interpret to be formed right there in that area. Because if it would have been moved much further in such a high energy, high depositional setting, then it wouldn't have been that preserved. Those fragments would be much more would be in much poorer condition. Now, most of the sediment fill in the reefing corridor is not this really immature sandy material. It's actually this thing that they call the blue marl formation. So it's this very fine-grained, also very carbonate-rich material that is essentially the same stuff, but just completely destroyed due to all sorts of processes. So this is kind of the more distal, more immature sink part of this carbonate source system. Now, if you look at the sedimentary fill of this reefing corridor, it almost entirely consists of this material. So it's almost entirely carbonate material that formed at the fringes of this reefing corridor in these areas such as the Benelux outcrops that I showed earlier. And then it makes their way inside the depicenters. And if you look at some of the cross sections, which are developed from seismic and drill core and outcrop work, then you see that a lot of this sedimentary fill, for example, in this Tafrant Basin and the Taunat Basin, is entirely from the Upper Tortonian. So the Upper Tortonian is this section of the Miocene that preceded the closure of this corridor. So during this relatively short amount of time, right before the closure, all of this basin was just filled with this blue marl carbonate material, right? This is another section. It's from Capella et al. These are some cross sections that are across the reefing corridor, and again you can see that some of these basins that existed during that time are completely filled during this Upper Tortonian interval. Some of them, they contain material from after the closure of the strait. So after the strait was closed, there were still some lakes that were not connected to the ocean. But basically the main strait that would facilitate this movement of water from the Atlantic to the Mediterranean was basically clogged up with all this carbonate material, right? Now, if you do an analysis of how much salt was deposited during this Messinian salinity crisis, then you'll see that an estimated 9 times the amount of salt that exists inside the Mediterranean Sea has actually been deposited. So what that shows is that we're not talking about a single desiccation event, but rather a series of partial desiccation events before one much longer and more widespread major desiccation, right? And in this outcrop here, which is in Sorbos in southern Spain, again, all of this outcrop is evaporite material. And you can see some of the horizons that are inside this. Those are actually the boundaries between 2 independent desiccation events, right? So the important thing to note here with this Messinian salinity crisis is that we're not really necessarily talking about a single event. It's a series of partial desiccations, partial closures of this strait, and then eventually a final, more long-term desiccation across the entire basin. Right, so multiple desiccation events are apparent from the rock record. All right, so we have these two effects, these 2 processes that are known to have played a very important role, which is basically changes in eustatic sea level during the Miocene. And according to our measurements of outcrop thickness and biostratigraphy, we calculate that this accounts for about 800 millimeters per 1,000 years. Now, one thing you have to note about this is that this is a lot of lowering of the relative sea level. But of course, we're talking about cycles. So these are basically glacial cycles during the Miocene, and they would alternate between low stands and high stands. So sea level would have played a very, very important role in this periodic desiccation phase right before the main desiccation event, but maybe it was not the definitive trigger for the final widespread desiccation.
Dan, you've got 2 more minutes.
Oh, okay. Now, the second factor we consider is tectonic, which is slightly less than sea level. And then finally, based on outcrop and seismic evidence, we show that sedimentation is also quite significant. It's not quite as large in scale as sea level and tectonics, but it probably did play some sort of significant role, right? Now, one thing that needs to be mentioned, though, is that there's a lot of oversimplifications, of course, in this very short talk, because we're talking about spatial and temporal changes in all these 3 different factors. And also, it has been known for some time that the break off of this subducting slab in this area probably caused a major isostatic uplift that was the ultimate trigger for the final desiccation event, right? So in terms of these immediate short-term closures, sea level was very important, and then slow tectonic motion. But for the sustained closure, we have this combined effect of this isostatic slab breakoff. And in addition, our sedimentation effect, right? So basically this arteriosclerosis, this clogging of the sea strait. Right, so to sum up, the sedimentation was mostly caused by autogenic production of carbonate sediments. It's possible that autogenic carbonate production and sedimentation played a significant role in the closure of the reefing corridor. And although sedimentation was not decisive in terms of the immediate closure, it should be considered in models. This sedimentation, this clogging should be considered when you talk about it, the longer term sustained closure of the sea strait. So that's it. Exactly in time.
Exactly on time. Thank you very much, Dan, for a very clear and beautifully illustrated talk there. So the chat is now open. If you'd like to post your questions in the chat for Dan, that would be grand. Can I ask you, you used a wonderful term, what about the sediment being destroyed to make the blue marl? What are those processes of destruction you're talking about? Are they physical processes, chemical processes?
It's basically turbidity currents. So in the shallow marine, like these fringes of the corridor, you have these sustained processes like tides, waves, things like that. But then deeper towards the depot center of the corridor, the material was brought in through turbidity currents. And also contour currents, so geostrophic continuous currents also probably played a role. So basically it comes down a hill and it gets pummeled and destroyed on its way down. And then when it's at the bottom, there's additional reworking over long periods of time that cause these shells, these fragments to basically become destroyed to like tiny marl fragments.
Sure, that makes complete sense.
At least that's my interpretation.
So
maybe maybe there's some chemical effects too, or maybe even biological effects, right? There might be some creatures that are, digging through it and destroying the material.
Okay. We now have a question from Stefan Enmatter. He had an interesting talk, Dan. Do you have any equivalent restricted carbonate facies in Morocco that are equivalent to the calcaire de Basse in Italy and elsewhere?
Restricted carbonate facies. So is this the Messinian kind of lacustrine material after the closure of the corridor? I think that's what is meant. I'm not entirely sure, but the answer is yeah. The answer is
that may be
yes.
what he means. Yes, yes, says Stefan.
The answer is yes. So in our paper in 2020 in Journal of Sedimentary Research, we find an outcrop, new outcrop, that has that's probably lacustrine or lagoonal interbedded with fluvial. So this is something that is semi-restricted. It no longer has this full connection between the Mediterranean and the Atlantic, but it may be still connected to the Atlantic Ocean. So it's not completely certain, because it's still possible that these outcrops are prior to this full-scale closure, but maybe those represent lagoonal, semi-stagnant marine lakes, right? And I have seen some outcrops in Italy. I'm not sure if that's what meant with calcari di Basse, but that are very, very similar. So maybe it's roughly the same.
Great.
So check my paper, Tide dominated deltas responding to sea level fluctuations, Journal of Sedimentary Research. It has the outcrops in there.
That's great. Thanks very much. Alessandro Inace from Naples has got a comment, and it relates to the paleotopography and the complexities of paleotopography during the Messinian, and specifically the presence or absence of the Tyrrhenian Sea.
Yeah, that's a good point. I chose this because I wanted to introduce the Messinian salinity crisis, right? Of course, it's a very old, outdated picture, but it looks very cool. So that's basically why I chose it. And it kind of speaks to the imagination, right? The whole Mediterranean is evaporated. But yeah, it's correct that this is not the most accurate recent interpretation. That's true.
A question while we're waiting any more. Carbonates are cool, of course they are, yes. So my question would be, thinking about physical erosion that might happen as your arteries got clogged up, then the flow velocities, presumably if the drive for flow maintained, your flow velocity as the channel cross sections decrease would accelerate. And even if the associated erosion that you imagine would occur, even if that couldn't keep pace with the sediment supply, you'd expect some record of the sediments that were eroded and redeposited within the Mediterranean basin to be preserved somewhere. Does that make sense?
Yeah, I think I know what you mean, but I guess you would find them in the Atlantic Ocean because the flow goes from Mediterranean to
the flow is going the other way.
Yeah, but that's a very good point. And there has been some work on that. So there has been some work on reconstructing this this paleo flow in this area.
Yeah,
but it's quite difficult. Like as I tried to show with some of these paleogeographic reconstructions, is that the area is very, very complex. Like there were islands, there were, the coastline was very complex. So it's very difficult to reconstruct exactly what you're looking at, what's going on at which place. So, but yeah, maybe there's some deposits from exactly that time in the Atlantic Ocean. That's possible.
Yeah, you think it might be quite a short time, but the volume of deposits might be substantial.
Yeah, yeah, it's worth looking for, I suppose. It's a good point.
Do we have any more questions for Dan? We've got about a minute left. If anyone wants to sneak in a last question. And if not, I'd like to thank you again, Dan, for a beautifully illustrated, very clear talk.
All right, thank you.
We will have, just to put a marker down, we'll have some discussion time as we did during the morning coffee break. We'll keep the chat open, throw the doors open. Anyone can unmute their mics after the session, which should finish at 12:10. But we're now pretty well on time. So I'd like to invite our next speaker to share their screen, please. So our next speaker is Khalil Azanud from the University of Ahmed Ben.
Hi,
Khalil,
everyone.
are you with us?
Hi, yes, I am here.
Perfect. That's great. We can see you. Perhaps you'd like to share your screen now, please, Khalil.
Okay, I will do it now.
And Khalil, I'm talking on a topic very close to my heart. I spend a lot of time with undergraduate students looking at tufa. He's going to have a look at suborbital controls on tufa occurrence and their character over the last 5,000 years using a case study from Northwest Africa. So take it away, Khalil. We will give you a warning after 10 minutes, and then you will have a further 2 minutes after that to wrap up.
Okay,
thank you.
I copy that. So thank you very much. It's a pleasure to be here and to communicate within this community and to be part of the Carbonate Forum. So here I will talk about tufa deposits as a continental carbonate, and I will further discuss whether climate is involved in controlling their occurrence, their character, and their extension within the suborbital timescales, on millennial and multicentennial timescales. Of course, this will be carried out in a K climate region. So this K climate region is the northwest of Africa. So northwest of Africa is influenced by the westerlies winds belt, by the North Atlantic Oscillation during winter time, which of course modulate the hydrological budget during winter time. And of course, during summer and springs, we have the precipitation, the rare precipitation and infrequent precipitation during the summertime is modulated and controlled by the degree of the cyclogenesis process within the Mediterranean basin. And of course, without missing the role that play the Saharan air dry masses in terms of controlling the Aeolian sedimentation in the site. So the local site here is called Imuzarkanda, which is a small town located in the Middle Atlas. And the bedrock here shown is constituted mainly by the limestones and dolomite, which were deposited during the Lias, the lower Jurassic epoch. And here it is presented. the local studied site, you can recognize here, you can find the emplacement of the logs here. So please remember the position of the logs, especially log 1 here, which is very important here to note after the topographic gradient is the presence of a failure or slope failure. This is very important when we consider tufa deposition. It is this point is known as neck point in the vocabulary of the geomorphology, and it has important meaning when we consider tufa deposition in terms of the weight growth and other things. So the result of the sedimentological and stratigraphic analysis is portrayed here in this illustration. We can find deposits that characterize the barrage cascade deposits. So here we can find deposits that characterize the barrage cascade deposits, such as the phytohem of hanging stems, such as the limestone or boundstones of bryophytes, such as stromatolite and other things. So this characterizes a barrage cascade deposit. Behind this barrage cascade deposit, we can find here deposits that characterize a dammed area. So we have either establishment of lacustrine sitting here, so we can find bioclastic lime and bioclastic sands, and we can find also the establishment of palastrine sitting within this dammed area. So this is very important. And another thing that is very important is within the occurrence, within the background occurrence and the precipitation of the calcite and the aragonite, maybe it was some period, it were some periods with interruption of this background biocalcification by occurrence, by deposition and preservation of some of the organic rich facies. We can find here the fen deposits, those PT facies, and here we can find at 2.7 kilo annum before present the establishment and formation of the sapropel deposits, which characterize lacustrine sitting. And at the upper part here, it is very important to notice that the occurrence of this organic rich facies is very, very occurred with high frequency. Here we can find the alternation between oncolite and the marshy facies. This is attributed and interpreted to marshy facies. So we have here vein deposits, we have here sapropel deposits, and we have here marshy deposits. And this characterize period with interruption of biocalcification. So this is from the sedimentological point of view. From the sequence stratigraphic point of view, we have here establishment of two sequences here. So depositional sequences, where the lower depositional sequences and the upper depositional sequences separated by or delineated by a subaerial unconformity, which of course mark a negative accommodation. And here it marks also a change in the sedimentation pattern from fluvial dominated sitting here at in the lower depositional sequence towards lacustrine dominated sitting, because of course this is controlled by the stacking pattern in the barrage cascade deposit. So this is very important also to notice. And we have to mention that from the literature from Arenas et al. 2014, paper published in Sedimentology. So this, in terms of geomorphic sitting, this geomorphic sitting resembles the single non-vertical step wedge shape geomorphic sitting described by Arenas. So after this study, we have a relationship between the stacking pattern at the barrage cascade and the extension of the dammed area here. So when we have a higher aggradation to progradation ratio within the barrage cascade, we have immediately extended dammed area, and vice versa. Okay, so this aggradation to progradation ratio is a very important parameter that describes the architecture, and of course it has some meaning in terms of the extension of the dammed area and the facies that characterize this dammed area. And this ratio is modulated, is controlled by the discharge, by some of the hydrodynamic parameters such as the discharge and the water velocity. When we have higher discharge, we have a progradation pattern. So we have a low aggradation to progradation ratio. And when we have lower discharge, we have higher aggradation to progradation ratio. So this is very important in terms of the sequence stratigraphy and the creation of the accommodation and the characteristics of the sequences that were developed or would be developed here in this Diamond area. So some of the proxies, some of the paleohydrological and paleoecological proxies shown here in this illustration. So when we consider these organic rich facies are developed at Uranium 4.7 and 2.7, 4.6 and 2.7 kilo annum before present, and those developed at the upper part. So using some proxies of using some species of the genera Aliocypris, which are these are structures. So Aliocypris brady and Aliocypris inermis are used here as proxies for cold water. Okay, and here the macrocalcul we have used the shape of this macrocalcul to have insights from the hydrological pattern. So this organic rich facies, the 4.6 and the 2.7, are cold events. Okay, they show the after this these two species, this indicate that these periods were cold period. Okay, and from the macrocalcul shape we have here so the macrocalcul show no feature, no reworking feature, which indicate that this is a primary signal, and this calcul or macrocalcul was not undergone or have not undergone a longer taphonomic process. So taphonomic process is not considered here. As for the 2.7 organic rich facies here, the macrocalcul shows some slight reworking features which indicate that this macrocalcul have undergone some longer or more or less longer taphonomic process, which indicate that this period is subhumid or humid period. Okay, this period is I would see a right period, and this period is subhumid. So the organic rich facies that were developed at the upper part here show high reworking features. So we can recognize the spherical shape here. So this indicates that this macrocalcul have undergone longer taphonomic process, which indicate that the drainage pattern was very, very important, was very active, and this indicates maybe a humid conditions. So now in order to test whether climate is involved in controlling the occurrence of this organic rich facies, that is the interruption of the biocalcification, the background of the biocalcification, and in order, of course, to test whether climate is controlled or is involved in controlling the shape of the deposit, the architecture of the barrage cascade and other things, we have referred to a curve-based comparative approach using some of the regional and global paleoclimatic data. So this subaerial unconformity that delineate the two sequences here we have, as we have mentioned before, this subaerial, this limit mark a shift, a net shift from
2 minutes. Khalil, can you then wrap up?
Okay,
thank you.
So this subaerial unconformity marks a transition from fluvial dominated to Lacustrine dominated, and so we have here a clear change in the sedimentation pattern. This is when it is compared to regional climatic data. This may consider with a reorganization, with a synoptic reorganization in the North Atlantic Oscillation. Okay, we have here establishment of, or we have here at circa 4 kilo annum before present, we have here establishment or a southward shift of the Azores front and the establishment of a pervasive NAO or negative NAO-like pattern. Okay, this may be coincident or may control this sedimentation change. And here, the high aggradation to progradation ratio at this point, at this interval, at this time interval, which have favored establishment of Lacustrine setting, the high aggradation to progradation is compared to the pollen-based reconstruction precipitation is here is coincide with lower precipitation or winter precipitation, higher summer precipitation, and of course after the insolation we have here hot summers and we have here mild summers. Okay, so this may control the aggradation to progradation ratio, and the upper part here, which the low aggradation to progradation ratio that would have favored establishment of fluvio-palastrine deposits, coincides here with lower summer precipitation and higher winter precipitation. So the winter higher discharge, higher winter precipitation would have favored progradation pattern and lower accommodation rate. So this is important also. In terms of multi-centennial timescale, so the occurrence of these organic rich facies 4.6 and 2.7 coincide with cold events, known as bond events, which are from the northern, from the higher latitudinal of the northern hemisphere. These cold events or these organic rich facies coincide with those cold events. So the multi-centennial variability of climate control even or influence the bioprecipitation and give rise to the formation and the preservation of organic rich facies. So for those which were developed at the upper part, it might be related to solar minima here from this study, okay, between or during the medieval climate anomaly and the Little Ice Age. So to conclude, so we have highlighted here that climate can influence the deposition of tufa, the occurrence and the character of the facies character of tufa within the suborbital time scale. So in on the millennial time scale and on the multi-centennial time scale. So for more detail, please refer to this paper. And thank you very much for your attention.
That's great. Thank you very much, Khalil.
Thank you.
I'd like to remind everybody to start typing your tufa-related questions in the chat. That was a beautiful, detailed study. Could I just ask you to take us back to your map view to just remind us where your cross-section is, because it's one of the nice things about chairing these sessions is that I get to ask some questions while we're waiting for other people to type them in.
Okay. Go ahead.
And I have worked a lot on ancient tufa systems, or I tend to work on the water chemistry and the flow. And one of the challenges I imagine in interpreting a record like this is trying to disentangle the climate record. And it's clear in your case, you know, there's this really nice correspondence with the change in the North Atlantic Oscillation and the Azores front. But to disentangle that from the natural variability in discharge, because in modern systems, I've seen in relatively short timescales, the discharge can switch from one part of the tufa mound to another part of the tufa mound really quickly, a bit like an alluvial fan. Rivers on alluvial fan can shift. You know, anything that's aggradational like this is very sensitive. So I wondered if you wanted to just talk about those difficulties, or whether you're confident that this cross-section you've looked at represents the long-term continued pathway for all of the tufa precipitating waters.
This is a good point. Okay, so here, of course, there is a lot of shift when we consider tufa as a fluvial deposit. So we have a shift, the lateral shift of fluvial of the water course. But here we have in this, when we consider the geomorphological setting, we have here the neckline or the neck point is continuous here. So the barrage cascade, the buildups here are continuous. Okay.
Right.
So here we have the preservation of because we have at the damed area, we have the creation of the space. So we have more preservation of the sediment, and we have more, of course, more continuity of when we want to decipher the climate signals. And this is because, of course, because we have here the establishment here of the barrage cascade. We have enlarged barrage cascade deposits. Okay, we have enlarged barrage cascade deposits, and we have extended damed area. So the preservation pattern is, I think, is more enhanced here.
Yeah. So even if your discharge points move around a bit, because you've got that extended barrage, that's created that effectively lacustrine setting behind. So that helps remove that. So do we have any questions in the chat? Otherwise, you'll keep getting Whittaker questions, which is not really fair on everybody else. Is there still discharge at the springs? Is tufa depositing now?
Now, yes, but not in this area. It is because, you know, this is a town. This is a
Yes.
small town, so this is the anthropogenic factor, which shifts all of the deposits. And
I was interested looking at that photograph to see quite how urban your setting is. That must be a bit of a challenge, but also perhaps an opportunity if there's construction work.
of course.
So your last slide was quite complicated. Well, not the last slide, slide number 5, when you were talking about the different drivers. So you were talking about the seasonal differences. If you were just to summarize the major control in terms of the seasonality of climate, because we kind of ran out of time for your conclusion slide. So your takeaway message about seasonality for other areas in semi-arid climates.
So here, what I think, the main control on the aggradation pattern within the barrage cascade is during summer. So when we have hot summers and we have humid summers, so then the aggradation pattern will be more favored in these conditions.
Yeah.
During winter time, when we have higher discharge during winter time, so the aggradation or the aggradation to progradation ratio of the barrage cascade will be lower. So we would have active overflowing through the barrage, through the neck point, through the seal height, and then we would have a progradation ratio rather than aggradation. Okay, this is shown here in the photographs. So when we would have a higher overflowing, so at the downstream facing of the barrage. So we have here the barrage cascade, and we have here the downstream facing of the barrage. So evidence from that, show that I would say it have been an active overflowing is the formation, the development here of this known as buttresses, the development of buttresses at the downstream facing of the main barrage. This evidence that it were at some time, at some period, active overflowing. So we would have had a rather progradation pattern.
Okay, thank you.
Thank you.
Just sorry, I'm going to interrupt you because we have a quick squeeze in the last minute question from Stephen, who said, "Hi, great presentation. What do you think the application of this could be to more temperate regions?"
To more temperate region, I think more temperate region, that is, I would say it will be a change, or it will be a difference between the shape of the shape of the build-up, the barrage cascade build-up, because in the temperate region we have rather more humid period, and we have less hot summers. So this will shift or will favor a rather low aggradation to progradation ratio. This will favor I would say more extended shape, which shape of the barrage cascade of the main barrage cascade. This will favor a progradation because we have a lot of humidity. This will then.
That's great. Okay, well, I'm going to stop the discussions at this point. We can come back to this as to all the other talks at lunchtime. So we can chew over sandwiches and science at the same time. So thank you again, Kalia, for a great talk. And I'd like to invite the last speaker in this session, who was the chair in the first session and is hopefully still awake and with us, and that's JP Gomez, who's joining us from Rio. Hi, JP. And JP's going to talk to us today about cyclicity in the upper part of the Barravea Formation in the pre-salt of the South Atlantic. So thank you, JP. Go for it.
Thank you, Fiona. So I will show you a small part of the work that I have been done, but I think it's an important part to share and to open for discussion. So I would like to start in showing this interval of, let me add only the laser, yes. Here it's a small interval of one of the pre-salt core in the centimetric scale, where you can see these small spheres that they are made of calcite and they have the radial extinction. Here I will call only as spherulites. And this fascicular calcite that I will call here as shrub. So if you take a look in detail on the alternation of spherulite to shrub, you can see that we have some shrubs in the basin, then they go to spherulite that looks like it's changing the size. Then laterally, as here, you can see that some shrubs started to grow. And then you have some layer of shrubs that goes to spherulite and then to more shrubs. So take a look into this image. I would say qualitatively that the pre-salted data has a high frequency cyclicity in centimeter scale. But someone can tell me, though, okay, there is some important surface. Yes, we could draw some surface. And maybe we could try to break this interval in some really small cycles. And then if you take a look in the thin section to the millimetric scale, we still see some cyclicity, where here we have shrubs that goes laterally to spherulite, and inside the spherulite, the size is also changed. So the cycles in the pre-salt has multi-scale resolution from millimeter to centimeters. But what I will focus here in this talking is for the metric scale cyclicity. So to try to incorporate the cycles or the variation in the centimeters and in the millimetric scale, I'm using the facies classification that consider as this triangle with the three end members, that is shrub, spherulite, and mud, and the abundance of those components will give the facies name. And the idea to use this new classification is try to highlight the variation on spherulites and shrub to metric scale, and also consider that spherulite forms in a different condition than shrubs. So here is 1 meters of core when I applied this classification. And as you can see, we can start with more shrub in the basin, then gradually you increase the abundance of spherulite. And in this piece, we have a thin section where you can check that it's all spherulite. But here it's a spherulstone that is a predominance of spherulite. And then if you go upwards, you see that you start increasing the abundance of shrubs. And in some case, you have a small decrease in the abundance. Are these variations important, and should we consider that small variation of spherulite in our interpretation of cyclicity? And in this point, we have a thin section where we can see that, yes, we do have fascicular shrubs here, but also we have some spherulites. And if we follow on with this interpretation, we can say that the data is made of some metric cycles, but are they quantitatively? So here I will show a study case with one core where I apply a quantitative method to calculate it and see if this variation is really ordered. So I had proposed two main trends of the upward increasing spherulite, starting from shrubs going to spherulites, or upward increasing shrub pattern, or maybe one symmetrical cycle, start from spherulite going to shrub and going back to spherulite. And also a lot of articles that I put a small synthesis here had already proposed before me some cycle that also include the grainstone in the cyclicity. And we'll analyze the both configuration when we add the grainstone that is a reworked, because here the grainstone is made of the reworked of in situ facies, and also the trend of from spherulite to shrubs. So the main objectives of this talking is try to answer this question. Do pre-salt shallow lacustrine carbonate of Upper Barravelha formation show systematic variation in facies order and thickness within metric cycles? If so, then what does this tell us about process forming spherulites and shrubs? So the data that I will use to answer that question comes from the Santos Basin, is in the south of the South Atlantic, specifically in the Santos Outer High. And the data that I will use for this talking is well 3 that is on the top of the structure. I took a look in all of these wells, but I will not have time in this 10 minutes to show. So I will only show almost 200 meters core and almost 600 thin sections. And the data come from the Upper Barravelha, that is the Upper Aptian in age, and they are separated from the two unconformity, the intra-Alagoas in the base and the south on the top. So I will show the method. The method that I choose is the one that was proposed by Peter Burgess in 2 nice articles from 2016. All the details are there, but to make this talking understandable, I will do a small summary. So in this article, Peter proposed that based on the synthetic data, that if you have one asymmetric cycle made of 5 facies from 1 to 5, from black to yellow, and if they are well organized, and if you do a Markov calculation, or if you know what is the first facies, for example, the black one, and count what is the next one upward, we will have that 100% of the time, we will have the gray facies. And in this matrix, it's from all facies and all calculation. So for a synthetic and perfect order data, the main diagonal is made of 1s. He also proposed a matrix that he calls Markov order for the facies order and the run order for the facies thickness. And the idea here is to swap the facies order to reproduce the 15 meters and the same numbers of units, and calculated what is the M values, and do that for thousands of times. In this case, I think it's 5,000 times. So the blue histogram is the random distribution of facies and facies order, and the red line is the observed data. And he also proposed the null hypothesis of order, where for this case, the p-value is 0. What means if the p-value is 0, no order is unlikely to be true. So there is a order in the data and also on the thickness. He also brought more examples to make it clear how to use these tools. So if you have a partially ordered data, your matrix, they decrease the 1 in the main diagonal, but we still with high numbers, where the green is high probability, red is the low probability, and the intermediate probability is made of yellows and orange. And the M values goes close to the random data, but the p-value, they still 0, means that even with partially ordered data, we do have some order controls. If you have a disordered data, as in this case, your matrix is start to distribute the main probabilities, and your M values goes within the random distribution, and your p-value has a high value, what means the order of facies and thickness are random. He also brought another example for a symmetric cycle. If you start with black, goes to yellow, and then goes back to black, your matrix is made instead of 1, as in the previous example, made of 0.5, but your p-value is still with 0, with high confidence of the null hypothesis. And
JP,
also,
you've got 2 minutes.
Okay, I'm almost there. Okay, so let's apply these methods that I gave some examples to the pre-salt data. So I have 200 meters of core, and that is my facies distribution, like using the grainstone and the mudstone. And this is my matrix of probability. As you can see and compare with the synthetic data from the metals, the main diagonal are with the green values with high probability. The M value is far away from the random data. And the most important, the P value is almost to 0. What this shows us is that there is an order in the facies pre-salt vertical distribution. However, for the facies thickness, the R has a p-value higher and the R is within the random data, what means that we don't have order in the thickness. Okay, so someone can ask me, oh, that your greenstone is made of the rework material and carbonate are precipitated. So maybe we should consider only the spherulites and shrub that was made in situ. So I did the similar calculation, excluding all grainstones and mudstones, and only take a look from spherulites to shrub. And the calculation and the conclusion is pretty much the same. And the M metric is a little bit higher, but not from 1. What tells us that our data has a asymmetric cycle, partially ordered, or a symmetric cycle. So if we recombine the facies distribution and try to see mathematically what is the best cycles for the two options, for the in situ and the in situ plus mud plus grainstone, the proposal cycles in other works and in this work, they are reproduced. So the takeaways point, to not take longer, is the method of transition matrix clearly show that strong support for the existence of cycles based on the vertical facies stacking, including or not grainstone as a component from the main cycle. Facies thickness within packets are perhaps unsurprisingly not cyclic because we are talking about a shallow lake. So maybe the thickness of the facies is conditioned to the accommodation space. And also the spherulites, although forming within a substrate, has a close connection to lake level variation or lake level chemistry. So even for those that interpret the spherulite as a diagenetic product, they have a connection from pore water and the lake water. And the last takeaway point is that the transition from a shrubstone to spherulite thus occurs, while the opposite is not observed, or in other words, from spherulite to shrubs, most of the time they are transitioning, that increasing slowly. And the next step that I couldn't show here is the same calculation for other wells or other feeder in different structural configuration using other methods as Fourier or wavelet analysis. We acknowledge Petronas for support, and we thank Peter for all the discussion and support. Sorry, Fiona. I think
that's all right. I turned my video on and looked threatening. That's my version looking threatening.
Yeah,
JP,
you scared me.
I'm so very scary person. Thank you for your talk. And I'd like to invite questions in the chat, please. So we have one from Alessandro Mangione from Manchester. Great talk, thanks. I was wondering if you've explored the sensitivity of the facies distribution on the matrix results. Many thanks.
Yes, that is it's an important question. If I use a different facies classification and only add the end members, or in other words, if you increase just a little bit of spherulites, you could classify everything as shrub. So your facies will have only two facies, spherulites and shrub. So the transition matrix would change. Yes, and it's not in this talk, so but I will tell you because I did for other wells. In some wells that is deeper in the structure, that maybe we have more accommodation, you have more symmetrical cycle, maybe because you have more accommodation space to organize, and also we lack of the misbits.
That's great, thank you. And Alessandro also said, okay, great, thank you. Do we have any more questions? As a co-author, I don't feel that I can really do my normal, ask lots of questions. So. Good, says JP. So Pete's got back to us. Right, great application of this method, Zhao. Obviously, I'm just a tad biased, but well done. It's really nice to see a cyclicity analysis based on robust quantitative evidence. The obvious follow-on question is, why are the strata, one, as classified, at least cyclical, and what is the mechanism?
Fiona, or could you repeat the beginning of the question?
Why are the strata, at least as we've classified them, cyclical? So what's the underlying mechanism of the cyclicity?
Okay, yeah, now I got, yes. There is many like possibilities. I would say the one that I believe, and with my data, that is made of the climatic changes, where the amount of the fresh water, they could changing the pH and the alkalinity and favor the magnesium clay and also the carbonate. And if you take a look only on the time of the carbonate, the spherulite grows within the structure. So they have cations coming from all sides, and they grow in this substrate. And in the opposition, the shrubs grows on the lake basin. So maybe they have more flow and more energy to the crystals to organize in one direction and to produce the fascicular facies. I think I answered you.
Can I jump in and suggest you might say something about the frequency of the cycles to back up the idea of the climate?
Oh yeah. So I have done some Fourier and also wavelet analysis and trying to add in all the high frequency and then to upscale into the low frequency. And we can have like from 1 to 2 meters and then almost 6 meters and then 20 meters. So we could have many scales cyclicity that it's hard to prove that it's related to the orbital cycles, but we did some exercise in trying to match the orbital cycle in Cretaceous according to Lasker and come up with some matchings with this data. So we don't have any proof that is really like related. It's one exercise, but we do have like multiple frequency in the data. That I'm sorry, I didn't have time to show all of this.
That links, we've had a couple of questions. I'm going to take them in reverse order. So Ramon Mercedi Martin has then followed up and with a question that links directly with that response, saying, great talk, Zhao. I was wondering if you consider cyclicity influenced by extrinsic or intrinsic factors as being more important. What about Milankovitch influences? So I guess about the temporal frequency that you were starting to talk about.
Yes. I think that it's important the external cycles, especially for the metric scale and bigger scale. But for the high frequency, maybe we could not follow for all the wells, so that could be auto-cyclical. And also the influence of the chemistry, as in the Mercedes Martin's articles with different source of water, could also be important to influence the evolution of the water chemistry and also the calcite morphology.
Okay, thank you. Kathy's got a question, but that sort of might help us transition into the discussion session, because we're aware that we've kind of, strictly speaking, reached the end of the morning session. But before we move into a rather more free-form discussion, so please, everybody that's spoken in the last session, the last 5 speakers, please stay online, because you all gave great talks and we'd love to discuss them a bit further. Reminder for presenters of the next session: they will need to be back in and join the green room, please, at 1:20, ready for the start of the afternoon session. We'll have some sort of structured discussion for the first 30 minutes of the lunch break. and then we'll leave things open for anyone who just wants to hang out. And I think Kathy has very kindly offered to chair the next sort of the discussion of the talks that we've had this morning. So I'm going to pass over to her.
Yep. So thanks very much, everyone. Thank you again to all the speakers this morning. Sorry I couldn't hear all of them, but I'm back. And as Fiona said, for the next 20, 30 minutes, however long people need, is a chance to ask any questions that you didn't have last time. You can unmute yourselves, turn on your videos, and we can have an open discussion. You don't necessarily have to post things in the chat. And so to get things started, not to let you off the hook, JP.
Sorry, I've just realised what I should have said is we're back with the afternoon session at 1:45. Yes. So apologies for not actually mentioning that rather critical fact. So I'll shut up.
No, that's fine. That was a good point. Yeah. So for those people who are going now to get some lunch, 1:45, where we're going to have an update of a Carbonate Forum field trip, and then we run into 2 sessions of talks this afternoon. So for those of you who are staying, we can carry on now talking openly, and I will ask the question that I put in the chat just to get things going, JP, if that's all right. So you were talking a bit about the changes in cyclicity and stacking patterns that you got in different parts of the lake, depending on water depth. I wonder if you could just say a bit more about that, and whether there was anything systematic you could then use to try and correlate between wells, whether there was a lower order cyclicity that allowed you to correlate between wells, or whether actually tying this all together is actually quite complicated.
Yes, you are right. Yes, I try to use for these studies only the chord interval, and I do have logs and image logs, and so if I use logs, it's easier to correlate it. But for facies and facies thickness stacking, I took the attention to only use facies. So in the low frequency, they repeat a similar thickness, and if you go a little bit deeper, this thickness is a little bit higher. It's not a huge difference, but it, for example, from 1.3 to 1.5 meters, or from 7.8 to 9. So it looks like that we can correlate it with some uncertainty, but we can correlate like laterally. That is the work that I already did, but I didn't have a chance to show. And I'm trying to expanding now that I'm back to the work to other fields that we do have, for example, 200 meters core as well in the same interval, and try to match a similar pattern there as well.
Yeah, excellent, thank you. Because it's always very difficult to do this, particularly when you have such sparse data points.
Yeah.
Do the image logs? Sorry,
and that is important because it's an oil field. So we cored in the producer well, but the injector well, we have a smaller core. So to have access to the low frequency thickness, it's harder if you only use core. So the other work that I have done is try to matching with other logs and try to pass the information from core, from facies to logs. Sorry, only to finish.
Right. No, I mean, I was just wondering with the borehole image logs, how much resolution you had. Can you really pick out these textures on image logs clearly?
Yes. If the quality of the log is good, yes, you can do, but the quality is variable. And sometimes you can have good resolution, but sometimes it's really a mess.
Yeah. Excellent. Thank you. Are there any more questions for JP or for anybody else in the session?
Hello.
Hi.
Hi, Alessandro. I cannot share my video. Don't know why.
Don't worry.
Anyway, the question is regarding the Fourier methodology you want to use. You just say that you want to use Fourier, but I was wondering what is the purpose of using this approach on this things. I mean, I'm not really very familiar with the topic, but you know, I would like to know a little bit more about this Fourier thing,
Yeah.
please.
Okay, yeah. The idea is we do have the facies thickness for each facies, that the total thickness is 200 meters. The idea is to enter with this sequence and try to see what is the dominant frequency by Fourier. So you got back to the Fourier domain and see what is the spectral distribution. And if you can select more than one scale. And for the wavelet analysis, I will assume that the depth is similar to time. So I will do a similar analysis, but assuming that my thickness are time, only to see if I can find a dominant frequency. So the idea is to calculate from different methods and see if they agree or if we have some incongruence on the cycle calculation.
Okay, yeah, makes sense. Thanks.
Thank you, Alessandro. Do we have any more questions?
Oops. Okay.
Hey.
I've just got a question, and I like the way like you did the analysis separately, like one set for the in situ facies and the other set for the in situ facies plus greenstone and mudstone, and the result seems like quite consistent. And so my question is, how do you consider the influence of like erosion? And because when you have erosion, they can cause facies amalgamation, and those kind of erosional horizons are quite difficult to detect. Yeah, and so how do you think erosions and gonna affect your results? And because I ask this because I see your result, the R value. So your result tells you that there is cyclicity in terms of facies order, but there's no cyclicity or systematic variations or in terms of like thickness here. So I think that maybe the erosion could be a reason. Like, what do you think?
Yes, thank you for the question, Haiwei. Yes, we sure have some hiatus. Maybe it's for non-deposition, because in a shallow lake, maybe you don't have space to form all the sequence. And then what I did was to calculate how many times my cycles it has a complete cycle or where I have some missing bits. The missing bits is that I don't have some of the facies or the transition is abrupt. So I try to find out my erosional or non-depositional by the abrupt change or when I'm missing some change, some transition. So that I think is the first part of your question. And for the second part, that is I forgot the second part.
Because I was asking about like erosion and facies amalgamation. And
yes, so I tried to see the order and if I have all facies that is supposed to be in the order. And my next step that I didn't do is try to relate that, the missing part vertically, and see if I can find some agreement. For example, do we have more missing bits close to bigger unconformity that is regional, or the bigger unconformity there is no control or influence on the missing bits within the high frequency cycle?
Okay, yeah, thanks. Yeah.
So we can take questions on any of the talks in this session. JP's had a very long morning. I'm sure he's happy to stay and answer more, but there were also the other talks prior to his, if anybody has anything they'd like to raise with any of the speakers. And if you feel happy of putting it in the chat, then I can read it out. Not seeing anything coming up. If everybody's hungry, we can break for lunch or breakfast or wherever you are in the world. Yes, good.
For me, it's a breakfast because it's 8 a.m. here.
Breakfast and a very large coffee, I should imagine. So.
Yeah. But we can leave this room open if anybody wants to jump in, and you may want to post something on the chat you feel is controversial you'd like to discuss. Nice to have an opportunity to get people together, and lots of people who are really doing some interesting work in a whole range of fields and carbonates. So I always tell my students there's no such thing as a dumb question. So, if you've got things you think would be fun to discuss, stick them in the chat and see who picks up on them.
Yep.
Stephen, were you going to add a few?
Oh, I was just gonna reinforce to everybody. Yes, we're definitely leaving the session open. There's no need to disappear. It will still be here throughout. So just go away and have your tea. If you want to keep it open, keep it open. I just want to do some blatant advertising on behalf of. No, it's this shoulder. Look, there it is. SEDS Online. SEDS Online. For those of you who are at the EGU session. Or an EGU in 2 weeks' time, face-to-face, anybody who's there face-to-face, we are going to have a thing called SEDS Offline. We're going to be meeting up in a bar somewhere in Vienna. So watch the SEDS Online Twitter feed. And we're going to hopefully see all those faces that for the last 2 or 3 years we've only been seeing digitally. And we'll see if people really are three-dimensional. So just blatant advertising, watch our space. That's me.
Excellent. Brilliant. Well, thank you very much to everybody for this morning's sessions. Fantastic set of talks. Go and grab yourself some food, something to drink, and we will be back in just over an hour and a quarter. So 1:45 time here. So that's, 1 hour, 20 minutes or so. And we'll move into this afternoon's sessions.
And this afternoon's speakers and chairs, please make sure you go to the green room. Oh, I got double thumbs up from Stephen.
Excellent. Thanks very much, everybody. See you all in a little while. Welcome back, everyone. Just allow you all to grab your coffees, teas, whatever, get ready for this afternoon's session.
Hi, Kathy. How are you?
I'm good, thanks.
Good to see you.
And you? We're switching time zones, I think, for a lot of people. I suspect we've probably lost some people from the east, and we're opening up to a few people who are now over in North America, including you, Chelsea, or are you still in Europe? You're muted.
Oh, there we go. That's better. Yeah, no, that does include me today. I'm over in Oregon, so.
Excellent.
Just a little before 6.
Nice and early for, thanks over that side of the Atlantic for coming online early. So for those of you that weren't here this morning, this is the 3rd Carbonate Forum, and we had a great set of talks this morning on a whole range of topics, but largely carbonate sedimentology, seismic interpretation, modeling, and imaging. So a really nice varied start to the day. And we're going to carry on this afternoon with a full spectrum of modern and ancient carbonates and models and a field trip report. So Chelsea's our chair for the first session, so I'm going to hand over to her. Thanks very much, everyone.
Yes, thank you so much, Kathy. So hi, everybody, and welcome to this next session for the Carbonate Forum. We're really happy to have you here. Just to remind you, we will have presentations. They will present their work for about 12 minutes, then we will have about 7 minutes of questions. So make sure and send your questions. You can send them already while they're presenting, but get them into the chat and make sure to send them to everybody or else we won't be able to see them. I'll then read out the questions and we'll go through all of that. So if anything comes up, you can let us know at SEDS Online and we will get your questions answered. Okay, so we were going to have our first talk. It's actually going to be one of the field trip reports that Kathy mentioned, the field trip from Purbeck. So Arnaud, if you are there and can turn on your camera and mic and share your screen.
Yes, I'm there. Hi.
Hi, good morning. Well, afternoon, I suppose.
Yeah, afternoon.
Great, looking forward to it.
Thank you. So today I've been asked to show you some results and the result of the discussion we had along the field trip that we had this over the weekend, so on Sunday. The main aim of the trip was to look at some potential tectonic control on microbial lacustrine carbonate and looking at the Purbeck limestone group exposed in the southern coast of UK along the Jurassic coast in Dorset. So the trip was led by myself and by Pete from Liverpool. So on the back is images that were taken from some years ago. All this work was done during my PhD. So for this field trip, we had in total 9 participants, which we think was pretty good. Over these 9 participants, there were 4 PhD students from Manchester University and Imperial College, 1 postdoctorate from Birmingham University, 1 lecturer from Bristol, 1 person that was retired from oil and gas industry, and one manager from BP. So it was quite a good representation and a good mixture between students, academics, and professionals from the industry. So here you can see an image of the group. We were already pretty tired. It was just before the last stop, but the weather was also very, very good this weekend. So it was a very good choice to go on that Sunday. So that were the stops. So we met in Weymouth. And the first stop was we drove down to the Isle of Portland, and we looked at, I will show you in detail after, but we looked at a disused quarry called Godnor, where we have very well exposed the very lowermost bed of the Purbeck limestone group. And then in the afternoon, for lunch and in the afternoon, we moved to Lulworth Cove in the center part of the area to look more at the fossil forest and New Bay. So most of you may know these outcrops. They are really stunning. We will see some pictures after, and to look on some beds that are a little bit above at the base of the Purbeck limestone group. So on the first outcrop, so it was located on the southeastern part of the island, of the Isle of Portland. Here is a zoom in on where exactly is the outcrop. That's the town called Southwell. And here on the right-hand side, you can see a generalized log that to introduce the stratigraphy to you, not to be lost in the terms I'm going to use after. And in this particular outcrop, we looked at the boundary between the Portland group, which is a late Jurassic shallow marine deposit that we find in the area, with the Purbeck limestone group, and in particular, the mute member, which is the lowermost bed of the Purbeck, almost a unit of the Purbeck. And then we have some transition unit, and we found some beds where we have some microbial development called the skull cap, hard cap, and the soft cap. And all these beds are sandwiched with paleosoils that are were locally named by miners and quarrymen as the basal dirt bed, the lower dirt bed, and the great dirt bed. So you can see with the red square, the red box here, where we are going, what we saw in the very first outcrop. So here you have a picture of the group at this aqua, and I will show you some stratigraphy in a minute. So the first discussion we had here on this first stop was to look, introducing the stratigraphy, looking at the facies and the different texture we found in this bed. And so we identified that there were, in that particular outcrop, only two beds where we found microbial mounds, the skull cap and the hard cap. And that these microbial mounds, they were separated with an intermound facies. You will see more pictures of these facies. And then we also identified that there were two paleosoils here, capping this mounded structure within this skull cap and hard cap, the lower dirt bed and the great dirt bed. And we also looked in detail. So that image here was taken from a mound that is located just here on the outcrop. And we saw that the microbial mounds, that they were first microbial mounds in this outcrop, and that they were composed of three main microbialite facies. The stromatolite, that I didn't put a picture because it's very localized and it's a minor component of the microbial mounds. But we found that it was only located at the base of the bed, and we had some discussion on the controls on that. And but then the main mound builders were what we call a burrowed bandstone that is located around tree trunks and branches mold. So the hole you can see in the middle is a tree mold that was that basically fell on the lake bed, and then this burrowed bandstone was developing around. And then after that we have this thrombolytic framework that you can see already that is thinner at the bottom and thicker at the top. So that could give us some interpretation on how this formed. The burrowed bandstone was mainly formed most likely when the trees are in living position, because it's circular and making like a sort of collar around the tree remains. While the thrombolite, because it's asymmetric, it's much thinner at the bottom than the top, must have formed when after the tree fell down onto the lake bottom. But if we also looked in a bit more detail at these facies. Why do we call that this burrowed bandstone? Because it's made of very sinuous cavity, and that is looking like it's burrowing some micrite. You can see here thin section scans of this burrow network. Sometimes it's very longitudinal and very long. Sometimes we can have some cross section, and we found out, or we interpreted that they were most likely made from larvae tubes. And then if we look at the thrombolite this time, we can see locally sometimes some columnar structure. Here I put some other pictures, but we can find the exact same features in this outcrop, where we found this clot and lumps on the outer part of the thrombolytic texture. Or sometimes these clot and lumps can be locally silicified. Another part of the discussion, the second discussion we had at this outcrop, was about the non-morphologies and the distribution, as well as looking the deposition environment during the deposition of these beds. And we found out, so we didn't measure per se, but that was something I've done during my PhD, so we were discussing all the results. But we measured the maximum height and the maximum width of every mound, and we plotted that onto this sort of graph of the height against the width, and here the perimeter against the area, to look at the mound, the shape of the mound, and to try to characterize their morphologies, and then interpret in terms of paleo-depositional environment. So we can see something we saw very clearly, that the small mounds are more or less correlated at the bottom here on the left, and they have a ratio 1 to 2. So they are more or less rounded, as you can see here. Or if we take only this sub-mound here, it will be like a rounded shape. And then when we go into much bigger sizes, we can see that, and you can see that in the image that is in front of you. That is, by the way, I forgot to mention, a LiDAR survey interpreted. We can see that the shape is becoming much more complex with time. With the size of the mound, and it's the same thing we see when we look at the perimeter and the area. So it's a way to characterize the shape. For small mounds, they appear to be more rounded, and for big mounds, they appear to be more complex. So that was the conclusion. That small mounds appear to be also more tabular. You can see here that's the skull cap and that's the art cap, so the two different beds. In the skull cap, they appear to be more tabular in shape, so flat and elongated, while in the art cap, so the second bed here, the mounds appear to be either more rounded, and if they are big, very much more complex. And in terms of depositional environment, so we took everything I explained now, and looking at what we see and the position of the paleosoil and the remaining of the trees, that the small mounds, the tabular and rounded, were most likely deposited into the shallowest part of the lake, so along the shore. And when we were going a little bit deeper, then was when we started to have this much more complex mounds. We also discussed the timing on the microbial growth, because that was something like how can they develop around the tree mound. So here I show you, we compared that with some images that I provided from a modern analog that we visited during my PhD project in Mexico, Laguna Bacalar, where we find thrombolytic structure developing around trees, in my case mangrove trees, or around pillars of an ancient deck of a hotel that was abandoned since. And that's how we could determine that we knew that the hotel was built or abandoned in 1997, and we measured that that the thrombolite mounds here were growing as fast as 1 centimeter per year. So it must have been, so the conclusion on this knowing that for the per deck, the development of the mound must have been really fast. We will never be able to know exactly how fast it was, but it must have been very, very fast. In the afternoon, then we had lunch. So here you can see a picture of where we had lunch. Quite a stunning place, and it was picnic lunch given the good weather. And we went after that to Fossil Forest and New Bay to look at the uppermost bed of the mute member. So to look at the soft cap, where we have the thrombolite mound that some of you may know develop around the tree stumps that gives this donut shape. And then some other fossils that I'm going to present to you in a minute. So here we mainly saw that here you can see a picture of the group studying this outcrop. You can see here at the bottom the microbial mound bed, and then here we found some presence of bellied evaporite that are into 2 or 3 beds, and on top of that something a bit more brecciated. So we found out that the evaporite were mainly anhydrite and gypsum, but they are pseudomorphs, now recrystallized in calcite. We also find out that the evaporite beds do not appear to be very extensive. They are only a few meters laterally. And we also found that this evaporite, that you can see in the picture here, are capping the microbial mounds. So here is a microbial mound from the soft cap. Once again, this tabular mound, and this evaporitic bed capping on top, which indicate that in that case, we may have had a change from something that was more brackish water to something to an environment that was more hypersaline. And then, as I told you, we saw this breccia above the evaporite bed. So here you can see a picture of this breccia, and then here, slightly further away from the fossil forest area, and it's locally known as the broken beds. So we had discussion on what could cause form this collapse, this breccia, and we had 2 main hypotheses: either collapse breccia due to dissolution of
2 minutes.
Okay, thank you. Or tectonic. So the collapse breccia must have probably been due to a dissolution of localized evaporite, potentially this evaporite bed that we find now, remnant and recrystallizing calcite, and that's something that we find in the area in this image. If it's, even if it's clear, but we have the undisturbed bed of this unit called the Cyprus stone, and laterally and abruptly we have the broken beds that form in the exact same stratigraphic area. And the tectonic hypothesis was due to because when we go to see laterally, so that's an image from Nuke Bay, a bit further on the coast, with the last stop, we can find this folded this fold structure. So we can imagine that, and we interpreted that potentially these broken beds here were on one limb or potentially linked to some tectonic forces that were in action after the deposition and much later of this bed. And the conclusion was, after seeing these two main outcrops, that it must have been a combination of both processes. So potentially collapse of due to dissolution of localized evaporite, and then remobilized later due by tectonic forces. And that was the last discussion and the last stop we had. And then I will leave you. I will thank again all the participants that came and for you today to listen to this presentation. And I leave you with some images to where they were taken from. Also, I won't be able, unfortunately, to join the discussion session after. I'm sorry for that. But if you have any questions, here is my email address. And please do not hesitate to send me an email if you have any further questions about the tool. Thank you very much.
Great, thank you so much for that great presentation. Looked like a really interesting field trip, and I'm sad that I wasn't able to attend as well. So if you can stop sharing your screen now, we're going to move on to our next presentation. Drew, thank you so much. Drew, if you can start sharing your screen and turn on your video and mic. Hi there.
Hey.
That would be great. So
All
Drew's
right.
going to be talking to us all about the ichnological diversity in various intertidal zones in Abu Dhabi, a place where I also work. So I'm really excited to hear your presentation.
All right, great. You're seeing it all right?
Yes, we see that. Great. Go ahead.
All right. So hello, everybody. Yeah, my name's Drew, and we'll be going over my assessment of the ichnological diversity intensity in Cantor Lagoon in Abu Dhabi. So I just wanted to start and talk about the main focus of our research here, which is hard grounds. So what are hard grounds and why do we care about them? Well, hard grounds are sedimentary carbonate features that are typically found exposed on the seafloor, and they're common early diagenetic features, yet we don't really have too much known about the physical, chemical, and biological processes that govern their formation in the modern. So why do we care about them? Hard grounds are related to the global carbon cycle. So they present a viable place of research as they're integrated into groundwater aquifers and hydrocarbon reservoirs, and maybe even sequestration here in the future. So we want to start with the importance of burrows in the hard grounds and why we believe that burrows have a significant role in the formation of these hard grounds right now. So burrows as a whole are difficult to identify within carbonates in the rock record. So if we can go now to the modern and look at examples of these burrows and maybe their associated features with them, maybe we can build an idea of how these hard grounds are actively forming. So some factors that they might influence are the porosity and permeability increases or decreases, any potential mucus linings within the burrow's walls that would drive geochemical changes, any actual macrofauna that could affect the diagenetic phases, and as well as the actual incorporation of aragonite from shell debris into the system. So how can we go about determining this influence of the burrows? Well, we can observe how they may reduce or enhance the porosity permeability. We can check their linings and see if there's any isotopic variance or trace element variance from the burrow to the matrix. We can analyze the water chemistry of both pore and tidal waters to assess the hydrologic influence in the diagenetic system. And we can also use Raman spectroscopy to identify our levels of aragonite and calcite and potentially even dolomite. And Raman spectroscopy is a great tool for the detection of early diagenesis in an in situ method. So just a little background on the actual Abu Dhabi hard grounds, following this 2017 paper from Paul and Lokier, who described the hard grounds in a similar setting to our subject sites as bioclastic, so largely consisting of these skeletal grains made from gastropod shells, as well as some sediments, peloids, and forams. So hard grounds can be traced all the way from the supertidal sediment subsurface to an outcropped seaward subaqueous surface. And they observe phases of aragonite and high magnesium calcite cementation, as well as active lithification tend to follow intertidal sequences or the sea level movement that was associated with these intertidal sequences. So the hard ground itself appears to be within the phreatic zone and following very early shallow burial diagenesis. And they mention dark coloring that was present in a lot of the hard grounds, and we believe that this is due to higher relative organic matter within the system. So the question we're chasing here is, what is happening within these intertidal zones to promote the hard ground formation, and specifically looking at the burrows. So just a quick introduction to our subject site. This is the United Arab Emirates on the left. And in the right, we can see our red box here of our actual subject site in relation to Abu Dhabi in the north. And if we zoom in a bit more, we can see our 4 subject sites, all with similar proximity to this primary tidal channel and along about a 600-meter transect. So each of these sites has unique levels of bioturbation and varying population densities, and hence why we chose them. So I'll just briefly go over some of these sites, and I'm going to actually start with site 4, which is our farthest upslope. If you look at the cross section here on the bottom, you can see site 4 in relation to our intertidal zone. So this was the lower edge of the microbial mats, and if you look at this dark kind of ring around these channels, that's all composed of microbial mats. So we wanted to look at site 4, which is within the sediment a bit more, and try to give some sort of characteristic. So on the left, we have a carbonate log that you'll be seeing a lot in this presentation. And on the right, a photo of the core that we opened at the University of Bristol. So I'm actually gonna not talk about this one too much as we haven't done too much research on it yet, but instead move on to site 1. So site 1 is what we nicknamed Crab Cove, as there was an abundance of crab burrows. We also observed some marine worms, the polycate worm nares. And over on the log, you can see in green the crab burrows that were observed and the worm burrows that were observed. So this is our farthest downslope site. It was our finest grain size. And we noticed that there was a gastropod layer closer to the base of our core, or of our pit, excuse me. And the crab burrows were sometimes filled with shell debris, and there was fewer worm burrows compared to our other sites. So now we can look at some of the grain size from our site 1. This blue box is representative of what is shown on the log. So our log here on the left is actually from our field observations and a dug pit of about 30 centimeters in the field. And the entire section of this grain size is based on the core to the right that you see. So the trend here obviously is it starts a bit coarse and then drops very significantly and then coarsens again at the base. And we might see this trend in the future, but as you can see at the base of our core here, of our log here, we see some gastropod peasants beginning, which is a bit interesting considering the large drop in grain size. So then we can go to our site 2, which was nicknamed Skittle Grove due to our proximity to a large mangrove. And this was kind of a mixed site. It had both crab and worm burrows, but in different relative abundance. And this was also a very shallow site. Here we were only able to dig our pit 20 centimeters before we reached the hard ground. And our notes that we made were that the gastropod shells tended to be mixed into the entire matrix of the section, as well as it appeared completely mottled or bioturbated completely. So here we have our grain size again. This was a little bit similar from the core to the actual pit, luckily. So we can see kind of a similar trend here where we start coarse and then we drop in grain size. But this site didn't display too much of a jump to the coarse at the end. So if we compare it to the first site, we can see again that the average grain size actually does increase to site 2 from site 1, but you can see there's much more variance in site 1. So the final site we'll go over is site 3, which we nicknamed Mary's Nirvana. And this was due to the large abundance of worms that were present in the shallower sections. So you can see over on the log here from about the top 15 centimeters, we were just heavily burrowed by the Nereis worm. There were no observed crab burrows, but instead there was a large presence of gastropods and bivalves and other shell debris that accumulated downward through the section. So as these shells accumulated, the worm burrows actually tended to diminish with it. And here we can see the grain size again, this time displaying a much different trend of beginning fine and coarsening upwards. And if you look over to the photo on the right, in this top 10 centimeters or so, you can see a lot of these dark patches and little teardrop shapes. These were all worm burrows, and they're very condensed in a very small section. So when we were actually in the field, we were able to observe many, many worms just by scooping our hands through the sediment. So if we compare site 3 to the entirety of the other 2 sites, we can actually see that it is coarser than the first 2 sites, despite its starting fine trend moving upwards. So I think where we want to go from here is identify the Nereis influence on this grain size. With the extreme presence of Nereis worms in that top 15 centimeters, why is it maybe affecting this completely different trend in grain size to the other 2 sites? Also wondering, does the shell concentrations at the base explain these coarsenings that are occurring in most of the sites? So just to move on a bit, we'll look at site 2 again, which was our Skittle Grove nickname. Here's a great photo of JP Zonwald from the University of Alberta and Fiona doing some coring and on our pit, and Fiona doing some pore water analysis in our pit. So the second photo here is the core that we opened at the University of Alberta, or sorry, at the University of Bristol, and the one on the right is from the University of Alberta. Our idea here was that we wanted to use an X-ray to determine our levels of bioturbation so that we could then go perform some isotope sampling. So over here on the right at the U of A photo, you can see some straws in place. This is where I sampled for our isotopes. And you can see with our X-ray why I might have chosen some of those spots. So when you look at these X-rays, there's, I think the main thing that might catch your eye is the heavy presence of gastropods and burrows and bivalves and just random shell debris. So what I want you to focus on is more or less the areas of dark colors, which is the areas of less density, which we interpreted to be bioturbation. So when we jump to the next slide, we'll see how good it looks when you spend some time and try to trace all these burrows.
2 minutes.
Thank you. So the red is worm burrows, the yellow is crab burrows, and the purple is areas where we wanted to sample. And our rationale behind this was to sample within an actual burrow and then the surrounding matrix to see if there's any differences. So just to quickly go over our isotopes that we got just recently, our white dot right here in the graph is our surface value at our 2,1. And all of these groups to the right are mostly related to this change in the carbon isotopes. And that's what we want to pay attention to. So organisms are going to preferentially take up the carbon-12, the lighter carbon. And so we would expect if there's any sort of microbial activity or in faunal activity occurring that we would see this concentration of the heavier carbon to the right. And that is what we're seeing in our middle depths. But at the end, we do see a bit of an outlier in this one crab burrow. So just for time, I'm going to kind of jump ahead really quick. So here's some cool surface traces that we saw in the field, all made from gastropods and making these cool patterns. And we were able to identify some of them here. So we have 2 species of bivalves that we saw a lot and about 3 species of gastropods. Going forward, we just want to look at the compositions of these shells and see if they have any incorporation into the system. At the subsurface, you've heard me talk about the polycate worm, the Nereis species. there has been some research done on the Nereis worm, and Eric Christensen here has a few papers showing that Nereis is capable of stimulating CO2 and ammonia production. They're very capable of accounting or of creating oxygen uptake in a closed system. Some of it due to the burrow walls and some of it due to the worm itself. And obviously know that when a subsurface sediment is exposed to oxygen, the carbon reaction rate can be enhanced, and that burrow walls as themselves can act as mineral nucleation sites. So the main message here being that the Nereis worm can certainly affect the system, right? And then there's some marine crabs that we saw, and there's the ghost crab, which I'm sure any of you have seen if you're walking on a beach at night. And there's also the sand bubbler crab, who makes these really cool sand bubble fecal pellets that we were able to see in the field. So I think where do we go from here? We want to do some CT scanning to see the burrow systems in better light. We want to do some more stable isotopes on our crab burrows and our hard grounds. And of course, we want to do some trace element work, which will be really important to see the differences in the burrow to the matrix and give us some more information to the diagenetic system. And we'll also be using Raman spectroscopy to be looking for aragonite and calcite also in the matrix versus the burrow. So that's all I have. Thank you guys. I just want to say thanks to all these folks here, and appreciate it.
Super, thank you, Drew. Nice presentation. If you have any questions out there in the audience, please send them over to the chat. Please make sure and send them to everybody so we can all see what you're wondering about. And we can get to those soon. So while we're waiting, I have a couple questions, Drew. So I saw in your isotope plot, you had some values that were actually pretty light in terms of oxygen isotopes.
Yeah.
So those, I guess the two over to the right, quite a significant difference. Are these sites that are a little bit more open and they're not as restricted, or what's causing that to be so different from the other values?
That's a good, so just for reference over here on the right, so the 2 is just our site 2, right? And every number is depth. So the 14 centimeter depth, for example, would relate to the 214. I think the reason you're seeing some differences in the lighter is mostly due to evaporation. And I think in this instance where you see there's a 14 centimeter depth here, and then there's also a 14 centimeter depth here. So we did kind of an A and B, and the A tended to be closer to the surface and the B tended to be deeper in the core. So I haven't looked into it too much, but I would assume that there's some sort of interaction with the actual air for the A, which was our top point here, and then our B is our lower point. If that answers your question at all.
Yeah, a bit. And what about the yellow dot? I can't really see, the text is a little bit small, but where's that one?
Oh, okay. Yeah, okay. So this yellow dot down here is related to this crab burrow at our deepest depth. And that is a really interesting, right? It's a big outlier. And we think that maybe there's a lot of irrigation that occurs through these crab burrows. So that's our immediate thought, is that for whatever reason, the water is filtering through here better and getting more of the surface water down deep. This point over here at the 4.9, 34.8, we think is just a bit of a mistake. It doesn't really seem to make too much sense. So we don't want to pay attention to this one too much, but that's what we want to focus on going forward now, is these crab burrows, right? So this is a really weird outlier, and we thought that the worm burrows would actually have more of an influence, but it seems that the crab at depth is a bit more significant. And that could also be due to the amount of shell debris that's down here too, just allowing aeration and irrigation.
Yes. Okay, we're gonna get to one more question from Kathy in the chat. She says, "Hi Drew, great talk, well done. Could you say a bit more about the trace elements you're going to measure?"
Yeah, I think the main thing that we want to look at there is probably nickel in the burrows. So as a bit of a proxy for organic matter as well throughout the entire section. So just after speaking with Hillary very briefly, she spoke that they have a way of actually looking at a single grain for the trace elements. So I think kind of a similar approach that we took for the the isotopes, we want to look at the trace elements within the actual burrow walls themselves, and then the surrounding matrix. So maybe so for example, here where we took a section from the actual burrow and then a section from the matrix above it that's undisturbed. I think we want to do a similar method with the trace elements and see if there's any variance on the actual burrow walls to the matrix surrounding it. And through the entire section, I think we probably want to be looking at nickel, for example, to be seeing the organic matter. As we saw through the isotopes, there's clearly some microbial processes going on within the middle section of this core. And so if we can get a better idea of what those are through the trace element work, then I think that would give us some really interesting ideas as to what's going on.
Great. Yeah, I would also suggest maybe throw sulfur in there as well.
Yeah, right.
In that system. Yeah. Okay, I will have you stop sharing your screen, please.
Okay.
And we will move over to Tom Kibblewhite. We're going to stay in Abu Dhabi, though. He's going to talk to us a little bit more about some geochemical evidence of the precipitation that goes on in the hard grounds.
Afternoon, everybody, or what time is we are? Like Chelsea says, I'm looking at the geochemical evidence of the informal influence that Drew's just been going through in the Abu Dhabi Sabqa, and seeing what, hopefully getting on to just looking at what influence that may have had on the hard ground precipitation. So this is work with the same group of people here in Abu Dhabi. So yeah, Drew's just gone through the sediments that we saw there from the 4 sites, what burrows and borings are going on. Most of my talk will be looking at the relationships between geochemistry and this informal activity that he's identified. I've gone at the end slightly into looking at hard ground formation, but unfortunately we didn't manage to get most of the data until Friday. We got a load more data for so the analysis I've done is a bit limited, but shows some interesting things relating to Drew's talk. So again, like Drew said, we're working in the Persian Gulf, UAE down here, Abu Dhabi working just to the west of Abu Dhabi, Cancer Lagoon. Zoom in, we've got the intertidal zone split into 3 parts. We've been working in the lower intertidal zone on 4 sites. And here are the 4 cores that we've got here in Bristol that Drew mentioned. If we've got site 1, site 2, site 3, site 4 going inland, I'm going to switch the map around now, and you can see here's site 1, the furthest into the lagoon, site 4, the furthest inland. And across this sort of 600 meter stretch, there are several tens of centimeters elevation gain roughly, but hardly anything. So when the tide is coming in, it moves across from site 1 to site 4 over the course of a couple of hours very rapidly. And this affects the amount of time that each site is inundated for with seawater. So the site 1 we think is inundated for a longer period of time than site 4. And this may be influencing what we see in Drew's burrows and surface activity and how much biodiversity there is in each site. Interestingly, the salinity is higher at site 4 than at site 1, so all of it is at least as saline as the seawater that's flooding over it. But as we move inland to site 4, this is probably the seawaters are dissolving salts precipitated on the surface and the salinity is increasing. Related to this, we have the crab burrows, which, as Drew mentioned, lots in site 1 that disappears inland. The worm burrows, or the neries, lots in site 3 and site 2. And then Drew didn't mention this too much, but the microbial maps at site 4, this dark bit on the higher upper intertidal zone, they're visible, but then they disappear and you don't get any down here. And I posit that perhaps the relationship to salinity is influencing where these different organisms are living. So they all like saline environments, but perhaps as it gets increasingly saline, it's too saline for the burrowing organisms. And because the burrowing organisms are not there, the microbial mats get a chance to establish. But we'll see what the chemistry says. So Drew's mentioned that we took cores. We also dug pits in the Sabkha and then stuck rhizomes into the sediment, which are under vacuum and suck up pore water from a range of different depths. And then our cores were taken just behind here once we'd finished sampling. So if we go to site 1, as Drew mentioned, it's furthest out to sea. You've got crab burrows, which you can see slightly more reducing conditions in this crab burrow, giving it darker colors. You've got shells infilling this crab burrow here. And there's a slight change in how shelly the layers are, and that relates to the grain size and the variation in worm and crab burrows that Drew mentions. We can see that for the whole of this site, it's oxic conditions, which perhaps is due to all the burrowing going on, that the surface waters are mixing down and oxygen is allowed to reach greater depth, 30 centimeters here. You can see it in the same way the ionic strength or the salinity in other units is also fairly homogeneous through the profile. pH is circumneutral, decreases slightly with depth, and because of that, well, and then that gives us gypsum and aragonite saturation indices on the right here. Saturation index is, if it's at 0, then the mineral is in equilibrium with the pore water. If it's above 0, it's supersaturated and likely to precipitate. And if it's below 0, it's undersaturated and less likely to precipitate. We've also got calculated values for calcite and dolomite, but they're more supersaturated, and halite is less supersaturated. It's gypsum and aragonite are the main things we'd like to see precipitating here. And because aragonite is near 0, then it means that it is possible that carbonate is being precipitated somewhere in the profile, but we've not yet done any analysis of the sediments to determine the mineralogy. If we move on to site 2, again, we've got a highly bioturbated bit here, and we've got, again, some crabs, but not so much activity, and worms to a greater extent. Grain size is less useful here, but the EH, again, same as the last site, it's all oxic. It's fairly homogeneous. It looks like the mixing is, bioturbation is having a mixing effect. Again, ionic strength, fairly low. I mean, it's high, but low compared to some samples. Is homogeneous, but the pH is all over the place. So perhaps, again, this is because of the bioturbation, but the pH is more temporal. So something that's been recently mixed or less recently moved we might be hitting different parts of the system. We might be inserting our rhizomes and taking pore waters from one of the burrows that Drew mentioned in different stages in their formation. And because of this, the saturation indices are slightly more wobbly as well. The aragonite and calcite and dolomite, they're all highly influenced by the pH. And so it wiggles around, but because all the parameters are the same, it's fairly similar conditions and likelihood of carbonate forming. Move further inland to site 3, we've lost the crab burrows, but we have, again, highly bioturbated bit with lots of worm burrows at the surface, which then they stop as it becomes shelly. And you can see in the grain size that's reflected as well. EH here gets more interesting. We've got the oxic area at the top, and then it becomes anoxic. So below 0 EH, you've got reducing conditions. And that's clearly, there's not so much mixing here. And yeah, from 0 to 10 centimeters, it's likely the worms are helping to bring down this oxygen again, keep it oxygenated before it becomes reducing. And then at depth, it moves back towards oxidizing because of the influence of groundwaters coming up from below. I've not plotted them here, but there's a groundwater that has a EH similar to this and an ionic strength that is higher than anything we've measured here. So that's fairly linear mixing line between the surface waters and the groundwater at depth. And that's reflected as well in the pH, which again has a slightly acidic groundwater. And because of that, the aragonite concentration is, saturation is slightly nearer equilibrium. And because of the higher concentrations, the gypsum has gone up and also potentially reached equilibrium. And there's more likelihood of gypsum precipitation in this site, but less likely than that. We move on to site 4, further inland again. Drew mentioned, but only briefly, we've got mats at the top, patches where it's more detrital sediment and less mat interbedded with the matty layers, and you get shelly at depth. We don't have any grain size for this, but the EH here starts off oxic, they're all oxic at the surface, and immediately, within a few centimeters, drops down to really anoxic conditions and stays reducing for the whole depth.
2 minutes, Tom.
Which makes sense because microbial metabolisms will be using up lots of the oxygen and other electron acceptors. Unfortunately, because of the superionic strength, we can't see any peaks in those electron acceptors. But again, this one is showing fairly linear mixing with one of the groundwaters that we've identified below. Interestingly, the pH is very high in this one, and that's reflected again in very high aragonite saturation and higher gypsum saturation. So going back to what I said before, the salinity may or may not be influencing how these different organisms are forming, where they're positioned. It may also just be to do with the types of sediments, but I'm not sure. And then haven't really mentioned how this relates to hard ground apart from the saturation indices. I said that the ionic strength was fairly similar and was representative of most of the ions, but a standout from that is the bicarbonate, which shows a different trend to the ionic strength, which is representative of all the different major ions. We see that it's very high in site 4, which is the microbial map, and that makes sense because that's doing odd microbial stuff. But in site 1, we also have very high bicarbonate, and we're not quite sure why. It's not really reflected in the calcium ratios or anything. They don't plot very well on a depth graph, but if we move plotting the calcium over chloride ratio against chloride, then we can look at the mixing between these well waters in the green squares here and surface waters in the blue diamonds, and then the sites are colored as before. And we can see that site 3, site 2 and site 1 stay around the surface water ratios and chloride concentrations. But then site 4, the microbial map, is mixing, as we saw with the wells. Site 3 is mixing with the wells. But then interestingly, if we look at the strontium ratio at site 3, that's significantly depleted and the calcium is slightly depleted, suggesting there might be some carbonate precipitation, possibly more likely aragonite with the low strontium. And just to add that it's not gypsum precipitation because the sulfate isn't similarly reduced. But yeah, only got data on Friday, so more to be done on that.
Super. Okay, thank you so much, Tom. Everybody in the audience, please type your questions into the chat, send them to everybody, and we can get them read out and Tom can start to address them. While we're waiting for those, Tom, I had a question. You have a lot of different sites that you've looked at, and of course the geochemistry of the pore waters is quite variable. I'm curious if you think that tidal ranges or tidal cycles, let's say, have anything to do with where you see some of those things like the redox zone. So if you were to sample at one point in the tidal cycle versus a different point in the tidal cycle, do you think you would see much of a difference?
So we've had some logger data that we put loggers out at various points. At
the surface or also at depth?
So we had some at the surface where the site was and in the tidal channel. I went back to so we had some loggers within the tidal channel here and others right by the sites. And in all of those, you can see sort of the salinity moving over a tidal cycle from sort of up to 100 grams per litre, and then down to 75 or so. So the range is fairly similar for all of them. It sometimes gets more, the peak salinity up here is more, so there's more variation with the tidal cycle as you go inland. We sampled all of these at lower tide because that was the only time we were able to actually get out there and take the poor waters. But certainly we think that is something to look into. It's something we are trying to account for. And there's a possibility of tidal pumping and where is the water flowing as it comes in? Is that the same flow path as it comes out? And lots of questions that I've not managed to look at all the data for yet. But.
Yeah, absolutely. That would, to me, that would just be really interesting to see, go to the same site and just measure the pore waters a couple times throughout the tidal cycle and just see, with depth, is it changing a lot or, not necessarily just at the surface, because of course we should see some variability there, but are things like the redox zone, is that moving up and down during different times of the tidal cycle?
Yeah, there's Hazel Valak who previously worked on this site. She had a site just over here and various bits of pore water work. She sort of started that a few years ago that we built on, and she had a few samples at different times of day, but I'm not sure what the redox was for.
Yeah, no, I remember her work very well. So I'll have to go and check back, see if she had anything along those lines. Any other questions, please send them in the chat. So just in case we have a couple more popping up, while we're waiting, what's your next steps? So there's a lot to do.
Yeah, lots to do. Looking at this data a bit more, it shows some promising signs of having lots of interesting bits. We've got samples for stable isotope analysis, so to complement Drew's stable isotopes on the sediments themselves. We'll hopefully get those done in the next few months.
Yep.
A few for methane analysis, which might just show that there is more going on in the microbial bit. But we want to do we want to do trace metals. You have to dilute these hundreds of times to get readings on an ICP or an IC, so you lose all the trace metal analysis. So hopefully at some point we'll get some mass spec or something to get those trace metals and potentially rare earth elements as well that I know Hillary's interested in. But.
Yeah, absolutely. Okay, we have a question in the chat. Excellent work. You reminded me of the Sabkha in Kuwait. We used to see the same relationship between type and position of organisms and salinity around the cores within the Sabkha. Do you see any differences in association to the different weather seasons? In Kuwait, we have wet and dry periods, but in Abu Dhabi, I think it's mostly dry.
Yeah, I'm not sure. Again, that's something Hazel's looked into, the long-term variation, but she wasn't looking at explicitly at how that affects the distribution of the morphologies and the different organisms. So I'm not sure what effect that would have, but I'd imagine the tide is still the main, bringing saline water in on a regular basis, and
I would
run off
think so.
or not.
Yeah, I would think so as well. As you mentioned, in Abu Dhabi, it's mostly just dry, dry or maybe more dry. So Stephen wants to know what time of year you sampled.
Yeah, this was in November last year, so 6 months ago. I know that Hazel's were in January and June, so we sort of got a different time of year. So if there is some
June as well, okay.
So yeah, that's Hazel did.
Yeah,
June we did. Yeah. So.
Great. Also mentions that there will be differences in the water table level and salinity.
I think there are, yeah, some differences. Again, I've not looked into our data on that enough yet. But
yes, lots to go into. All right, great presentation. Thank you so much. We're going to move on. We have one more presentation in this session. Evind, if you would like to put your video and sound on and share your screen. And we look forward to hearing you talk a little bit more about meteoric diagenesis. Yeah. Before you get started, I just want to remind everybody in the audience that during the 15-minute break, which will come after this presentation, we will open up the floor and everybody can have a discussion about any of the presentations that have gone on thus far. So stick around and yeah, we can all discuss together.
Right, can you see my screen okay?
Yes, looks great.
Yeah, okay. So my talk is about meteoric diagenesis and implications for porosity development across mineralogical boundaries. As we know, carbonate evaporite successions are susceptible to dissolution and collapse. And meteoric water flowing across lithological boundaries may lead to diagenetic changes to the host rock through processes such as de-dolomitization. And de-dolomitization is a process where dolomite is basically replaced by calcite, and generally that will decrease the porosity. So you can see from this log here that the calcite layers matches up pretty well with the decrease in porosity and permeability. So this can be quite important. So the aim of this study is to better understand the controls of these processes by applying reactive transport modeling to mineralogically complex systems. So a bit about the methods and modeling workflow. First and foremost, we use ToughReact, which is a modeling code that simulates fluid flow, chemical reactions, and incorporates feedback between porosity and permeability. We model in 2 consecutive steps. First, we do a 0D simulation and then a 1D simulation to evaluate the main controls on dissolution and precipitation. And the main control we have found so far are water chemistry, temperature, kinetic rate, and flow rate. And we'll be focusing on the water chemistry for this talk. So this is a 0D model. It is basically one cell. We take our initial water and equilibrate it with the mineral in that cell, which in this instance is calcite. And then we get a calcite equilibrated water. So these are very handy because they give information about the chemistry and diagenetic potential of the fluids, obviously before, but also after reactions. By diagenetic potential, we basically mean how much that can be dissolved or precipitated by that fluid. And we also get reaction rates, so how long it takes for to fully precipitate or dissolve in that cell before it reaches equilibrium. Then we have the 1D model, which is a column of cells. We use the equilibrated water from step 1 as our input water. Then on the top and bottom, we have 2 infinite volume cells with fixed pressures. And this creates a pressure gradient that drives the flow from the top to the bottom. And after the simulation, we can see what has happened to the model. So we might see something like this, where we get porosity changes in the cells until a certain depth, and we might get replacement of some mineral with another. Then a bit about the modeling parameters. I've been using this water chemistry for my input water, which is the average freshwater lens from Bahamas, from this Whitaker and Smart paper, which has a pH of around 7.5, 7.6, and this PCO2. For our physical parameters, we have a permeability of 2 Darcy, 30% porosity, a discharge rate of 1,000 millimeters per year, and 25 degrees temperature, which is constant. For our chemical parameters, we have calcite and anhydrite assumed as equilibrium minerals, which means that they go straight to equilibrium right away, while ordered and disordered dolomites are kinetic minerals, so they will need some time to reach equilibrium. And we use a reactive surface area of 1,000 for the kinetic minerals. Then for our simulation parameters, we have 5,000 years simulation time, grid resolution of 1 meter, and a total length of 10 meters, which means 10 cells in total, not including infinite volume cells. And our initial water has these saturation indices. These are a bit surprising, especially with respect to dolomite. We really didn't expect them to be so oversaturated. So I'll come back to this later. So for our first simulation, step 1, we take our initial water and equilibrate that with respect to disordered dolomite, which is this light red color. And then we get this chemistry before and after, all including the important ions there. And what happens in this cell is actually de-dolomitization. That's why we get less calcium and more magnesium afterwards. And we can also, even though it's not showing this, we can also see that from the mineral composition of that cell after simulation. This, of course, eventually goes to equilibrium, and we inject this water into the column. And after 5,000 years, nothing has happened here. And that's not really surprising either, because if you look at this equation, then this water is at equilibrium with both dolomite and calcite. So nothing should really happen here. In the next step, we use ordered dolomite with this red color, equilibrate that. And we see that we get a bit less calcium, a bit less magnesium, and a bit less of bicarbonate. That's best explained by this equation for primary dolomite precipitation. We inject that water into the calcite column, and here we get some change. So we see that dolomite, which was initially at 0, we've had precipitation of that, most of it in the first cell, and then it gradually decreased to 0 downwards. We have had some porosity increase, and we've had a calcite decrease, which matches the dolomite increase. So we can say that the dolomite is replacing the calcite here. This is the chemistry afterwards, which supports that. More calcium in solution, less magnesium. This is the equation for dolomitization, which is what is happening here. Then on to the third simulation we did, which is for de-dolomitization. So to get de-dolomitization, we need to have calcium ions in solution. And one way of getting that is to try to dissolve some calcite. What actually happened here is that the water was already super saturated with respect to calcite, so we get some calcite precipitation.
2 minutes.
Yeah. In the next step, we inject that water, and we basically get the opposite reaction of what we saw before. So calcite increases, porosity decreases, and dolomite decreases. Yeah, here are the concentrations, and so this is de-dolomitization going on. Another way of getting anhydrite into solution is by dissolving anhydrite. So we do that. The solution was very undersaturated with respect to anhydrite, so we get a lot of calcium and sulfite ions into solution. We inject that, and yeah, basically the same de-dolomitization process happens here, but the main difference is that it happens much faster. So in the simulation, the top 2 cells are fully replaced by calcite. Yeah. So one reasonable question to ask are, how valid are the results from these simulations? We need to remember kind of what's the purpose of the model, and that is to look at these main controlling factors. And I think, I definitely think that these simulations give some insight. So we have looked at changes in water chemistry due to water-rock interactions, and that seemed to be very important. Temperature, recharge rate, and kinetic rate we have not looked at, but those are also important according to the simulations. We see a porosity increase during dolomitization and a porosity decrease during de-dolomitization. That is what we expect in nature. But of course, this model is way too simplistic to reproduce the complex patterns that we see in nature and that you can see on the right here. Yeah, and it's important to remember that modeling relies on many assumptions. One of the key ones here are only matrix flow allowed, so no bypass flow. We got fully saturated pores. Yeah, the simulations show that dolomitization can occur at 25 degrees with meteoric water. Is that really realistic? I think we need to go back and look at the input water to be more sure on that. And then, yeah, young dolomites are generally disordered and become ordered over time. So is it really realistic to precipitate ordered dolomites under these, and especially under these temperatures? So yeah, there is definitely some future work. So I'll just finish with this. We will circle back and look at the input water chemistry, try to model bypass flow with fractures and increase the flow rate. We'll refine grid resolution, look at 2D grids, and look at some other geochemical environments like the mixing zone and Weddell zone. Yeah, that was it. Thank you.
Great, thank you so much. Okay, so we already have some questions in the chat. Arlene wants to know which parameters in your model takes the connectivity and surface area of your porosity into account. Should your model work equally for intergranular, moldic, or fracture porosity?
Yes, so in this, go back a bit. Yeah, so so in these models, the surface area will only matter for the kinetic minerals. So for the equilibrium minerals, then basically what happens when the water hits the first cell is that it goes to equilibrium straight away. And we can assume this because these reactions are relatively fast. So when we model for 5,000 years, that's a reasonable assumption. For the kinetic minerals, we can't really do that because we know that dolomite is much slower to reach equilibrium. So then we use reactive surface area. And I know that there is a lot of uncertainties regarding this. It really depends on you know, how fine-grained the sediment is, if there has been a lot of cementation. So what we will do is to use an end member approach to kind of capture a bunch of possible scenarios here.
Great. So one question that I had, oh, sorry, we have one more in the chat, so I'll have to get to mine afterwards. So they say, great talk. I'm curious how you calculate the dissolution and precipitation rate for disordered and ordered dolomite. Is it based on their saturation state and some other factors?
Yeah, so the calculation of the dissolution rate is done entirely by the modeling code. But for instance, to use these 0D models as an example, so this cell is actually in 3 dimensions. So so it's a 1 by 1 by 1 meter cube. So you know that that cell would be able to hold 1,000 liters of fluid, and then the program or code calculates the precipitation or dissolution based on that.
Based on that volume, then.
Yeah, so what you basically get are 2 files. You get one file with your mineral where it says how much the porosity has changed and how much the minerals has changed. And it gives you one file with that shows you how the concentrations of ions has changed in the water before and after simulations. So it actually gives you 2 ways to calculate what has happened there.
Yeah, perfect. Okay, hopefully we can get quickly to the last 2 questions in the chat. Mohammed wants to know, how do you know about ordered and disordered dolomites in reactive transport modeling?
I'm not sure if I understand the question. Could you elaborate, perhaps?
Yeah, Mohammed, if you want to add a little bit more to the chat on just exactly what you're trying to get at, then that would maybe be helpful. So now we're going to move on to Jim's question. It's a very interesting talk. Thank you. Sorry if this passed me or if I'm being thick, but could you explain a bit more why you invoked a different dolomitization reaction for the ordered dolomite case versus the disordered case?
Yes. Yeah, so this is in the first step. So what's happening here is that the water equilibrates, and afterwards we see that the concentration of calcite is less and the magnesium is more, and bicarbonate is the same. So what I've interpreted from this, yeah, and also what I didn't show is that the fraction of dolomite increases and the fraction of calcite increases in this one cell. So what I've interpreted from that is that dolomite goes with calcite ions and transforms into calcite, and we get more magnesium into solution. So that's basically what I've interpreted from this plot. And then that's also why we don't get any change here, because the solution is at equilibrium with calcite. And when we push this water through a calcite column, then nothing really happens. Okay. For this ordered dolomite, we see that both the calcite decrease, the magnesium decrease, and the bicarbonate decrease. So that is best represented by this equation. If we look at the previous one, then the calcite decrease while magnesium increase. So we need different equations to explain it there.
Yeah. This might be a good time to stop the questions, because I think there might be some additional comments to that specific question. So we will now have the open discussion. Kathy, I think will run that, but you are welcome to turn on your videos and your mics and get into a little bit more depth conversation.
Great. Thank you very much, Chelsea, for running that session. That was great. And thanks to all the speakers. And as Chelsea just said, we're going to leave the cameras and mics open now for the next sort of 15-20 minutes. I guess I should probably say anybody who's speaking in the last session should go to the green room if you haven't already done so, just to check the mic and everything else. But for those people who want to stay here and don't want to grab a cup of tea or coffee, feel free to fire ahead. So questions for Ivan, Tom and Drew from the last few talks, or even to Arno if anybody's got anything they'd like to ask about the field trip. Hi, Gabriel.
Hi, Kathy. Good to see you again. Interesting research. Hi, Fiona, if she's still here. Yeah, I'm not sure Elvin quite answered my question, and I didn't quite understand the answer. So I suspect the question wasn't clear. Well, so the title is implication for porosity development, and I didn't quite understand the actual implication of the model and the parameters on porosity development, and how can the initial porosity connectivity and shape not play a key role in the chemical reactions that you're modeling?
So there were three things you said there. Can you repeat them?
Right. No, sorry. Obviously, that has to do with my previous research. So there are many ideas in my mind. But yeah, as fluids flow through porosity, they will interact with the host rock, and I'm assuming that the geometry of the porosity and the connectivity of the porosity will define, will influence how much reaction will take place. So I would have expected this parameter to be crucial in your model, and yet you're just assuming like a permeability value and an initial porosity without saying, well, this is the type of porosity I'm dealing with.
Okay, so so you're thinking about the type of porosity. So if it would be moldic or yeah, the different types, right?
Yeah, any. I mean that will influence the flow, the turbulence of the flow within the pore. You know what I mean?
Yeah. So this model is a bit too simple to answer kind of those questions because this model doesn't assume any type of porosity or any specific times. It just basically says that we have porosity that is evenly distributed in the rock. So it can't really take into account the different types of porosities that you would have. So if you would model that, then you would need a more complex model that can represent that.
Can I add something?
Yeah.
It's always bad for the supervisor to jump in, but I can't resist it. I think your questions are really pertinent, but the first step is to work out what the potential for diagenesis across lithological boundaries is. And that's the question that Ivan's addressing first of all. And then the fact is that you're discussing the pore shape, size, connectivity, control the extent to which that diagenetic potential is used up rapidly, just below that lithological contrast, or it could be transmitted and effectively that diagenetic could be felt further down away from the lithological boundaries. So I think that's kind of the next step, isn't it? And the idea, I think, is we want to try and run some models which do incorporate an element of bypass flow. And that's a way of getting the diagenetically more active waters to flow more rapidly for short periods of time through that more interconnected part of the pore network. So I think that's kind of the next step. But the first thing you have to find out is how much difference does it make if you go from lithology A to lithology B?
So this is just assuming a single permeability, isn't it? So
yes.
Yeah. So that there's ways of changing it.
Yeah, but I'm pretty sure that you can achieve the same permeability with completely different pore types, and the area of reaction of the fluids and the rock will be completely different, whether you're dealing with a
That's what a multiple interacting continua type model does. It allows you to specify bypass flow routes and for you to have interaction between those bypass flow routes and the matrix. And effectively, it's really simplistic. Again, as a starting point, you just divide it up into a series of sugar cubes. So you're assuming your bypass flow routes are all connected to each other and that you have a series of matrix blocks at different distances away from those bypass flow zones. The ultimate is the sort of model that we're aiming for from Drew and Tom's work, where we have a fully three-dimensional representation of the complexities of the pore geometries based on CT scans, which we can then put the same fluids through. But you have to start with something simple and check you understand a simple model. And even a simple model throws up all sorts of complexities. So I'm always wary. It's very easy to create a lot of complexity early on, but you've got to start simple, understand each step, and then build up complexity. And I'm really bad about that because I get over enthused and want to model everything at once. But I've learned from my grad students that you need to do one thing at a time.
Yeah, good questions. And certainly, this is, again, we're early stages on this, so there's a lot more to do. Yeah. Has anybody got any other questions? Anything they'd like to come back to? Tom, Drew, discussion on looking at these modern settings and what we can learn from those. So So yeah, I mean, I'm quite interested. Maybe. Oh, hi, Sarah. Did you have a question? Your camera's just popped up.
You're on mute, Sarah.
I just needed to ask Stephen, I've got to come out of Zoom to change my security settings. Could you make me a co-host as soon as I come back in, please? Thank you.
Good luck. Can I?
Hi, sorry, I'm going to just have to step in for a second. Sarah, you are already a co-host. Please, can you go back to the green room? I'll come into the green room and try and help you out. Sorry, guys.
Right. I asked Tom or Drew or maybe Fiona about your scans, the X-ray CT scans that you've got of these burrows and so on. How? Hi, Hilary. You do work on this as well. What sort of resolution have you got on those, and are you what's the plan with them? You've taken cores and then you're trying to reconstruct those in 3 dimensions. Are these sort of centimeter scale, or you just tell us a bit more about those, because that's really quite interesting to see those.
Yeah, sure. I could talk on that really quickly. I think our cores are pretty small comparatively, centimeter scale. So when we were in the field, we took 2 of our fat cores, which were a bit shorter, maybe 40 to 50 centimeters in length. And we had our longer cores, which were a lot skinnier, that were about 60 centimeters. And so the photos that you saw in my presentation were from the University of Bristol, which were the skinnier cores, which we cut open. At U of A right now, we have our fatter cores that one of them we cut up to do the X-ray sampling that you saw. So that got a bit disturbed, but we have our other cores completely untouched. So I think we want to do our CT scans on those while they remain as equal as they were from the field.
Cool. And are you getting the enough contrast in there to be able to see all these burrow networks?
I think we should. There's another student who works in our lab who has, I think, less of bioturbation occurring, and he did some CT scans on his and saw it looks really good. So I think with ours, where we're actually seeing a lot of these worm burrows, we're actually going to be able to see them really well and outlined. At least I think we should.
Excellent.
Yeah,
sorry.
I'll just say that we did actually scan a core of Hazel Valix, one of Fiona's old students, at Bristol, and that one turned out really, really well. It was a drained core, so we drained the core fluids, and the clarity was amazing. When we scanned some cores that still had pore water in them, they were a little less clear, but it was still pretty good contrast. The reason we did these initial X-ray images, Murray and JP, the 2 technologists we're working with, are really used to dealing with those kinds of X-rays. And we also were waiting on the CT scans. We had duplicates of each core, and we decided to just cut them so that Drew could also get a stabilized tilt work for his class. So we kind of needed to, out of necessity, do some X-rays. But it's great to see the contrast, and like it'll be interesting to compare how well the 2 techniques work out, because really a CT scan should be an infinite number of X-rays, right? But we'll see if there's some maybe detail lacking in those. So we could have maybe a paired data set that will help Drew identify everything in there, because they're quite, in some cases, they're quite bioturbated, so intensely bioturbated.
Yeah, because it's always, the issue is always, particularly in carbonates, is getting that contrast so that you can really see things. And I'm used to scanning rocks and on a much higher resolution scale rather than sets.
Yeah, the X-rays you saw were very contrasted in Photoshop. There had to be a lot of work done to see all that.
Yeah, I'm not surprised, but it was good. I'm glad it worked, because be able to get a visualization of these things in 3D is fantastic.
I had a question for Tom. Oh.
Yeah, go ahead.
Tom, do you have any thoughts on the sort of ranges of the magnesium that you're seeing in your in the data from the different sites. The site one looks very clumped, and then there's lots of variation in the other. Do you think that's simply due to the groundwater that you showed? But there's also, there's within, I think it was site one and maybe site two that had like variable. One of them had variable magnesium, the other one didn't. But those are both not seeming to be affected by the groundwater.
Yeah, then the cost plots at the end. There was the site one, site two near the sea. They had essentially surface water levels of chloride, and between that very fine amount of Mg cell ratio, so very similar Mg, and then a couple of bits from site two were higher magnesium. It was only the site three that the reduction in magnesium relative to chloride, and that was along potential mixing between the wells. So I'm not sure what magnesium, but first looking at it, and it looked like a more obvious depletion. Certainly there's some of the site one is possibly depleted relative to the surface water, and whether there's any dolomite or higher magnesium something, but I'm not sure. But
I guess something to keep our eye out for.
Yeah, a lot more things against each other and getting more data.
Thanks.
Did you have a question? Dika, sorry, your camera came on. I wondered whether you had a question.
Sorry, are you asking me?
Yes.
Oh, I don't have a question. I was just in the breakout room doing breakout room stuff. That's all
That's
that
fine.
on.
No, that's okay. I'm just checking that I'm not ignoring you there.
Oh, thank you. Yeah.
Yeah. No, so I think we're nearly up to time on the break. I'm really excited about these results, and be looking forward to seeing what comes out of the follow-up work for this. I realise it's all very, very fresh, and well, for all of you actually, you're all sort of been, just got hold of this data and analysing it. And so I think come back next year and tell us some more about where it's all got to.
Kathy, was Arnaud appropriately excited about his rocks?
Yes, is Arnaud still here? That was a really nice summary of what you did on the.
Oh, good. I didn't see it. There was I had a student coursework assessment deadline that coincided, and there was a slight flurry, let's say, of activity. So I was dealing with that. But he was all right, was he? Yeah, no, Arnaud gave a fantastic summary of everything from Sunday's field trip. So yeah, it was really good. We nearly ran out of time on it. Okay, I am going to hand over to Alessandro, who I could see a minute ago, but I can't see now.
Yep.
Ah, there you are. Sorry.
Yep.
The trouble with 3 screens. Trying to find you. So we've got a couple of minutes before we start the next session, and Alessandro Mangioni's postdoctoral researcher is working with me in Manchester, is going to chair this session. So I'm going to hand over to him as everybody starts to filter back. We've just got a minute or so before we get started again. Thanks very much, Alessandro.
Thank you. Okay, so welcome to the last session of the day. So we have three presentations, and each presentation will last for around 12 minutes. And then after 10 minutes, I will give a warning to the presenter, so they have additional 2 minutes to finish the presentation. So the first speaker will be Sarah Robinson from Imperial College in London, and the presentation will be about time, temperature, and pressure, kinetic similarities and difference between carbon dissolution, during precipitation, and kerogene thermal decomposition during burial of Cretaceous micrite sediment. So it's for you to go ahead.
Can you see my screen?
Yes.
Hi everyone, so I'm going to be discussing the kinetic similarities between carbonate recrystallization and kerogene thermal decomposition in Cretaceous micritic sediments, and I'm based at Imperial College London. So why have I decided that this is something that is worth researching? What is the problem? Why do we need to know these similarities and differences? Well, organic matter maturation and calcite recrystallization are both influenced by temperature, but how do they behave during burial? Do they behave similarly, differently? And what can these two things tell us about? What's the importance? So the importance is understanding these kinetic reactions during burial for both proxies. We can then utilize each proxies either in conjunction together or using one to back up the another to understand burial histories with a much greater in-depth knowledge than if we just use one or the other. And my aim for this presentation is using rock eval and carbonate clumped isotope analysis. I'll compare the results from the same samples using both techniques and compare the temperature proxies obtained from both. My hypothesis is that carbonate clumped paleothermometry will measure the calcite recrystallization, which is primarily driven by temperature, and will record the point at which recrystallizations occurred. Whereas when we look at the organic matter maturation, this requires sufficient temperature, but also requires more time in order to reach different points during maturation. So I hypothesize that at greater temperatures, you'll see a greater temperature from clumped isotopes than you will from organic matter. So this case study is the Eagle Ford Shale in Texas, and within this, it's from the Cenomanian to Turonian, so we're looking at late Cretaceous sediments. These sediments are carbonate rich, but also organic rich, and we see TOC values of up to 11% in the lower Eagle Ford Shale. The depositional setting for the carbonates and the organic matter is a shallow water platform, as you can see here, and it's just at the base of the Western Interior Seaway and just before we get to the Proto Gulf of Mexico. You can also see that we have a thick deposit of the Eagle Ford towards the southwest, in which it then thins out towards the northeast. So the data set I had available was 17 outcrop samples, which have been analysed in a previous publication by myself, and that's Robinson et al. 2022. And then this research adds on to this already published work using 3 wells. And these wells span different maturity windows. This spans the post-mature, the oil and gas window, and the dry gas window. And in total, including both studies, we have 42 samples. So the methodology, I use a novel technique called carbonate clumped isotopes. And what that is you have a calcite or any sort of carbonate sample. Within that, you have the lattice. And this lattice is made up of oxygens, carbons, and you've got the heavy and lighter atoms. And then we have the clumping of the heavier bonds, which we use to measure carbonate clumped isotopes. At Imperial, we have an automated system, so we can purify our carbonate samples to produce purified CO2, which is what we run through the mass spectrometer to analyze this anomalously heavy CAP47. So basically, when you get these CAP47 results from the mass spectrometer, low temperatures are therefore heavy isotopes. This means that these isotopes will have clumped together, so the O18 and the C13, If we're getting high temperatures, these heavier isotopes will actually be more randomly distributed in the lattice and won't be clumping together. So the results from the work so far, if we look at the organic matter maturation, we can see that the outcrop samples are immature, so we would assume these are less than 60 degrees. That one of the wells, well B, is within the gas condensate or the oil to gas condensate window. Then well C, we have in the dry gas to post-mature window. Unfortunately, I don't have any Tmax data for well A as it was all degraded, but we do have a few measured vitrinite reflectance data, and that indicates that that well is also in the post-mature window. Looking at the carbonate clumped isotopes data, we can see that from the outcrop samples, we're actually reaching temperatures of roughly 40 degrees all the way up to 110 degrees, which if we look at the data before, the outcrop data showed that the outcrop samples were immature, and we would assume that's less than 60 degrees. So we're already seeing a discrepancy within the results. And then if we look at the well samples, what was actually quite interesting and also kind of frustrating at the same time is that we were measuring temperatures of 550 degrees in some of the post-mature samples, which is we have no geological explanation as to why they could be that hot. So what we actually decided to do was, with clumped isotopes, as you increase the temperature, you have more and more of an error. So looking within the 95% confidence interval, we have assumed that the overlapping temperatures of all of these well samples is approximately around 200 degrees if we look at the very edge of each of these error bars. So then when we look at what the organic data was telling us, we had 3 different levels of maturity within those well samples, 4 different levels when we also include the outcrop data. However, if we're assuming that all of these well samples have probably reached a similar maximum burial temperature, which is this 200 to 225 if we look at the 95% confidence interval, how come we have 3 different levels of maturity? What is going on? So that was where I needed to investigate next. So when we look at organic matter maturation, as said right at the beginning, I hypothesized that this was driven by temperature, but not only temperature, but by time. So if you look at the hydrocarbon production, you have temperature down on the y-axis and we have time on the x-axis. So what I have hypothesized is that this kinetic reaction during burial, if you were to reach, let's say, 200 degrees, you need to be at that temperature for a sufficient amount of time in order to pass from the immature window to the oil window to the gas window and then finally to the post-mature window. So therefore, I think if we look at well A, B, and C, that these wells actually all reach the same temperature, but have probably not been at that same temperature for the same amount of time. And if we look at where they're based stratigraphically, they are actually slightly offset from each other. So if we had some sort of tilting event once these have been deposited, if they reached shallower temperatures or stopped and weren't at these hotter temperatures as long, this would be feasible. As I've said at the beginning again, looking at the carbonate diagenesis, there was a number of things with regards to the hotter temperatures that we had to consider. Are these artificially too hot? Is it contamination? Or is it actually recording a process that's occurring? We eliminated contamination very early on because we attempted to clean the samples multiple times using different methods. We also monitored the samples using standards and there was no indication of any severe contamination. So then we had to think, right, so what are these temperatures measuring? So this can be a number of different things during burial for carbonate diagenesis. We could have had isotope bond reordering via diffusion. We could have had solid state mixing where we have 2 phases mixing. And then there's also carbonate recrystallization. When you look at isotope bond reordering, we end up getting, you'd measure a blocking temperature. Therefore, we would have actually expected we'd have lower temperatures rather than hotter temperatures, because this actually, it measures cooling rates. And then when we looked at solid state mixing, in order to artificially produce temperatures of 500 degrees, you had to have extremely ridiculously negative isotopic compositions for the carbonates. And again, we had no way of viably saying that this was the reason. Then finally was carbonate recrystallization. And this is when we've had, the sediment has been buried, the sample will have dissolved, the calcite will have dissolved and then reprecipitated. And the point at which it reprecipitates is the temperature at which it records. So this, out of the three main features discussed here, I felt was the most reasonable to explain what the temperatures were recording. Again, I don't think 500 degrees is realistic. I think within error, looking at 200 to 225, geologically, we can explain this. So calcite recrystallization, you can have intact, where it will represent the original.
Sorry, Sarah, you have 2 minutes.
Where it will represent the original deposition. We can have partial, complete, and then complete recrystallization that is actually a mixture of different temperatures. So again, my sample size is quite big, but each section, for example, in the outcrop, I only had 40 meters of stratigraphy. So I think we have had either partial recrystallization here, and that's why we preserve such a range of temperatures, or complete, in which we preserve a lot of different temperatures. So the kinetic similarities and differences. So again, both of them are clearly driven by temperature, but I think time is a much greater influence on thermal decomposition than recrystallization. We're actually probably getting almost instantaneous recrystallization when we think of geological time. But now I'm trying to investigate what are the actual rates of these processes? Why are they so different? And can we model this difference? So my current work is looking at geochemical modeling. So far I've successfully modeled the calcite recrystallization through time and the organic matter decomposition when it comes to immature samples. So samples that haven't reached over 110 degrees. However, when I've gone to move on to look at these hotter samples that have actually reached maturity, I'm finding that the equation originally used, which was just a simple first order Arrhenius equation, really doesn't explain this. So what I want to do is try and model using a second order rate equation and try and graphically interpret this and determine a rate for the thermal decomposition. So to conclude, clumped isotope temperatures represent calcite recrystallization. The measurements at high maturations, clumped isotope measurements at high maturations, and therefore high temperatures, are subject to large errors. Thermal maturation values and clumped isotopes don't match exactly. The kinetic variations in thermal decomposition of organic matter and the dissolution of recrystallization of calcite do vary and are not completely similar, especially at hotter temperatures. They're both primarily driven by temperature, but affected differently by the amount of time at those given temperatures. And then the future work is to try and actually successfully model this using multiple rate equations throughout burial. Thank you.
Thank you, Sarah. Can you just stop sharing?
Oh, yeah.
Thank you. So is there any question for Sarah? Okay, so first question. Thanks for a great talk, Sarah. Can you say something about the diagenetic textures that you were sampling for the clumped isotope analysis?
So yeah, I completely forgot to include, so I had some thin sections that were done on the well samples, and we can see that there is, so we have two to three different types of calcite recrystallization within the cements. And the only way I could really tell the difference is the size of the crystal grains and the morphology of the crystal grains. These again are not in every single sample that we, on maximum, was either one type or up to three.
Second question, lovely data. Got to love a more complex picture than you originally expected. What was the primary mineralogy of your calcite?
Primarily mineral. So do you mean? Yeah, it's just it was calcite. I didn't have any dolomite or anything. Was that the question?
Was this the question?
Mineralogy of the calcite.
Was it digitally?
Yes, it was originally deposited as calcite. So because my samples are micritic, so they have a very, very low porosity. So therefore, we've actually interpreted it as a recrystallization trend. Therefore, we've got low water rock ratio. So it's rock buffered calcite, recrystallized calcite.
Okay, so the next question is great, thank you. As a follow-up to your answer, did you see any difference between the temperature of your different calcite microtexture? Sorry if I missed this.
No, so we actually did see this in the outcrop. The hotter samples had this third calcite cement, whereas when it looks at these hotter temperatures, it varied drastically. Like there was no pattern between if you had type 1, type 2, or type 3. They had quite a mix. So we weren't able to say that this cement was this hot and this phase of cementation was the hotter phase, for example, unfortunately.
Any other question? So I have a quick one, because you were talking about maturation of organic matter. So I was wondering whatever either you or someone else is working on a basic modeling to try to understand the timing of maturation.
Yeah, so that was something that I was hoping to do in once I'd done the rates and things. But other people, because the Eagleford is such a well studied area for organics, I've actually been very lucky as in being able to use other people's modeling as such, whereas I'm trying to now actually understand more the kinetics, whereas usually when people look at organic data, they are bothered about immature, mature, what maturity level. And then, so I've used some other people's basin modeling where they've looked at the temperatures history to see if, for example, the clumped isotopes saying that it was 200 to 225, is this realistic from their basin modeling? And with an error of the modeling software, 200 degrees isn't unreasonable for the geological history.
Okay, thanks a lot. Any other question? Anyone? So otherwise we can go to the next talk. So thanks again for your nice presentation, and we go to the next talk from Fang Yang from University of Wisconsin-Madison, and the title is Constraining Marine Cap Carbonate Formation using a geochemical model coupling dolomite formation with dissolved silica. So it's over to you.
Oh, sorry about that. Do you all see my screen now? So hi, everyone. My name is Yihan. I'm now a postdoc at Washington University in St. Louis, and this is I actually defended my PhD like last month, and so this is part of my PhD chapter. So today we're gonna switch the gear a little bit and start talking about using geochemical models to couple dolomite formation with dissolved silica to try to understand the Marinoa cap carbonate formation. So let's start it. So the cap dolomite is what we talk about during the cryogenian, during the snowball Earth event, which is when presumably the Earth is covered entirely by glaciers. And then towards the end of it, there is a rough layer, usually 100 meters thick of carbonate, usually what we call them cap carbonate. And a lot of times they're actually composed majority of just dolomite. And based on the geologic record, there are two major snowball Earth periods during the end of the Proterozoic, the Sturtian and the Marinoan. So the reason why we choose the Marinoan for this study, because we try to keep the modeling simplified, because I'm a mineralogist in training, so geochemical modeling is not my strongest suit. So the reason we choose Marinoan is based on literature, marinoan is the one that composes almost all just dolomite across the globe. Instead, the sturtium, in some cases, they're going to have calcite composing the carbonate, which is going to cause a problem that we need to consider about local heterogeneity and all the other factors. So we just use the marinoan because it's entirely just dolomite, so it's easier for us to calculate. So the reason why we started doing this because we saw this amazing paper from back in 2019, and then they're using couple carbon and silica cycles, and then they're using MATLAB, which is a language I know how to use, and then they can actually predict the carbonate precipitation, which in this case is entirely calcite, because they are not so sure about how to incorporate the magnesium cycle because dolomite precipitation is a mystery so far. So they only use calcite to calculate the result. And they do see there's a peak overlap with the silica burial along with the calcite burial, which makes sense because you're seeing a really high elevated PCO2 level towards the end of the snowball. And then that's how it's getting out from the entire glaciated state. And so you need the PCO2 to accumulate to a certain level, so it starts to deglaciate. And then that extreme high PCO2 level, in that case, is going to cause very intense chemical weathering. And then so then you're going to have weathering silicate rocks, and then you're going to have a lot of silica input into the ocean. So what we want to do improve on that model is that we want to incorporate the dolomite precipitation in that model as well. From my previous work, and we know that silica is actually a catalyst that can help dolomite, at least disordered dolomite, to precipitate at room temperature. And the good part about dolomite is that its trend is overlapping with the dolomite abundance changes through geologic time. So here is a macrostrat compiled data of abundance of dolomite within carbonate rocks. So you're seeing from the left, from like the beginning of Archean, Hadean, and then go all the way to now. We're seeing a dramatic decrease in dolomite abundances after Proterozoic, and especially to around Mesozoic, the abundances drop dramatically. This is showing in a first order approximation, showing a very similar trend with the silica abundances in seawater. Before the appearance of diatom and all the other siliceous microorganisms, the dissolved silica level in seawater is close to saturation state of dissolved silica. And that fits in our favor because Proterozoic is still around time when you don't have too many siliceous consuming microorganisms. So we should have a high enough dissolved silica to catalyze dolomite formation. And from synthesis work, we know that with increasing of dissolved silica in your solution, you're going to have increasing of dolomite precipitate as well. So in that case, we can actually couple this and put it into the previous model and try to understand how is the paleo seawater, especially during the Cryogenian, during the marinoan snowball earth, and then right after during the deglaciation period, how it's going to change. So this is a simple box model similar to the previous paper that we put together. So in this case, the purple indicates the silica, and then the blue indicates the magnesium. So essentially what we changed from their model is that now we have diopside weathering instead of wollastonite weathering. Of course, you're not going to really just weathering diopside. It's just an approximation of the average continental crust. And everything is very similar to the Penman and Rooney model. We're just adding an independent cycle of magnesium, but the magnesium precipitate in this case will be dolomite. And the dolomite burial rate is coupled with your dissolved silica concentration. So that's how the free cycles actually link together. So this is a very simple schematic model which show how this is working. So on the upper right, you're going to see the snowball earth period. So you're going to have the sea ice covering the ocean, and then you don't have air-sea exchange shutdown. So that's for a hard snowball case. But sometimes when people argue there might be not entirely covered, so you still have a little bit of air-sea exchange. So you still have a little bit CO2 that can diffuse into the ocean. So that's what we call a soft snowball earth situation. And then during deglaciation, on the middle plot here, you're seeing on the left-hand side, you have the silicate weathering. On the right-hand side, you have the carbonate weathering. And the sudden input of the magnesium, calcium, and silica from the silicate weathering gonna help promote dolomite precipitation really fast. And then you're gonna, because of this sudden input of material during the beginning of deglaciation, you're gonna have a stratified ocean of the surface water and the deep water. Later on, of course, you're gonna have the mixed seawater, and then you're gonna start seeing the barrier precipitation. So here is our result, our modeling result on the right-hand side. So essentially, you see that like right after the snowball earth, you see the appearance of capped dolomite, and as well as calcite and silica, of course. But the reason why we're not seeing significant amount of calcite in the capped carbonate, the Marinoan capped carbonate, is because if you look at the number, the dolomite precipitation is over 25 order of magnitude higher than calcite. So that means you're not going to see less than 0.1 or even less than that % of calcite in your total carbonate. So that's why we're only seeing dominantly just dolomite. And then you're also seeing a huge pH drop too. So we try to compare to other people's hypothesis on how long this will work, this will fit with other people's models. So the blue region is how the entire different set of our data through different kind of sensitivity tests. And then our duration of formation range from 0.3 to 1 million years. So which fit like within the range of some of the data, but slightly on the longer side. So we can do all kinds of sensitivity tests. You can do calcium magnesium concentration. You can do soft snowball earth, hard snowball earth. You can change the PCO2 level, and then you can play a lot of different things with it. But the good part is you can actually provide a lot of constraints by this model on the seawater chemistry changes and also on the weathering. So the first thing we have for sure, this is a very solid constraint, the appearance of capped dolomite. In order for the capped dolomite to show up in our model, you need a certain amount of silicate weathering. So by silicate weathering, I'm talking about the silicate weathering % within the whole total chemical weathering. So on the left-hand side, you have 100% silicate weathering. So that means in the chemical weathering, you have all the silicate. There's no carbonate being weathered at all. And in that case, you're gonna see a very sharp dolomite peak showing up. And on the other hand, when you have 100% carbonate weathering and no silicate weathering, the dolomite peak will smear out. There will be no capped dolomite precipitated. That's because in our model, dolomite is coupled with the dissolved silica concentration. So in that case, when you don't have a really significant silica peak, you're not going to see a significant dolomite peak. That's what we're showing here in 2 red circles. So if we plot it in all just different kind of condition, so NC means the carbonate weathering percentage, NS means the silicate weathering percentage, 0.5 means 50%. So calcite is actually not too sensitive with whether silica is present or not. On the other hand, dolomite is very sensitive to it. The dolomite, in this case, you can have as low as about 20% of silicate weathering, and then you can be expecting to see the capped dolomite to come out. And then this is coupled, as I was mentioning earlier, is coupled with the silica, the burial rate. So that's the first boundary we have. You need at least 20% of silicate weathering for the capped dolomite.
Sorry, you have 2 minutes to go.
Okay, thanks. So the second boundary, which is more ambiguous, is matching with the pH suggested by boron isotope. So people use boron isotope to measure the capped carbonate, and then they see that the pH need to swing from 8 point something all the way down to a little bit over 7. So that's what we're seeing, the red circle, the dip over here. And then you're seeing here, this is a range of sensitivity tests we run. So 1.0 is just 100% silicate weathering. As you can see, increasing of carbonate weathering actually helped the silica, but you never reach that low level as just slightly above 7. However, if you incorporate in the single glacier chemical weathering, you can actually further drop down the pH. So, and then the trend actually reversed in this case. So essentially, what we are seeing here is that in order to match with the boron isotope, if they're accurate, if they actually do preserve the original data, this suggests that capped carbonate, the Marinoan capped carbonate, need to have about 70 to 60% silicate weathering to actually show the pH dropped down as low as the other paper suggested. So in conclusion, we provide additional constraint on the chemical weathering rate, not chemical weathering rate, chemical weathering composition, seawater chemistry, and cap carbonate formation duration. So the deglaciation of Marinoans probably involve about 60 to 70% silica weathering. So that actually tells us it's actually weathering the pre-existing silica crust compared to the Sturgeon glaciation, when it's actually eroding more of the pre-deposited carbonate that's presumably from they accumulated from the boring billion. And that's all for my talk. Thank you so much.
Thank you. Is there any question for Jan? No one? So I have just like a quick question out of curiosity. This workflow is really nice, but my question is, whatever you are also going to apply the same workflow in other areas, just to double check that the results you're having in your study area are going to be the same or similar to, so your model is able to predict similar things in other areas.
Yeah, we actually thought about this. We think about like using it for the PT boundary, or if potentially we can use it for something with less dramatic changes, and then we can use more advanced ODE software, so it can actually speed up the calculation time. So right now, because we're using MATLAB to run it, and then sometimes it takes about 2 hours, 3 hours for each cycle. So if we use let's say if there's a particular area you want to build a box model for, we can actually use it for using probably Fortran and others to actually make it much faster. And that's actually that's probably one of the next steps we're trying to hope to do.
Okay, thanks a lot. So the next question is, sorry, I may have missed this, but can you discuss how sensitive is the model result to the mineralogy of your silicate that is weathered?
Oh, that's a great question. So for the lower boundary of silica weathering, it's very sensitive because that's a hard boundary. You need that amount of silica weathering for this dolomite peak to show up. So that boundary is set. For the higher end, like how much exactly, how high the silica weathering can go to, that's a little bit into the fuzzy area. We are suggesting it might be 60 to 70%, but depending on exactly the intensity of the chemical weathering and the intensity of the single glacier deposition, so how much carbon is actually being precipitated during the glaciation period, you can have very result on that too. So there's still quite a lot of wiggle room on the higher end of silica weathering, but on the lower end, it's pretty clear. Hope that answers your question.
Any other question? So thanks, Jan. Really nice study, well presented. So any other question? Okay, so thanks for a great talk, Jan. How does the amount of dolomite precipitation that your model predicts compare to the observed thicknesses of the Marinoan cap dolomite?
The absolute amount of the number might vary a little bit. So our model suggests it could be ranged from tens of meters up to even like a couple hundred meters thick, which is a little bit outside the range of what the actual outcrop is. But I think because it's still like in the close to the same order of magnitude, so we're still seeing I think the trend is working, but the absolute number is not that reliable.
Any other question? Okay, so any other question? Otherwise, we will move to the next talk. No. So thank you again, and let's move to the next talk. So the speaker is going to be Radlika Saini from the University of Alberta, and the talk is going to be about detection of early calcite to aragonite diagenesis in a modern inner carbon drum. So over to you.
Hi, thank you. So I have to keep my video off because my internet is a bit unstable, but the study I'll be presenting today is detection of early aragonite to calcite diagenesis in a modern inner carbonate ramp setting. So the aim of our study was to determine early aragonite to calcite diagenesis in carbonate sediments of Abu Dhabi. Abu Dhabi is a prime location for diagenesis to occur because it is a SAPCA environment, as shown by this diagram, where the water evaporates really rapidly due to the hot climate, which can concentrate these sediments with ions, which can amplify the diagenesis process. So the study location has already been discussed twice in two other presentations, so I won't dwell on this, but here's the Cantor Lagoon relative to the Abu Dhabi island. And then this is the sample collection site, also relative to the supertidal zone and inner SAPCA. So the most common type of carbonate diagenesis is aragonite transforming to calcite, and in modern oceans, we have calcareous organisms precipitate aragonitic shells. Once these shells are deposited, however, the aragonite loses the temperature and pressure that is needed to sustain on surface level, and it transitions to calcite, its more stable polymorph. And in doing so, the fossil gets preserved, but the original structure gets altered. Aragonite also has high relative solubility, as shown by this diagram, so it's prone to dissolution, which can also lead to loss of fossil. And these fossils are important because they're used for paleoenvironmental reconstruction studies. And as shown by the diagram on the right, it shows how the fossil record can be skewed if aragonite shells don't transform to calcite in time. So colony A and B existed at the same time. However, colony A shows great preservation, whereas colony B doesn't. So we wanted to identify this diagenesis through Raman spectroscopy. Raman is a microscopic tool which is effective for differentiating between two polymorphs. So for example, aragonite and calcite. Their spectra is really similar, but aragonite has a peak at 205, whereas calcite has a peak at 283. And those two peaks can be used to use as characteristic peaks for the minerals and be used to differentiate between them. So thin sections were made from core sediments from 1 centimeter to 26 centimeters below the sediment surface. So really shallow sedimentary layer. And the Horiba Explora Raman spectrometer was used at McGill University for all of the analysis. Lab Spec 6 was used for processing. X-ray diffraction was used to identify mineralogical compositions within the sediments, and stable isotope data was obtained from Saskatchewan Stable Isotope Laboratory. So this is the very first Raman map that I'm going to talk about, and this map was primarily made to figure out at what laser power is Raman the most efficient at, and at what laser power does not harm the sample or burn it. So at about 20 milliwatts, this Raman map is of a gastropod, of an area on the gastropod shell, and it shows all aragonite in red. And the spectra is also taken from all the red areas of the map. I also made some maps with laser power more than 20 milliwatts to see how higher laser power can influence Raman analysis. So in box A, there's the Shelly fragments that Raman maps were made from, and box B and C are two Raman maps made of that fragment. Box B shows the first Raman map, box C shows the second Raman map, and they're primarily the same, except that B has higher spatial resolution, so you can see really great transition between calcite to aragonite. So calcite in blue, aragonite in red. And the spectra also correspond to the colors shown in the map. So the same Shelly fragment was mapped for 2 more times using more than 20 milliwatts of laser power. And the third time, we see that most of the aragonite actually started transitioning to calcite due to laser-induced heating. And by the fourth Raman map shows complete transformation of aragonite to calcite. So once we knew that more than 20 milliwatts of laser power can cause aragonite to transition to calcite, we stuck with lower laser powers for the rest of the maps that I'm going to present. So this is box B shows the Raman map of an area of a gastropod shell. So this is the inner wall of the shell. This is the outer wall, and there's lots of borings. And most of the borings have calcite fillings in them. And this big blue blob is a foraminifera. And the spectra, again, the color of the spectra corresponds to the color on the Raman map. This is another map of a gastropod fragment. So if the tip was to just cut off and just get deposited, this is what it would look like. And in blue, again, we have calcite. In red, there's aragonite, and there's quite a lot of purple region in this map, which indicates specific regions where both aragonite and calcite are present, as also shown by the spectra here. This Raman map is of a region from a bivalve shell. And the highlight on this map is that it's hard to see, but there's little blue regions over here. And this shows calcite is actually present in open spaces or fractures within the shell. And again, the spectra shows different minerals present. This map is of another shelly fragment with some mud attached to it. But in the shell, we can see that calcite is kind of transforming from inside of the shell, as most of the calcite is inside, and then there's aragonite in the outer shell. This is a Raman map of a keloid, and it shows a mix of aragonite and calcite and the different distribution. And this is another map of a keloid, but this keloid's been heavily eroded. And there's no calcite, but there is calcite, but it's mixed with aragonite as shown in purple regions, and then there's lots of aragonite as shown by red regions. So the XRD data shows that aragonite generally decreases from sediment water interface down to the 26 centimeters of unconsolidated sediment. So everything in the blue here is aragonite, and everything in red is calcite. The stable isotope data, so this graph shows that in deeper sediments, there's generally lower amounts of delta oxygen 18 and delta carbon 13. And near sediment surface, there's higher delta carbon 13 and delta oxygen 18 values. So these values are pretty common for the sediments in the type of area. The graph here shows that there's a moderate correlation between percent aragonite and delta oxygen 18 as they both decrease. And this graph shows that there's a negligible correlation between percent aragonite and delta carbon-13. So I'll just discuss my results in the order that I presented. So laser-induced heating effects most likely occur during mapping sessions because you have a higher surface area under laser heat for longer periods of time, as opposed to spot analysis. And it's obviously caused by higher laser power. In our study, we found that more than 20 milliwatts of laser has the potential of causing heating during Raman analysis. And this creates a very significant downshift and broadness of the external modes. So the external modes are found in the lower wavelength region.
You have 2 minutes.
Okay, thank you. So this is what the calcite spectra should look like at room temperature, and this is what it looks like when the calcite's been subjected to higher or increased temperatures. Raman spectra can also reveal at what stage of aragonite to calcite transition a grain in a shell is. So if the 208 peak, which is the aragonite peak, is of higher intensity than the 282 peak, which is the calcite peak, that would tell us that there's more aragonite present in a particular area than calcite. This is also supported by which way the 700 peak is shifted towards. If it's shifted towards 703, it again has more aragonite and calcite, and vice versa. So Abu Dhabi early diagenesis is occurring in shallow sediments, and this is supported by the XRD data, as I showed earlier. And based on the sedimentation rate, this transition is occurring within the first about 900 years, and the most likely source of diagenetic fluids is concentrated seawater, which is linked to the high levels of evaporation experienced in Abu Dhabi due to the hot climate. So the oxygen 18 data could be showing a decreasing trend due to the hot water conditions. However, the fact that we're seeing a decrease with the percent aragonite can tell us that the oxygen 18 is changing with the aragonite transitioning to calcite. The fact that the carbon-13 has a negligible correlation with percent aragonite is a good thing, and it tells us that even though this diagenesis is occurring, our carbon-13 data isn't in fact changing all that much. So still, we need to use the stable isotope data extracted from these shells with caution, and more studies need to be undertaken to determine what effects these changes may have on stable isotope data and also trace element data. So to conclude, Raman spectroscopy is an effective method for identifying aragonite to calcite diagenesis in the natural setting, as it provides a spatial context and can be done in situ. And we can use Raman spectroscopy for identifying other carbonate transformations, for example, calcite's replacement by dolomite. It can be mapped using the same technique also in situ. I would just like to acknowledge McEwan University because that's where I did this project. Hillary Corlett for supervising this project, and Fiona and Hazel for also being part of this project. And thank you for listening. I can take any questions now.
So thank you very much for your talk. And we are moving now to the question part. Okay, so great talk. How accurately do your Raman maps differentiate between calcite, aragonite, and mix of the two? How confident are you that these maps have detected the correct composition within the area of the sample? Was not sure if you could quantify the confidence of your Raman spectroscopy.
Sorry, I'm reading that question. Okay. So before we did any analysis, we always calibrated the spectrometer during every session So we are pretty confident that we are seeing calcite where I'm saying we're seeing calcite, and aragonite where I'm saying we're seeing aragonite. Also because it can provide a pretty high spatial resolution, so about 1 micrometer. I'm pretty confident that wherever we're seeing a mix, or like wherever we're seeing a spectrum with both peaks, there is in fact calcite and aragonite present in those specific grains. If you could quantify the confidence of, yeah, we didn't quantify in my study, but it can be done, and it actually has been done in other studies. There's a study by Parker et al. In 2010 that quantified their results, and that were able to estimate the amount of aragonite and calcite in a particular grain by the intensity of Raman bands in their spectra. Do you ever see the solution of aragonite to create porosity in your sample? We didn't see any dissolution in our study. We mostly just saw bioerosion or borings in the edges of shells. But yeah, we didn't see any dissolution.
So really nice to catch up this process in action. Given that high magnesium concentration is generally seen as strong kinetic inhibitor of aragonite stabilization, it is interesting to see the transformation in such young and shallow sediments. Why do you think you saw more calcite in the interior of the shell you imaged?
Why do you think? Okay, I think there's, actually I'm not sure. So why do you think you saw more calcite in the interior of the shell you imaged? Are you talking about like that round shell that had calcite coming from the interior outside? If you're talking about that, I think that's okay.
Yes.
I think that's happening because in that particular shell, there's actually erosion inside the shell, like more erosion inside than there is outside. I think that's why there's more calcite interior than on the outside. Thank you for your interesting talk.
Do you ever see the calcite distribution following the original shell structures? You look a bit random in your images, which is surprising.
Do you ever see the calcite? Yeah, it does look a bit random. I mostly saw calcite in fractures, open spaces, or borings. So wherever there was more surface area revealed, that's mostly where we saw calcite in our study. Yeah, it might be possible that there's more organic matter in the interior.
Oh, okay.
Yeah, that's an interesting idea.
Any other question? Another question. Thank you. Another question. Were your isotope data just from the shells or were they bulk data?
They were bulk. Yeah, they weren't in situ.
Thank you. Fiona add, my also explain distribution not following shell structure. Any other question? So thank you again for your nice presentation then.
Okay, thank you.
You are on mute.
Sorry, that's not going to help, is it? Thank you. That gets us to the end of this session and to the end of today. So sorry, I'm just reading the comments at the end. That was a really fantastic set of talks. And firstly, thank you, Alessandro, for chairing that last session. And
thank you.
And to all the speakers in that session. So what we're going to do now, we haven't got any more talks. I'd just like to say a few thank yous and just wrap up the sort of the main part of the session. But what we've, Steve and I have agreed is that we'll keep everything open for the next sort of 10, 15, 20 minutes maybe. If anybody has any subsequent questions once I've finished talking or anything they'd like to ask the presenters from this session, and or anybody else actually that wants to hang around and have a bit of a discussion. So let me just push on quickly and do the formalities. And first and foremost, a huge thank you to all of our presenters and session chairs. For as much as we possibly can, we've had early career researchers chairing these sessions, and all of our talks are from current PhD students, recent PhD graduates and postdoctoral researchers. And when we set this meeting up in 2020, that was our sole ambition, was to give a voice to people who sometimes don't always get heard at major conferences, and who are at the forefront of a lot of really new and exciting research that's taking place in carbonate. So I think we've proven again today that there's some absolutely fantastic work going on out there on a whole range of modern, ancient carbonates, diagenetic processes, sedimentary processes, looking at modeling, characterization, and really bringing in some very new, exciting and interesting techniques. So I've thoroughly enjoyed today, and really appreciate you all putting time into sharing that with us. And as I say, to our session chairs for keeping the questions going and keeping everybody on time and so forth. So thank you for that. You will see that there was a new addition this year, which was our field trip report from Arno, the field trip that he and Pete ran down to the Wessex Basin. This was a bit of an experiment this year because when we started 2 years ago, nobody was able to move anywhere and go anywhere and meet up face to face. And last year we were just coming out of COVID restrictions, and we thought this year that we would give people a chance to get out in the field if they can, or if they could. And Arno was kind enough to offer to run the trips to the Wessex Basin for those people who were able to get to the south coast of England last weekend and actually look at some rocks. And he gave us a great piece of feedback on that this time around. So next year, hopefully we will see some more. That was a really nice addition, and I think was really highly appreciated by those people who were able to go out and look at those sections. Thank you to the IAS for sponsoring that trip, and indeed for sponsoring SEDS Online, but most importantly to Stephen and to Johanna at SEDS Online for keeping everything going today, letting everybody in, re-entering people who had problems getting everything set up, keeping all the tech working, and all the hard work that goes on behind the scenes in trying to make sure that this actually happens on the day. So very, very much appreciated. Thank you also to my co-hosts, Fiona and Pete and Rachel, as well as Stephen, who helped me review all the abstracts. Pete put the schedule together, kept contact with the speakers and so forth. So brilliant. I'm so pleased that we've had so many exciting new things to look at today, and really some things to take away and think about. So I think that covers everything. The only outstanding task, if everybody is willing to turn their cameras on, is that we would like to take a photo. If you don't want your photo taken, keep your camera off. And then I think Stephen's going to take a snapshot of us all as best he can.
I love it when the cameras come on and all you get. You know who you are. We'll give everybody a few more seconds. You don't have to put your camera on.
It's nice to see everybody out there.
But it is nice to see some faces, isn't it? All right, okay. So, all right, everybody say carbonates are gorgeous. Carbonates are gorgeous. There we go. One more for good luck. There we go. That was fairly painless.
That was fantastic. Thank you, Stephen. So excellent. Anybody who wants to stay around, we're not shutting down too quickly. But for those of you who can't stay, thank you very much for joining us and being such a great audience as well.
Cameras can be turned on, mics can be turned on if anybody wants to turn anything on. Thanks, Kathy, for all your announcing.
It's the easy bit.
Yeah, all the hard work goes on behind the scenes. We do appreciate
it does.
Joanna and Stephen, thank you so much. And all those that know how to tweet, whatever that modern stuff is. But I don't do, so.
If there's anybody who's got any further comments or questions, thoughts, feel free. Speak up.
I've got a question. How can we encourage younger people to ask more questions? I'd love to hear questions from people who are actually doing the science rather than old fogies like me that just have ideas. But it's the younger guys and girls that are younger people who are really doing the research and must have lots of questions. And it would be really good to hear more questions. Because that was kind of this whole conference sort of arose from a reflection at the Bathurst meeting in Mallorca. And one of the things Bathurst always wanted was lots of half-formed crazy questions. There's no such thing as a bad question. So we'd love to have more questions, and I don't know what we can do to encourage that. Any idea?
I personally think this is going to, the remote aspect sometimes makes people a little bit worried about asking questions. For some people, it makes them more confident to ask a question. For some people, I think they don't engage in the same way. Personally, the trend I noticed is there was a strong drop-off in the questions after lunch. Now, is that because the Western Hemisphere doesn't ask as many questions as maybe the Eastern Hemisphere did? Because we started the day with many people coming in from Asia. And maybe we're saying a cultural difference there. Maybe it was lunch that killed the questions, that we all had too much to eat and were just too relaxed and soporific. I don't know, but yeah, it is a good question.
I went to a conference that was virtual and they had questions, but it was, you could state your name or state just as a random like just as an anonymous don't know if that's the word, but for example, like I'm dyslexic, so sometimes it takes me a few minutes to write out a question, whereas if it came up as someone, not my name, there was a few grammatical mistakes, I probably just press send and I'm like, I'm sure someone will figure it out. I don't know if that seemed to help at that conference with, especially, do you know if you have any masters or undergraduate students that I think come to this, because they did last year, they might ask, it sounds silly, but sometimes if there's no name.
That's a really good point. Yeah.
Yeah, I can make it so that you can anonymize yourself whilst you're actually asking the question. We can maybe look into that for next year.
Sorry, I was just going to add that I recently attended a conference where they had panel questions. So like 5 people would just present back to back, and then there would be like a 10-minute or 15-minute question period at the end of the 5 presentations. And like so many people would ask questions because people have had time to like digest the material and then come up with questions pretty much. Because it's also sometimes hard to come up with a question right away, especially if you're like me, who doesn't have a lot of like experience as a grad student. but that's something I thought was pretty cool.
I think that's also a good point. And I mean, even I find that sometimes trying to frame my question in words, you know, whereas if you're actually in a conference room, you would stick your hand up, and I don't, you know, having the experience, I wouldn't mind sort of trying to speak it out. But if you are slightly less confident and you've got to type it, having thought of it, it does take a bit of time, and almost you feel like the moment's passed. So perhaps making it clearer that there would be time at the end to have general questions, which, you know, which could be put to the whole group and may or may not be have your name tagged to it, might be a good way to go.
Personally, I think it was the in previous 2 years. I mean, we are probably one of the few conferences that have done 3 years now of remote or virtual, whatever you want to call it, but I prefer the term remote because this is not virtual, it's real. Remote conferences. We've done 3 back-to-back, and this is the first year that we didn't have the breakout room for the questions. So we all stayed in there, we all heard the questions, which I think worked well, personally.
Mm-hmm.
Hi, Stephen. How are you?
I'm fine.
Long time no see.
Yes.
Yes, long time, yes. Regarding that problem, you know, because most of the researchers, the young researchers, sometimes they are like oriented in their own work, like not like the older generations, which normally they have more experience. That's why they will find out, you know, to write down a question or ask anything in particular regarding to the talk. I think this is the main issue. And also, as you said, you know, in the face-to-face conferences, it is easy to talk into the microphone directly. Than the online one, you have to put down your what do you think in words and write it down. It will take time. That's why.
So do you think opening the microphone and saying, you know, raise your hand if you've got a question would actually be more open?
Yeah, I think it will be more easier for the people to ask the questions.
That's a really good point. Thank you.
Thank you.
Yeah.
You know, I think I remember you for a long time. You have been in Manchester,
I've been
right?
around for a long time. That's all the grey hair.
Yeah, I didn't recognize you first. We were together in 1993 to 1996, maybe. Have you been? No? Or when did I see you? 2011? 2011? I don't remember.
Where was that?
I don't know. I have seen you somewhere.
Oh,
in Manchester or in the IAS conferences?
IAS conferences, maybe.
Yeah, maybe.
Bathurst.
Yeah.
Bathurst, one of my favorites.
Yeah. Bathurst. Yes. I've been there. Yes.
So I guess one last question. I'm going to have to go in a minute, unfortunately. But you know, we're coming out of the pandemic. We've kept this entirely online, and I think this is, you know, there's a change to a lot of hybrid meetings now. But there's, I mean, even looking at the people in the room now, still that, you know, we're talking across continents here. My personal feeling is that we should still keep it in this format, and that bringing the field trips was a good thing. I would hope that maybe that's something we could do more of, but that, you know, as a way of bringing in people who can't travel and can't afford to travel, or, you know, and particularly for a 1 or 2 day meeting, it makes sense that we should keep it in this format. But I don't know if anybody else has got any other thoughts on that.
Yeah.
I think you're right, Kathy. It's there is another Carbonate meeting on tomorrow that is 300 quid registration for 2 days, and that's out of the reach of very many people. The beauty of this thing is that everyone can come to it from across the world, and it's free.
Yeah, and that was what we intended, was to make it as open to as many people as possibly can.
Yes, free and online, best option. Yes.
Yeah.
So
my only concern was that people were getting a bit fed up of being online, but I think if there are fewer and fewer, then we look different, and that keeps it, fresh, if you see what I mean. So my personal feeling is that we should keep it in this format, because that's what it's, makes it so unique and special, is that I'm hearing talks from people that I would probably not hear from in other situations.
It would be good if we could build on the field trip model, though. If we could have something maybe in America, maybe something in the Far East, some different centres where people could actually physically get together as a precursor to this, which is sort of the whole idea of the Jurassic Coast trip, which was, great. I wish I'd gone on it, but it was lovely to have that report back as well. So
it was.
Thanks to the guys that run that.
I think maybe a bit more advanced notice and planning on those trips, because I mean, even if there's one per continent, there's still potentially a lot of travel required to get people to go along, and it doesn't necessarily have to be a field trip, it could be a tour workshop or something, but still, if you imagine one or two in North America, that could still involve a lot of travel for some people. So
I totally agree that having that field trip did add an element. I totally agree. We need to start the whole organisation earlier. The call for field trips needs to perhaps start
now.
Really early. Now.
Yes.
If anybody here wants to run a field trip, remember, the more field trips we can have. Remember, this can be in any country. You can run a field trip in your back garden, in your local city. The carbonates are the building stones of my city. That can be a field trip. Any kind of field trip. The more field trips there are, the better. They don't have to be in any specific country, because even if you have only one other person, if you turn up on your own. But no, seriously, it could be any number of people. It doesn't really matter, does it? I mean, at the end of the day, the idea is to show somebody some beautiful rocks.
And we could do it at any time of the year as well. So I think if we open the call up earlier, it doesn't have to be in May, because obviously that's not a good time in some parts of the world to get out in the field. So I think when all of us have, who normally organise this, get our heads together, we could perhaps get this advertised fairly soon. Right, guys, I'm really sorry, but I'm going to have to dash off. But thanks very much for staying with your thoughts. That's really helpful. See you all soon.
Likewise.
Maybe sooner than others, but bye. Nice to see you. Bye.
Bye, everybody. Bye.
Bye.
Bye. Bye.
Okay, is there anybody that wants to say anything else? Any discussions that want to continue? Happy to hang around, otherwise we can just shut down and go quiet.
I appreciated the slightly extra long lunch hour, I must admit. Well, not that I got any food, but it gives you a chance to just deal with a few other things. And I mean, the online thing is so manageable when you're trying to deal with a lot of other commitments.
This is true. I agree with that.
And I must admit, I'm still really happy that we're doing 10, 12-minute talks. I was so impressed with everybody's timekeeping.
Yeah, we had and that should be that pat on the back should go not just to the presenters but also to the chairs. It's hard being a chair when you've got to interrupt somebody. It's not fun. But it worked well.
Yeah, but I think the emphasis on really getting that high level message across allows us to have lots of time for discussion and include people working on a whole range of different topics. So I think that unless anybody disagrees, wants longer talks or more discussion, it's nice having.
I think it's about right. It's about right. Works quite well.
Good.
I agree. Right. speaking of discussion, it looks like this is coming to a natural closure. So I will just again thank everybody who's here. The last, what we've got, 11 of you, the last 11. Well done. You'll get your badges are in the post. No, it's terrific. Without the audience, it wouldn't work. Let's be honest. But without the presenters, it wouldn't work without everybody. So everybody does their bit. So thank you, everybody. We'll see you again next year. We will be back. Try and keep us away. Watch. The best way to keep up to date is to get onto Twitter or read things like the IS newsletter, things like that. You'll see lots of announcements next year about everything we're doing. In fact, you'll see them this year. We'll start organising this year, won't we? Won't we, Fiona?
We will, absolutely. Can't wait.
Okay, guys, I'm going to end it there. The recording
Thanks, Stephen. Thanks, Joanna.
Bye.
Take care, everyone. See you next week.
Bye. Thank you very much. See you.